Begin by the talk of Bartek Czech from Tsinghua University. We're very happy to have Bartek here, and I will hand it over to Bartek to start the talk.
Thank you so much. So thank you very much for the invitation to speak, for the opportunity to speak. I am really delighted. I also want to say that, in addition to my profuse thanks, I want to say that this talk is very much work in progress. So much that if I was giving this talk 4 days ago, half of it would be different. So the abstract I sent is also outdated relative to what I will say. And and also it's very much work in progress. With whom? My collaborators are Jan de Boer from Amsterdam, Labro from UBC. I think you know these people. And Zizhe Wang and Bo and Chen, who are graduate students at Tsinghua. You might not yet know these people, but they will also be applying for postdocs. So please remember these names. So that's directly in this project. A lot of what I will say is based on another project, which I'm not talking about, but actually they are very different, but they overlap in some very interesting way that I will try to sketch, with Gabriel Wang, who just moved from Fudan to Harvard for a postdoc, and Robert Ausendorf, who is an information theorist and at UBC in Vancouver. I also owe many thanks for what's in this talk to Janet Hang from Fudan, who explained a lot of what a lot of what I will explain to you, and this is very important for this work. So I'm not even sure when eventually we are writing the papers, who will write what, because all of these projects are so interconnected, at least in my mind now, that it will be hard to separate them. So all of these people are co-responsible for the good things in my talk. If there's anything bad, surely there will be, that's all my fault, but the good things are owing to them. And so holographic complexity mostly from second, but just from group cohomology, or even more broadly from cohomology. The group will play some role, but then we'll see if it really plays a role later. That's the subject. Let me just, this is a workshop on quantum information theory and holography, so I probably don't have to give this introductory slide, but let me just briefly barrel through it for completeness. So the last 15 years in AdS CFT have been largely inspired by the idea that maybe the geometry of space-time is the geometry of information in the CFT. And so, for example, if I take a reduced density matrix in a CFT, it corresponds to a specific region, which is called the entanglement wedge in AdS space, and I drew the entanglement wedge here. The boundary of an entanglement wedge, or a codimension 2 surface that defines the entanglement wedge, is an extremal surface. Its area is given by the von Neumann entropy of the density matrix. So we have these two examples are information theoretic concepts in essence. The reduced density matrix, it's von Neumann entropy, and they correspond to very geometric things in the bulk, a region of space-time and some areas. If I take the modular Hamiltonian, which is the minus logarithm of the density matrix, then that is an operator which generates boosts orthogonal to the RT surface that defines the entanglement wedge when I am close enough to the entanglement to the RT surface. So farther away, this thing develops corrections and becomes non-geometric. But when I am sufficiently close to the RT surface, then the boost orthogonal to the RT surface is the modular Hamiltonian. So these are examples of a relation between a geometry of space-time and the geometry of information. And I think that in this audience, these are familiar examples, so I won't belabor that point any further. So in this talk, I am interested in another concept, which is complexity. And so we have the belief or the conjecture is that that list I made before, geometry of space-time versus geometry of information in the CFT, and that this list contains at least one more entry, where the CFT entry is state complexity, and the AdS entry is some notion that quantifies how large spacetime is sideways. So in terms of the spatial extent of it. So there are various ways of measuring the spatial extent of a holographic spacetime. It could be a volume. It could be the action of what's called the Wheeler-DeWitt patch, which is the bulk domain of dependence of this volume of this spatial volume. You could, in fact, there are other ways of quantifying a spatial extent of a spacetime. For example, I could take the Wheeler-DeWitt patch, and instead of computing the action, I could compute the d+1 dimensional volume of that. That's also a way of characterizing how big a spacetime is. And Lenny Suskind's proposal and collaborators from 2014 and 15 is that these quantities, one of them, or maybe some other one, but he focused mostly on these two quantities, that one of them defines, or both, but one of them at least should define something called state complexity in the CFT. So before talking more about what this proposal really means, let's talk about what it should mean, which is the motivation part. So most of the motivation is coming from black hole physics. When I look at a two-sided black hole and ask what are the spatial slices as time evolves in this two-sided geometry, then those slices are getting longer and longer. And those longer and longer slices roughly correspond to, they grow proportional in time for an exponentially long period of time. And this is believed to be related to the fact that the time evolution operator, e to the negative IHT, is more and more complicated to write down as time progresses, and it never becomes simpler for an exponentially period of time. Whereafter it does, but for an exponentially long period of time, it just gets more and more complicated with time. And so that's the belief. It's the belief that it's that aspect of writing down time evolution operators, which is being visualized or represented by the fact that these spatial slices are growing longer and longer. And this seems like a match of parameters in two one-parameter systems. There is a suitably defined complexity of this time evolution operators parameterized by t on the one hand, and then there are the volumes of slices parameterized by t. So we matched two functions of one variable. That doesn't sound like a terribly compelling reason to believe the conjecture, but it turns out that you can make combinations of these things by basically making time sort of run forward and backward in a suitably defined sense. And what this prepares is a generalization of this geometry, which is called shockwave geometries. And for those shockwave geometries, the dependence of these spatial slices of their sizes is more complicated. It depends on more parameter, but it corresponds to the appropriate generalization of this time evolution operator for shockwave geometries. And so, in fact, we are matching not just two functions of one variable, we're matching two functions of arbitrarily many variables as you make more and more complicated shockwave geometries. And this is explained in the original paper by Suskind and Douglas Stanford from 2014. So that's the motivation for why Lenny and others believe that complexity in the CFT is related to spatial sizes in AdS. But there are big buts in this story. The first but is, what exactly is this complexity in the CFT? I have been very vague in talking about the complexity of the time evolution operator, but in general, what if it's not the time evolution operator? What about complexities of other states that are not related, where we're not just talking about the time dependence of a single state, but maybe more complicated comparisons need to be made between states, not the same state at different times, but completely different states. And what can I say about the complexity, the relative complexity, or just the complexity of those? So I need to be able to talk about complexity more than just for this simple time evolution operator. And that's the subject or the question of what is complexity in the CFT. There's also a question in the bulk, which is Lenny Suskind told us that complexity is the volume. Or then he told us that it's the action of the width patch. But both of them are more or less equally sensible because they satisfy the same set of basic consistency checks. But is that all? I mean, are there other possibilities? Even if we don't invent completely new, different possibilities, the fact that both volume and action are consistent with what we know about, or what we think we know about complexity, means that their linear combination also will be. So since we have volume and action, why don't I take different linear combinations of them? That also ought to be a complexity. Now, action and volume come with different dimensions. That means that these coefficients are dimensionful. If the coefficients are dimensionful, there is nothing wrong with inserting things that have higher powers of volume and action. Or maybe a cookie thing, such as action to the power of 3/5 times the volume to the power 1/pi. This is a dimensionful combination, which with the right coefficient could also contribute. And so what I'm trying to emphasize here is that there is no God-given way of quantifying spatial sizes of holographic geometries. But all that Lenny and collaborators really told us is that we should be looking at spatial size. And then whichever way they used to measure the spatial size, they were all consistent with their general qualitative predictions. So that means that all of these ways of measuring spatial sizes in AdS geometries should be presumed to be on an equal footing, unless we discover some specific feature that favors one of these options over other ones. But we haven't so far discovered such a feature. So all we have is a bunch of conjectures, each of them are on an equal footing. And the fact that volume and action are the currently best studied options doesn't mean that they are unique in any way. They are just the easiest things to conjecture and the easiest things to study. But maybe the true answer to complexity, whatever that is, even on the bulk side, is something we haven't thought about before. Even more so on the CFT side. We don't have a definition of complexity on the CFT side. And so the proposal about spatial sizes being state complexities in the CFT is at present infinitely pliable, infinitely flexible, or you could just say it's ill-defined. There are just too many options on both sides of this proposed duality. And so my goal in this talk is to propose a framework for complexity in the CFT. And this framework should be sufficiently flexible so it can accommodate all sensible bulk proposals, volume, action if it's sensible, maybe other things. And this framework will be based on some principled reasoning. So we're not going to just say, oh, I conjecture this and maybe it's true, but we're going to try to identify some guidelines, some conceptual guidelines that make the concept of complexity well-defined, both on the CFT side and on the AdS side, but probably with a bigger focus on the CFT side. And when I say principled reasoning, I have to start from something. So what will I start from? I will start from things that I believe I already know about holographic duality, which are the things that I mentioned on the first slide. The fact that RT surfaces measure entanglement entropies, the fact that modular Hamiltonians generate boosts, the fact that entanglement wedges realize or are duals to density matrices. These are the types of things that I will be using, or I will be using as starting points in my reasoning. And the final punchline will be that we need to be talking about a certain type of cohomology to properly define what we mean by complexity at this level of rigor. So that's the goal for today. Are there any questions or comments after these introductory words?
Sir, I have a question. Sir, will the relationship between the action and the volume remain the same if we consider fields like electric field or flavor, stuff like that?
To be honest, I'm actually not an expert on the specific cases that distinguish the volume from the action proposal. Lots of people that I know write papers with a flavor of your question, which is consider this system where the volume and the action don't behave the same. So here's a way to check the difference between the volume and the action proposal. That's good that there are papers like that, but they're not going to ultimately tell us what complexity is. And that's because we need to have a similar study at the level of the CFT, on the CFT side. If we had similar level of rigorous knowledge about what state complexities are in the CFT, then we could say, oh, this bulk proposal is right, this bulk proposal is wrong because it disagrees with what I have in the CFT. The problem is that we don't know enough about complexity in the CFT at the level of even how to define it. So that even if we have scenarios where volume and action disagree, we still don't know which one is right because we have nothing to compare with. And so that's, so in this talk and generally in my work, I'm not really inspecting particular geometries and volumes and actions because I'm interested in what principles define or constrain the concept of complexity, not what it numerically turns out to be in specific cases.
Yes, sir. Yes. Okay, sir. Thank you, sir.
Bartek, I also have a quick question. So this, as far as I remember, the volume proposal is non-unique to the extent that you need to divide, to make it dimensionless, you need to divide by some characteristic length, which Susskind mentioned in his papers. So in some sense, this is less well-defined than the action. And what the criteria if I remember correctly, what he had used is that the rate of change of complexity should be proportional to the energy or the mass. Now, if you divide by a wrong characteristic length, like square of some Schwarzschild, it might, I mean, if you divide by the wrong length, it might not come out to be equal to the mass of the state. Or so, can we say that the bulk one is perhaps a little, the volume proposal is a bit more, ambiguous than the action?
I mean, basically, what you're saying is that in this equation, this coefficient can be dimensionless, but the other ones are dimensionful.
That's right. And I think the way out he was suggesting is that dc dt should be equal to m or proportional to m.
Okay, so we can draw two types of. Okay, so we can have the facts that you mentioned are obviously true. So we can have different attitudes to them. One attitude is forget about the volume proposal. The action proposal is correct because it's the only one that's dimensionless that we know how to define. So basically, purely by eliminating all alternatives, we have arrived at a unique possibility, which is volume equals action, complexity equals action Wheeler-DeWitt patch.
Yeah, I will just be a bit modest, and I will say in the case of, at least in the case of flat space, when it is not, if you don't have a black hole in the space-time, there is no Schwarzschild radius to define the length which you define.
All of these things are true. So I'm trying to summarize the list of possibilities. Yeah, the facts you say are true. So I'm asking, what conclusion do we draw from this? Are we drawing the conclusion that all other possibilities are already known to be wrong because we have eliminated them based on pure reasoning? Or is it still possible that complexity in the bulk can be defined in a way different from the action of the Wheeler-DeWitt patch? Which of those do you subscribe to? Do you think it's an open question, or do you think it's a closed question because we already know that action is the right answer?
I think at least for the cases in which the characteristic length is not clear, I would say the action proposal is well defined, is the only well-defined object.
Okay, so good. So that's your attitude. My attitude is different. My attitude is that I don't yet know what complexity is in the CFT. And let me put it this way. I don't know what it is in the CFT. Therefore, I'm not yet in a position to judge whether complexity on the bulk side is correct. Because ultimately, I need to be making a statement of the form complexity in the bulk equals the complexity in the boundary. If I haven't yet defined it on the boundary in a rigorous way, I'm not yet in a position to say that it's right. And so I need to have a set of rules to tell me what possibilities there are, and then I will be maybe in a position to judge whether something is right or wrong.
Okay.
That's what I think. So, okay. So but this talk is going.
I have a question. So along the previous line, if you add the coefficients like this, for example, action square and other things, so doesn't this, from the effective field theory thinking, doesn't this coefficient should be have some bounded? I mean, they cannot be arbitrarily large or small.
Okay.
I mean, is there any possibility that this coefficient should be bounded or something? This coefficient of this action or volume square or volume cube, whatever you add.
Okay. Is the question, are there some bounds on these coefficients?
Yeah, I mean, can they be
how would I derive such a bound? Like you would say from an effective field theory point of view, but complexity is not an observable that's defined in field theory. So how do I know that effective field theory type of reasoning even applies to defining complexity?
Okay. So I'm just translate this to the field theory side. If I just translate this to the field theory side, so we can have some in terms of say in terms of the path integral, we have some terms that corresponds to the volume square and actions cube or whatever these terms. In that sense.
Okay. I think these. I just wanna. I think I'm gonna. I'm going to make a very different comment here, which is these slides are the motivational slides for my talk. I'm going to talk about something completely like at a different level of abstraction from what's here. The last thing I want to do is to debate the merits of the volume proposal versus the action proposal. I think we are not in a position to talk about volume or action yet. Instead, we should be studying first principles that define complexity rather than trying to guess ahead of the way. Is it going to be volume or is it going to be action? I think the little that we know about complexity, whenever we are making conjectures, we're just making guesses. And rather than trying to do guesses, I'm trying to write down some set of rules for complexity. Now, those rules, after I apply them, maybe they will favor volume over action, or maybe neither. But first, let's write talk.
Okay, thanks.
Right. So yeah, so if there are people in the audience who have written papers about the volume proposal versus the action proposal, this project is kind of tangential to your work. So don't necessarily try to think like, is it telling me that I'm right or that I'm wrong if I believe in volume or believe in the action? It's not about beliefs. It's about being rigorous in talking about complexity. So, okay, so before I go on, I just want to say one more thing about a heuristic for what complexity should be, which is tensor networks. So we're all familiar with the statement that an equal time slice of a AdS geometry that may show up in AdS CFT bears a striking resemblance to certain tensor networks, which are condensed matter theorist tools to represent many body wave functions. Every node of this network corresponds to a tensor with some indices. And so contracting those tensors forms an object with so many different, and the indices are vectors in some Hilbert spaces. And so contracting all of these things together gives me a state of many little Hilbert spaces, which is like a state of a many-body system. And that many-body system, when you choose that wave function, when you choose the tensors right, can approximate the ground state of a CFT arbitrarily well if you're working in the Mera tensor network. And the ground state of a CFT, if the CFT is holographic, is dual to pure AdS. And so this is an example of such a correspondence, but people don't just work with Mera, also with other tensor networks. The idea is that the tensor network is a picture of what the geometry is. And if the tensor network is a picture of the geometry, then the volume is what? The volume is like counting tensors. And so, in fact, one of the original motivations for the complexity proportional to volume proposal was the idea that let's just think of a spatial slice as a tensor network. And if it is a tensor network, then let's just count the tensors. And counting tensors, when I undo this discrete approximation, is going to be just like taking volume. So, so this is a good at the level of cartoons, but it is not good rigorously. And here is one example of why you can't just simply count tensors. And so the question is, with what measure? So let's say that I look at a little piece of a tensor network where some edge is contracted. Now I'm going to insert here a unitary and a unitary dagger along this leg. When I have U and U dagger, obviously they cancel out. So this is still the same tensor network. But I can combine the old tensor with U, and I can combine this old tensor with U dagger to make new tensors. Moreover, I can do it across every edge here. And so I have lots of possibility for what these tensors actually are. And if I'm lucky, some tensors might even cancel out as a result of these types of manipulations. And so this kind of freedom of including UU daggers across edges is a tensor network's version of knowing about, it's a gauge freedom. It's really like diffeomorphisms in the bulk of AdS. And just like volume is, well, if I do a diffeomorphism that doesn't preserve a spatial slice, then the volume of a spatial slice is not diffeomorphism invariant. And so similarly, when I'm just counting tensors, I have to be careful about in which of these gauge frames am I counting them and with what weight. And so counting tensors is a good heuristic, but it can't be the answer. And so that illustrates both some of the types of reasoning that constrains my choices for what complexity can be, but also it illustrates the need for being rigorous about the definition of complexity. Okay, so without further ado, let me tell you about what I actually want to say, which is that I'm going to tell you in the first half of the talk, this is the plan for the first half, I'm going to tell you about a very different system, which is understood in terms of a certain group cohomology. This is called the cluster state. It has symmetry protected topological order, and it is used in a scheme for quantum computing called measurement-based quantum computation. And we will see that this state has some very specific properties, and that those properties are defined, on the one hand, they are defined in terms of group cohomology, and on the other hand, those properties are basically the same properties that we want out of complexity in holography. And so this suggests that thinking about cohomology is actually the right way of thinking about complexity. And so that's what I want to tell you about. Are there any questions about the general plan? So for the next 20 or 15 minutes, I'll be talking about something which is not holographic at all, just as but treat it as a toy model for what we really want to say. Questions?
Yeah, just a quick question. So, so what you're going to tell us about, is it going to be this qubit finite dimensional system, or you are talking about quantum field theory?
I will be talking about this finite dimensional qubit system, and you should understand it as a toy model for a holographic CFT. It's a toy model that has it's a very toy-like toy model. It's very far from being realistic, but we will see what aspects of it are good.
All right, thank you.
So yeah, so the cluster state it's just qubits in some entangled state. For the purposes that I need, or for the purposes of measurement-based quantum computation, where this thing is most often studied, it's best to think of these qubits as living on a circle and imagine there are at least 6 of them. I won't really be using the fact that there should be at least 6 of them, but if you have fewer than 6, then certain things are harder to talk about. So let's just say that it's 6 or more. And so here is how the cluster state is defined. I'm going to take the plus state, which in the Z basis, it's just 1, 1. It's the plus 1 eigenstate of the Pauli matrix X. By the way, in this talk, when I say X or Z, I mean the Pauli X matrix or the Pauli Z matrix. That's the notation I'm using. And so I'm going to take 6 of these plus states. These are pure states of individual qubits, plus, 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 plus. And I'm going to act on them with C-phase gates. What are C-phase gates? In this Z basis, a C-phase gate is a 2-qubit gate which acts on 0, 0, 0, 1, 1, 0, and 1, 1 states. This is a 2-qubit gate as this diagonal matrix. Plus 1, plus 1, plus 1, minus 1. So it's just some specific gate that you use. And I'm going to use this gate on qubit 1 and qubit 2, then on qubit 2 and qubit 3, on qubit 3 and qubit 4, and so on around the circle. Moreover, because these things are these qubit gates, these C-phase gates, because they are diagonalized by the Z basis, that means automatically that they all commute with each other, so it doesn't matter in which order I apply them. So I just get a picture like this. And just to be clear about why we're talking about this, okay, and this is the preparation of the cluster state. Just take 6 qubits in the plus state and apply these 6 nearest neighbor C-phase gates, and you're done. That's the cluster state. So with this definition of the cluster state, the first thing that you might ask me is, what's the relation to holography? And what I want to say, what I want to say is that it's a little bit like a single layer of Mera, where I start with some completely disjoint Hilbert spaces, but then I apply one gate which mixes Hilbert space 1 and 2, one gate which mixes 3 and 4, and so on. And if I do this both here and here, then this is just like the cluster state, where I mixed 1 and 2, and in Mera I also mixed 3 and 4 and 5 and 6. But then I have to imagine that I'm doing exactly the same thing one layer higher, which is mixing now 2 and 3, and 4 and 5, and 6 and 1. So the cluster state is, roughly speaking, analogous to having applied a single layer of Mera. Holographically, it should be roughly analogous to having applied a single step of coarse graining in some sense, which holographically should mean that I have gone some level of or some amount of radial direction inwards in my holographic geometry. Very rough analogies, but that's the reason why this system is a toy model for holography for my purposes. Any questions about that? No questions. That means that either I lost everybody or it's all crystal clear. Please ask a clarifying question. Okay, really no questions. Is anyone still in the audience, or am I?
Yeah, just a quick thing. So should we think of the qubits as living on a lattice, or one dimensional,
Yeah.
2 dimensional? It doesn't matter, or
Definitely they're living on a one-dimensional lattice which has the topology of a circle. Okay, so maybe I won't insist on more questions and I'll move on. So
I have a question. Yes, sir. If you apply the C phase, to any 2 qubits, and the resultant is applied to one, and the resultant is found, and the C phase is applied between the resultant and an initial state, will it help in the would that have any physical consequences in the CFT? If we
I'm sorry, can you repeat the question? I'm afraid I didn't understand the question.
Yes, sir. If we apply C phase in between any 2 qubits, and we get a resultant, and if we apply a C phase between the resultant and another qubit in the initial state, would it have any correspondence to holography or CFT or something like that?
Yeah. So the let's see. So this question is going to be relevant in the second half of the talk, and I'm going to talk about this in a lot more detail then. So I'm going to postpone that question. For now, imagine that this C phase is combining some qubits into a collective state, and then these C phases, what you're really asking is the fact that these C phases act on overlapping Hilbert spaces.
Yes, sir.
What is the significance of that? And
Yes,
we will
sir.
be talking about it a lot in the second half of the talk. So let's postpone it until then.
Okay, thank you, sir.
It's actually a very important question, and thank you for raising it, but I'll only get to that later.
Yes, sir. Okay, thank you, sir.
Okay, so let's understand the cluster state in a better way. I will be using terms. So the next 2 slides are a little busy, and I apologize for that, but that's the only way to take advantage from this toy model cluster state, is to actually understand it and then move on to holography. And so here is a preparation of the cluster state. I have plus, 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 plus. Then I applied these C phases, and so up to this point, this is the cluster state. without these extra things that I have drawn here. So what are these things? Suppose that I wanted to make a measurement of the cluster state in my favorite basis, such as the plus minus basis. This is the eigenbasis of the X Pauli matrix. And I will get a bunch of coefficients for these basis vectors in the cluster state wave function. And so making all such possible measurements is equivalent to specifying the full cluster state in that basis. Well, specify it in some basis. So imagine that consider the process of extracting a particular coefficient in the expansion of the cluster state in this plus minus basis. Well, this is that coefficient, and this coefficient is obtained by these types of measurements. Yes. So if I do this measurement, notice that the full measurement that I have done, plus minus, there are 6 qubits on which I have to project, corresponds to a repetition of a basic object in this circuit that defines it, which is this object. And I have redrawn this object for you more clearly over here in this big square. So what is this object? It's called, notice that it takes whatever state is coming in from the rest of what I'm doing. It takes a plus, which is that initial plus before the application of the C phase. I apply the C phase, and then I measure one of these qubits in the plus minus basis, and the other one is left off going into the next similar process, and it will emerge again as an input for another such thing. Yes. So it's a combination of 6 things of this type. What are these things called? They are called half teleportations. So if you have studied quantum teleportation, you know that you have some input state, and then the recipient, you and a recipient have to share some entangled pairs, and then you make a measurement and the recipient ends up with the information. This thing is a little similar, except that we are preparing that entanglement between you and the recipient on the go by the application of the C phase. And in some sense, this thing is actually doing half the job of quantum teleportation. And so we call it half teleportation. I don't have time to explain more in detail about why this name is well founded or justified, but it's a fact of life that this thing is a half teleportation quantum protocol. And you can see that it's doing something like teleportation because this is me, this is the recipient of the information. After we have acted with the C phase, I will be making my measurement, but the recipient far away will be getting the information about the outcome. And so there is some non-local information transfer in the sense that I'm making my measurement here, but someone else is getting the information over there. And so that's why it's doing a job analogous to half teleportation. In a certain very precise sense, it's actually doing half of it. So a single act of teleportation can transport 1 qubit, which is like 2 classical bits. This thing really transports 1 classical bit, so it's half of it. Any questions about why measuring the cluster state in the plus minus basis corresponds to a sequence of half teleportations?
Well, I guess it's half just because there is no classical communication, right? For you to complete the teleportation.
To be honest, that's not the reason. It's not the reason because you get this plus minus here. So when you measure in the X basis, you either get a plus or you get a minus. And then I still have to communicate 1 classical bit to the outcome so that that person will get information that is in 1-to-1 correspondence with what came in. If I don't tell them whether I got a plus or a minus in this X measurement, then they're getting something random. But those random options are both related to this. They're just related by 2 different unitaries, and which unitary they have to apply depends on whether you got a plus or a minus here. So in ordinary,
okay, so in this box, you are doing a classical communication, 1-bit communication to the recipient or not?
If I wanted to use the box for the purposes of teleporting something, then I would have to send classical information. However, I am not using this to teleport. I am just saying that measuring the cluster state in this basis is using 6 times over the same procedure that would have been used in teleportation.
Okay. All right, thanks.
I'm not actually teleporting anything. I'm just saying that I'm doing the same thing that I would have to do if I had to have teleportation. But why am I doing it? Because I'm trying to get this coefficient of a basis state in the cluster.
All right, thank you.
So yes, so this thing depends. Okay. So thanks to the question just now, we see that what this procedure does, this single box, is actually doing different things depending on whether I get a plus or a minus. And so we call this A of plus minus as a linear transformation from this leg to that leg. Okay. And so I have computed for you what A of plus is and what A of minus is in terms of in terms of this H, which is called the Hadamard gate. It doesn't matter terribly what it is. The point is that we can compute it, and I computed it for you. Okay. But now let's think about what the actual state is. So I have these teleportation type transformations, and there are 6 of them running in a loop. You see, this thing is a loop. At the end of the day, this leg is connected over here. And so I have these 6 quantum teleportations running in a loop, and each of them provides for me an A plus or an A minus, depending on whether my measurement reveals a plus or a minus. So because they're running in a loop, I'm getting these A pluses and A minuses, 6 of them. The fact that it's a loop means that I have a trace. And that trace is exactly this quantity, which is the coefficient of the corresponding plus minus state in the expansion of the cluster state. So this reveals that if I wanted to write the cluster state in a basis, then I would be writing this expression. I just do these plus minuses, and I get these plus minuses from my measurements, and each one of them defines for me an A plus minus. The trace of 6 such A plus minuses tells me the coefficient of 6 plus minuses in the actual expansion of the state. So is that clear that why I wrote down this form of the cluster state in the box? I'm just basically rewriting what this circuit did for computing the coefficients of the state. I'm going to have to assume that the answer is yes. It's probably not crystal clear, but just trust me that that's a correct thing to do.
Could you describe the state in some kind of a stabilizer kind of formalism, saying, well, this is the symmetry, that's going to.
Yes, I can, and it's not conducive to my purposes of talking about complexity, but of course I could. And if you're interested, I can tell you after the talk, but it will, a different way of talking, this way of talking about the cluster makes a more direct contact with complexity. The stabilizer does not, but it also exists.
Okay, thanks.
Mm-hmm. Okay, so the next one is an even more of a busy slide than the previous one, but I need it to tell you about why the concept of cohomology is important. And so bear with me, and we're going to barrel through it, and then things will become clear. So every time I measure a plus or a minus, I'm basically getting an application of A plus or A minus in a circuit that runs in a loop. Now, it turns out that these A pluses and A minuses, I have computed them over here, but they're not terribly well behaved individually. But if I group them together in pairs so that I have A plus, I'm going to call it A plus plus. So this corresponds to making 2 measurements in a row on, let's say, qubit 1 and qubit 2, or qubit 3 and qubit 4. Then these A's actually are very nice. So A plus plus is the identity. A plus minus is just the Z Pauli matrix. A minus plus is just the X matrix. And A minus minus is XZ. So I want to notice that I labeled them with plus minus. These are the eigenstates of the X tensor X Pauli matrix on 2 qubits, but the way I have labeled them is also a natural labeling in terms of Z2 cross Z2 group elements. Yes, and so a question you can ask is, since I have these A's labeled by plus plus, plus minus, minus plus, and minus minus, and they are some operators, do those operators respect the same algebra as the group multiplication in this Z2 cross Z2 group? Yes, you can ask that. And so the answer is almost, but not quite. There are exactly 3 offending cases where if I multiply one A and another A, I am sort of getting the A that I should from multiplying minus, 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 minus. That gives me plus, plus in the Z2 cross Z2 group, but with an extra coefficient, which is -1. And so what do we call a set of operators which are assigned to a set of matrices which correspond to group elements, but which, when I multiply them together, they only produce the corresponding matrices for the group product up to a coefficient? And the answer is, we call it a projective representation. So in a normal representation, or an affine representation, AG times AH would be A of GH, but now we have AG times AH given by omega of GH, where omega tells me if I have a minus sign or if I don't have a minus sign in this supposed group multiplication. Now these omegas cannot be, so this is called a projective representation, and it's given by, it is at least partially characterized by this choice of omega. Now the omega cannot be chosen randomly, because if I take a product of free A's, then I can rewrite this product of free A's in two different ways using this formula. So I have done this for you here, and you can do this at home. It's probably too fast to verify it right now during the talk. But what I want to say is that at the end of the day, this thing is only a successful or like a consistent assignment of coefficients in my projective representation if I have the following equation, this box equation. And this box equation is called a two cocycle condition. And I will explain in a moment the reason why it's called a two cocycle condition. But that means that because it's called a two cocycle condition, that means that the omega is actually drawn from what's called the second cohomology of the group Z2 cross Z2 in coefficients which are U1 phases. In this case, they're just plus minus ones, but they could be U1 phases in general. So, so the punchline of this slide is that projective representations of G are classified by different cohomology elements in this group cohomology. It's also true that symmetry protected topological phases of matter are characterized by that. And in fact, the cluster state is in an SPT ordered phase of matter. And that was explained in this paper by Xiaogang Wen and Xie Chen and others. So I should probably next explain why this equation defines a two cocycle. So let me tell you about this in a second. But are there any questions before that? Actually, I have a question to the organizers. At what time must I really absolutely stop?
So it's 4, but you can take like 5 minutes extra. We have some discussion break after the next talk also, actually. So
I see. Okay. Well, so
but go proceed. Let's go on. Let's see how much you can.
Yeah. So why cocycle? So let me think of okay. So the way to think about it is think of this omega of GH. Think of G, H, and K that show up in this equation as labeling edges of a tetrahedron. And then think of omega GH as being the flux through the face that has edges labeled by G and H. And so that means that this equaling that is like a statement that the flux in through these two faces of the tetrahedron is equal to the flux out through the other two faces of the tetrahedron. And that means that the tetrahedron contains no source inside it. That means that this omega is something that doesn't live on a tetrahedron, but really lives on triangles properly. And so we say that omega corresponds to a harmonic function. It's harmonic because it has no source, higher dimensional sources that define it. And so that's the reason why this kind of omega that satisfies this equation is said to live in the second cohomology of the group. Any questions about that? Okay, so I need one more thing about the cluster state, which is that it can be prepared by a Hartle-Hawking type path integral of a topological field theory whose action is simply given by e to the is is given by this product of these cocycles. So what do I mean by this? Let's prepare a state. So here's a triangle which has 3 legs coming out of it, if you like, in the dual picture. and I want to label these legs with elements G, H, and K. And what I'm going to do is I'm going to write down what would be a vacuum, Hartle-Hawking type vacuum state for a topological field theory so this is a vacuum which comes out of nothing and defines a state on the borders of the triangle. So what I have to do is take sum over all possibilities of what G, H, and K are, and then I'm going to take the action for this triangle, which is the exponential of I times the action is just this omega and this omega. And then take the various states labeled by GH and GH inverse and take a sum over all possibilities. This is this equation. But remember our equation from before about what the cluster state was in terms of traces of A, G, and H? I wrote it here this way. And by applying to this equation repeatedly the fact that A's are a projective representation of Z2 cross Z2, I first get this expression, so G and H times a factor of omega. And then this GH and K became A of GHK, and there are now two factors of omega. Now this trace of AGHK is just telling me that GHK together has to be the identity, so K has to be GH inverse. And then I discover that in the end, I have exactly what I said would be a Hartle-Hawking type state for a topological field theory with this action. And so, in fact, these SPT ordered states can be prepared by these topological field theories, and the action of the topological field theory is just the cohomology. Okay. Any questions about this slide?
Oh, yeah, just a quick question. In the last step, the state goes from that needs two labels, G and H, to only one label?
There are actually three labels, G, H, and K.
Yeah, but in the last step, you need really only G and H, then everything else is different.
Oh, yeah. I should have said GH1, tensor GH2, tensor GH3. That's what this is meant to say.
Okay.
That's what we mean by a that's what we mean by a state prepared by a path integral. In fact, a state prepared by any path integral is always going to be, there's going to be a G assignment to every edge.
Okay, yeah, thanks.
Yeah, okay. So hopefully you can see that the cluster state, we rewrote it on a previous slide, but it actually is also this. And so notice that here's a situation where I have an action and a Hartle-Hawking path integral with that action prepares for me the state, but the action is given by a cohomology of something. In this case, the states are uniquely labeled by elements of the group, and then it's the cohomology of a group. But you can imagine that more broadly, if I have the action, I should be thinking of the action as being a term in an appropriately chosen cohomology, and then counting the action is like, well, okay, it really just relies on a choice of an element from a cohomology. But so putting these things together, you could say, we could say that complexity is like the action because Lenny Susskind told me so. And action, in this case at least, it's like a cocycle from an appropriate cohomology. So that's what's true in a cluster state. So maybe complexity is a choice of cocycle, or a choice of complexity measures like a cocycle in the cluster state. And if I want to map this story that I just told about SPT phases of matter about the cluster state to holography, then think about taking a spatial slice of a geometry and triangulating it. So dual to that triangulation is a bunch of edges, and think of these edges as being part of some tensor network. And now what I'm saying is that every one of these triangles is really defining for me some object in an appropriate cohomology class. And what object it is, well, from a tensor network point of view, I would just be choosing the tensor. But from a different point of view, like what I have to assign to this triangle is really decided by a certain type of cohomology. Okay, so so that's kind of the picture for why that our discussion so far with its cohomological conclusion is supposed to carry over, hopefully, to a discussion of complexity in holography. Now, you might say, why cohomology? Where am I, in fact, using the co-cycle condition. Remember, it's these co-cycles had to satisfy an equation, which was the co-cycle condition. So from the point of view of a triangulation, the co-cycle condition is the statement that what you get in terms of such states defined by path integrals is independent of triangulation. So what I want to tell you now is that we interpret, the correct interpretation is that this co-cycle condition, independence of triangulation, is in fact an independence of RG scheme that you choose to describe the bulk in holography. So let me tell you about this. So suppose that I have a state on 6 Hilbert spaces, a six body state, and it is defined by a, like I said, by some kind of, let's say, topological field theory whose action is given by the co-cycle evaluated on these triangles in the dual triangulation. But then suppose that I want to, so this is my state, okay? It's a state on these 6 Hilbert spaces labeled A, B, C, D, E, F. And I want to say that the green triangles are going to correspond to the how I prepare the state. They're related to the action that's necessary to prepare the state in the Hartle-Hawking formalism. It's also they should be related to the complexity of that state, because that's what I have to do to put together the state. Now, let me use the co-cycle condition to replace these 2 triangles with these 2 triangles. So I kind of blew up these triangles. They look bigger on the other picture, but they are supposed to be the same. So now, what interpretation does this have? Well, it looks like I have these Hilbert spaces A and B, these Hilbert spaces, and they first merge, and only after that, they merge as one into the definition of the state. So I would say that on the left-hand side, I have a state defined on 6 Hilbert spaces, but it's a 6-body state. But on the right-hand side, I have a 5-body state, which is labeled by A, B collectively, because these are inputs coming from A and from B that have merged together. And then I have C, D, E, and F. And so the difference between these 2 pictures is that on the left-hand side, I have a 6-body state. On the right-hand side, I have a 5-body state because 2 of my bodies have merged into 1. Now, what do we call such merging? We call it coarse graining. I have taken A and B, these 2 Hilbert spaces, and I have defined a collective state for the 2 of them, and that state can be part of a description of my global green state over here. So this picture can be thought of in, so the difference between these pictures is really a difference of cutoff. On the left-hand side, I have a state on a finer cutoff where I have 6 component Hilbert spaces. And on the right-hand side, I have a state with a coarser cutoff with 5 Hilbert spaces. And on the left-hand side, the state complexity of this finer state would consist of 6 triangles. On the right-hand side, the state complexity of the coarser state would only consist of these 5 triangles. What about this one? Well, this one is not not contributing to the complexity of the state anymore. It's the complexity of the coarse graining of Hilbert spaces A and B to a collective Hilbert space that lives here, but it's not part of the definition of the state. And so chipping out this single triangle is like coarse graining. So I would say that the pink triangle represents the complexity cost of doing an external coarse graining, whereas the green triangles are the actual state complexities here. And the fact that I can compare these 2 things relies on this equality, which I have boxed here. This equality is exactly the co-cycle condition from our previous slides. And so the co-cycle condition, the relevance of cohomology is that I should be able to do these manipulations and assign complexities independently of the RG scheme. Are there any questions about this? So this slide is meant to explain why the co-cycle condition translates into RG scheme independence of complexity computation. And that's what I would call a reason, like a principled way of approaching complexity. We should say, it doesn't matter how I do my RG scheme at intermediate stages, the complexity of a given state should be the same. Any questions about that? Okay, in view of time, I'm gonna keep going. So what we said so far, and the application, the picture of the cluster state, which I have drawn over here, this is the cluster state on 6 qubits, yes? It's very similar to a holographic geometry that I would get if my cutoff looked like this. I had an actual set of disjoint cutoff sized regions in the boundary, and I'm just asking, well, what's the collective state on the Hilbert spaces of these individual cutoff sized regions? I would get a picture like this, and that picture is identical to this picture. What's special about this picture on the left is that, or the thing that makes holography more complicated than SPT phases of matter, is that these triangles here are for Hilbert spaces which are non-overlapping. So this little cutoff sized entanglement wedge and this little cutoff sized entanglement wedge, they don't overlap. And so that's why I get this kind of star shape. And if I always wanted to only describe these kinds of star-shaped states in the bulk of AdS, then that problem would not be different from the SPT phases of matter at all. However, we typically don't want star-shaped cutoff surfaces like that, but smooth cutoff surfaces, yes? And so what's the complexity at a smooth cutoff like that? Well, a smooth cutoff like that, especially if you know my work from before, because I've been previously obsessing over many papers about describing such curves using tangent geodesics or tangent RT surfaces, can be described, in fact, by a collection of tangent RT surfaces, yes? But these tangent RT surfaces will have to be overlapping, yes? And so the non-overlapping case is not realistic for what we typically mean by a cutoff, but that one is directly similar to the cluster state. But the extra complication we have to do is that we have to account for these overlapping cutoff sized entanglement wedges. And so in the remaining, I don't know how many minutes I have, I'm going to just sketch for you a picture of what to do, how to, so far we concluded that cohomology is relevant to complexity. I'm going to sketch to you how that cohomology, or what you have to do to upgrade it so that your formalism is not just describing these types of cutoff shapes, but also these smooth cutoffs. And that's what I will do in the remainder of the talk. Any brief questions now? No, okay. So remember, cohomology tells me that if I have a triangulation, I can retriangulate and nothing changes, yes? And so I'm going to take this picture that we believe we already understand, even though it's not terribly realistic, and I'm going to retriangulate it this way, okay? So let's think about what happens here. Then we'll get to the realistic case. So what happens here? I have a state on some little cutoff sized Hilbert space A and B, and I'm mapping it to a collective state of a Hilbert space AB, which lives here on this RT surface. And then I'm taking that one and merging C and making another one, which is the state of ABC. And then I take D and I get row of ABCD and so on. So these individual triangles, at least when I triangulate them this way, they look like quantum channels that take cutoff sized entanglement wedges or density matrices and map them to coarser density matrices. The reason why I have selected these particular quantum circuits, which correspond is, first of all, they correspond nicely to a very well-ordered triangulation of this bulk picture. But the second reason is that they correspond to, for each one of them, I can see exactly what they're doing. Because I take something, row A, which has entanglement entropy SA, and row B, which has entanglement entropy SB, and then I'm mapping it to a row of AB, which has entanglement entropy AB. And I know from subadditivity that the sum of the input entropies minus the output entropy is non-negative. And I know it for each one of these things. So subadditivity tells me that whatever these regions, these triangular regions are doing in the bulk of AdS, they're always doing coarse graining because they're taking input states from which collectively have larger entropies, and they're mapping them to something that has smaller entropies. Okay, that's what subadditivity tells me about these triangles. Now, if I just, these triangles, the ones with subadditivity, or which represents subadditivity, are sufficient for describing these states, which are like the SPT state phases, SPT ordered phases of matter, or like our cluster state toy model. But the thing that we wanted to understand is this kind of cutoff. This kind of cutoff is never going to be collected from these types of triangles. Instead, it needs these types of triangles that don't go out to the boundary. And so the question is there a similar way of understanding a triangle which can triangulate a region that doesn't go out to the boundary at all, such as this one? And in the case of these ones, it was possible to think about the components of the state as being related to, as first of all, performing coarse graining. And I know that they perform coarse graining because of subadditivity, which is an entropic inequality. So a question you can ask is, maybe there is also some kind of inequality that's associated to this little triangle. And this inequality would also tell me about the amount of coarse graining that's happening over here inside this triangle in the bulk of AdS. And the answer is, yes, there is such an inequality. We call it the triangle inequality, that two sides of a triangle together are always larger than a single side of a triangle. And in fact, any entropic inequality that I can write down, if it's true, can always be understood as telling me about the amount of coarse graining that happens in a channel, and that channel has its own complexity. And the art of assigning a complexity number to such a channel is what we call, is an element of a cohomology, as we explained in the previous part of the talk. So the strategy for dealing with more realistic cutoffs that don't go out to the boundary is start with entropic inequalities. Think of these inequalities as signaling the presence of a quantum channel that is being done or performed by the bulk spacetime. It's a coarse graining type of quantum channel. And then the cohomology is going to take such a channel and assign a number to it, which tells me how hard it is to actually do this kind of coarse graining. So here's a brief example I just did the subadditivity example in detail. A plus B is greater than or equal to AB. This is subadditivity. And now A and B can be in one of two phases, the disconnected phase or in the connected phase. If they're in the disconnected phase, then AB is the same as A plus B. So the inequality is saturated. And that's a statement that nothing happens when I take row A and row B to row of AB. I'm just tensoring these two input states. So the complexity is 0. But if they are in the connected phase, then there is a region in between these RT surfaces that mark this inequality. And the region in between them is a non-trivial quantum channel, which deserves to have its own non-zero complexity. And assigning numbers to these types of channels is what the cohomology should really be doing. And here are two more examples of this, where I similarly rewrote two other inequalities. One is chunk subadditivity, and the other one is the cyclic inequality. I rewrote them in terms of, first of all, I pictured the kinds of circuits in the bulk that they would be doing. And I also told you which inequalities they correspond to. And I'm telling you that the proper way of thinking about them is from algebraic geometry, where every inequality defines a boundary chain. And because it's a boundary, it defines a higher dimensional chain, which is a quantum channel. And then mapping that to complexity costs is what the cohomology should be doing. And so I stop here. This is a summary and also a slide about what the next steps are, or how to go forward with this program of understanding a cohomology on quantum channels as defining complexity. Thank you very much.
So thanks, Bartek, for wonderful talk. I think there are a lot to digest actually. I will ask audience if they have questions, one or two questions. You should please go ahead and ask now. Otherwise, we'll have a discussion session after next talk actually, or after Omkar's talk. I think Bartek may stay around, and then if there are more questions you can ask there. But if you have some immediate question, you can ask now actually. Any questions? Okay, so I have a quick question actually. So when you say that given the channel, I think the one slide back. So when you say that channel, you use the cohomology to assign a real number, which means this omega means are you trying to sort of interpret the value of omega as the complexity corresponding to that channel?
Yeah. So if we were doing, if we were trying to apply complexity equals action proposal to SPT phases of matter, then we would be forced to do this.
I see.
Then we would be forced to do this. And so I'm saying, let's take it, let's basically take it seriously. But we just have to be careful about what kinds of things do I have to, where should this homology be defined on? So in the case of SPT phases of matter, they were fully characterized by a group. And so it was group cohomology there. But now we have these picture of a bulk. The bulk has some simplices or triangles. If those triangles go out to the boundary, like I was picturing here, then that's basically the same as the SPT phases of matter case. But when they don't go out to the boundary, such as here and such as here, yes, then I have to invent something a little newer. So my cohomology has to apply to something more complicated than just a triangle. And what should it correspond to? Well, in this case, in the case where I didn't have any complications, I recognized that the triangles on which my cohomology had to be defined really corresponded to circuits which are in one-to-one correspondence with applications of subadditivity. And I'm saying for these other types of things that I encounter in the more general case, they will also correspond to other entropic inequalities which are not subadditivity. And so evidently that's where the cohomology has to be defined.
I see, I see. So when you talk about cohomology, you can use these relations, this relation like this S goes to T type relation, you can generalize for other thing, right? Not just group cohomology. You can have in principle category also, means those fusion relation will still go through there will be more of them though.
Pretty much. So yeah, so I focused on a two-dimensional cohomology which applies to SPT phases in one dimension, because that one is the highest dimensional case that is easily readable by humans. But then in higher dimensions, so it's impossible to draw cartoon pictures for the higher dimensional cases, and especially since I will not actually be talking about simplices eventually, but about combinations of these inequalities, which don't have a very nice realization. But the cohomology should apply there.
I see.
So the second part of the talk was about defining the domain for this cohomology theory that needs to be defined to properly define complexity.
I see. Okay, so I don't want to postpone the next talk. I can ask you later more questions. So any other? So any other questions? Immediate questions from audience? Okay, so if not, for the moment we thank Bartek, and if you have any questions, we can postpone it to after Onkar's talk.
Very good.
Thanks, Bartek, and
thank you.
Thank you. So okay. So let Onkar, let me make you co-host, and then you can share.
Okay. Yeah. Sure.
Yeah, I made it.
Hi, Onkar.
Hi, Bartek. Good. Thank you. How are you?
Did you hear at least a little bit of my talk, or did you just get it?
No. I heard your talk.
Oh, thank you very much. Because I would like to talk about it with you at some point. So,
sure,
let's arrange a time when we could do it.
Sounds great. Yeah. It was a great talk. Thanks for the wonderful talk. Yeah.
But thanks so much. Thanks so much.
Okay. Let's see. Okay. Is that better? Can you see it?
Yes. I think so. Okay, so let's start with the next talk. Our next speaker is Onkar Parikar and from TIFR, and he will talk about quantum error correction in the black hole interior. We'll hand it over to Onkar.
Yeah, thank you so much to the organizers for inviting me to this wonderful workshop. I want to tell you about some work that's in progress with Vijay Balasubramanian, Arjun Kar, and Kathy Lee. And the title is Quantum Error Correction in the Black Hole Interior. So as you all perhaps know, recent progress on evaporating black holes has shown that after the page time, a portion of the black hole interior, namely the island, what is called the island, is encoded in the radiation. And so the setup for these calculations involves some quantum system, which I'll call B, that is dual to a black hole, coupled to another system, let's call it R, which is some sort of a bath which absorbs the radiation. Okay, so I'll try to stick to this convention throughout this talk. B will be the quantum system dual to the black hole, and R will be the bath which absorbs the black hole radiation. And the semi-classical picture that's dual to this quantum mechanical picture is, as I just described, a black hole that is coupled to a bath and is radiating into it. And after the page time, what happens is that there's a new quantum extremal surface, namely this black dot over here, which develops, and the sort of this blue region, the island region, moves over into the entanglement wedge of the bath. So this is sort of broadly the spirit of all these recent calculations. And quantum error correction has sort of played a very crucial role in AdS CFT. It really sort of provides the underlying framework for entanglement wedge reconstruction. In particular, at least in the standard picture, we think of the sort of bulk semi-classical degrees of freedom in the entanglement wedge of A, some boundary subregion, let's say capital A. We think of the semi-classical degrees of freedom in its entanglement wedge as being encoded in this boundary subregion A, and in particular, errors on A complement do not affect this encoded information. Now, similarly for islands, we expect that the semi-classical degrees of freedom in the island or in this portion of the black hole interior to be encoded in the radiation Hilbert space. But recently in this beautiful paper of Kim, Preskill, and Tang, they proposed that even going beyond the standard quantum error correction properties of AdS CFT, black holes have a sort of slightly different but robust quantum error correction property, where the information encoded in the island or in the black hole interior is in fact protected against low complexity errors on the radiation. Okay, and so in this talk we will try and explore this proposal of Kim, Preskill, and Tang about this quantum error correction in black holes, but from a somewhat more gravitational. So their arguments were more quantum information theoretic in spirit, and we will try to explore this proposal sort of from a slightly more gravitational perspective. Okay, so here's an outline of the talk. I'll begin with some preliminaries on quantum error correction, just sort of a review to catch us all up. Then I'll talk about the setup for our calculation of this quantum error correction in the island. Then I'll discuss the calculation in JT gravity, and I'll end with some final remarks. And I should say, please feel free to interrupt me with questions if you have any at any point. Okay, so let me start with a brief review of quantum error correction. So the general setup of quantum error correction is one where we have some code subspace, which we can think of as some small Hilbert space. And it's sort of encoded isometrically in a bigger Hilbert space. Let's call that H physical. So the code subspace will be called H subcode. There's a bigger Hilbert space, which I'll call H sub physical. And then there's an isometric embedding map between H code and H physical. And isometric just means that it preserves inner products. Now, the general theory of quantum error correction deals with sort of recovering this encoded information from the physical system after the action of potential errors on the physical system. Now, an error in this setup is modeled with or modeled by some quantum channel which acts on the physical system. Now, a quantum channel is just a fancy way of saying a linear map which takes density matrices on this bigger Hilbert space to other density matrices. Okay, so a quantum channel is a general map which will just map. It's a linear map which will map a density matrix to another density matrix. So we think about errors in this physical Hilbert space as some quantum channel, and then the question is, when can we recover the encoded information after the action of some quantum channel? Okay, just to set up some notation, it turns out to be true that any general quantum channel can always be represented in this form. So the action of this channel E on some density matrix rho is given by this particular expression, a sum over these sort of operators conjugating the density matrix rho. These operators E sub m's are called Krauss operators, and for the channel to be trace preserving, these operators satisfy a particular identity given here. Okay. Now, it's a generally useful fact that any quantum channel can always be expressed in terms of an ancillary environment, which is here denoted by which I'll always denote by this term environment. So we should distinguish this from the bath or the radiation system that we introduced before. So this environment or H sub environment will always be reserved for an ancillary environment system corresponding to the quantum channel E that we are acting with. Okay, and let's say that this environment has some basis of states which I'll denote by E sub m. Okay, so this quantum channel E can always be written as taking the density matrix rho, coupling it with some fiducial state on the environment, and then acting with some joint unitary on the system of rho as well as the environment. Okay, so this U is a joint unitary acting on this entire density matrix, and then you trace out the environment. So it's easy to show that if you define these E sub m's, these Krauss operators that I had discussed here, if you define these Krauss operators in terms of these unitaries U as such, then you reproduce you reproduce this expression down here. Okay, and this is just a useful fact. But in quantum error correction, we'll say that a channel E is correctable if for every density matrix rho supported on the code subspace, there exists a recovery channel R, which is also a quantum channel, such that R composed with E is the identity. Okay, and it's important that this density matrix in this definition is only supported on the code subspace. So it's only in that situation we say that this code is or error the error E is correctable on this code subspace H. Are there any questions so far? I hope I've not lost connection. Can you hear me?
No. Okay.
Yeah.
No,
okay.
no.
Great. Thank you. Yeah.
Keep going.
Sorry. Yeah. Great. I'll just proceed. Wonderful. So so one of the central theories of so far I've just given you the definition of what a correctable error is on a code subspace. But a general theory or a general result of the theory of quantum error correction is sort of a condition for when it's a very nice information theoretic condition for when an error channel E is correctable. Okay, So in order to tell you about this condition, I have to introduce a little bit more notation. So what we do is we introduce a reference system. So this reference system will be called H sub ref. And this reference system is basically isomorphic to the code subspace. So in particular, it has the same number of states as in the code subspace. So let's denote let's say the states in the code subspace by the index I. I is some label for the basis of states in the code subspace. Then the reference system will also have some, we can pick some basis for the reference system such that they're labeled by the same index I, okay? Because it's isomorphic to the code subspace. Now, given that, you define this particular state, psi prime, where note that, so this, the other thing I should just define here is these capital psis. These capital psis are basically just images in the physical Hilbert space of your code subspace. Okay, so remember that there was this isometric embedding of the code subspace into the physical Hilbert space. So these capital psi i's are just the images of these basis states in the code subspace. Great. So now we can define the state psi prime where at least without this unitary hue here, I and so I, the reference system is sort of roughly speaking maximally entangled with the physical system. But the only difference in psi prime is that there is this unitary U. U is this unitary corresponding to the error. Okay, I remember that in the previous slide, I told you that every error channel corresponds to a joint unitary acting on the system plus the ancillary environment. Okay, that's the same U. So this U here is the U corresponding to the error. Okay, so we take this sort of maximally entangled state of the reference and the code subspace, we couple it to the environment, and we act with this error unitary U. Okay, and you can also write the same state in terms of these Krauss operators, which I had described a slide ago. Okay, and the condition that the condition for correctability of these errors is the following. You look at the state psi prime and you compute the reduced density matrix on the reference and the environment. And if this reduced density matrix factorizes between the reference and the environment, then the error is correctable. Okay.
I have a question.
Yes, please.
So I was disconnected for a few minutes. So can you go back to the previous slide?
Yes, please. Yeah.
So you said this code is correctable when this recovery channel acts like this, but there should be some error margin that code could be recovered, right? Not only the fully recovered, something like this. So how does this works in this case?
Yeah. So what I'm describing here are exactly correctable errors. There are, as you rightly said, there are also approximately correctable errors where you don't require this exact equality, but you say that R of E of rho minus rho in the one norm is upper bounded by some small number. Okay, and that's the notion of an approximately correctable error.
In that case, you use this relative entropy definition to this. Okay.
Yeah. So in that case, what you can just to answer your question a little bit more, what this condition is saying is this factor. So whenever you have a factorization of the density matrix like this, it just means that there is no mutual information between these two systems, reference and environment. Now, in the exactly correctable case, what this condition is saying is that this mutual information should be exactly zero. But in the approximately correctable case, this mutual information will not be exactly zero. It will be some small number. And that small number, basically, you can show upper bounds the one norm between R of E of rho and rho.
Okay.
Okay, so in other words, this mutual information that one is talking about for the state psi prime is sort of a good quantity which naturally generalizes to even the approximately correctable case.
Okay.
Is that helpful? Okay, great.
Okay, thank you.
Any other questions?
Yes, sir.
Yes.
If we have an independent error, then how will we define? How will you define the joint unitary?
Could you repeat your question, please?
you have a time-dependent error, will the joint unitary remain the same, or will it? How will it change?
A time depend. Yes, so the joint. I have not said anything about sort of Hamiltonians, right? So in particular, your unitary could as well be like time evolution with some time dependent Hamiltonian if you want. So I'm not saying anything about what this unitary U is. It can be whatever you want. And as you rightly said, in general, it can be some time evolution with a time dependent Hamiltonian.
Thank you.
Sure. Okay. Right. So what I was saying is that this criterion of error correction can be nicely reformulated in terms of a mutual information. In particular, we define the state psi prime, and then in the state psi prime, we compute some mutual information and check whether it's 0 or not, or in particular, whether it's small or big. Okay. And this is sometimes called the decoupling principle. Now, there's also a simple bound which tells us how many errors a quantum code can tolerate. So I won't go through the full derivation of this bound, but let me just tell you what it looks like. So if T is the maximum number of qubits on which we can tolerate errors, then this bound, which is called the quantum singleton bound, states that 2 times T is less than log of the dimension of the physical Hilbert space minus log of the dimension of the code subspace. Okay, so this is what is called the quantum singleton bound. And then the only reason I'm introducing it here is because we'll come back to it in our gravity calculations later. Now, before moving to the black hole calculation, we need a small refinement of this formalism that I just reviewed. In particular, what we need is we need a refinement where the code subspace has a further structure to it. In particular, we are going to assume that it has a tensor product structure. Okay, so this code subspace before was just assumed not to have any additional structure. Now I'm saying that let's consider the case where this code subspace has some further tensor product structure H sub A, tensor H sub A prime. And for future reference, roughly you should think of this H sub A as being, let's say, the Hilbert space of effective field theory degrees of freedom in the black hole interior versus H sub A prime, which will then become the Hilbert space of effective field theory degrees of freedom in the black hole exterior. Okay. Now, with this additional structure, we can define a more general version of quantum error correction, which goes under the name of subsystem error correction. And in subsystem error correction, what you require is that you require errors, this error channel E, to only be correctable on, say, H sub A, or one of the factors of this code subspace. So in particular, we say that E is correctable on H sub A if there exists a recovery channel R for any input density matrix, so that the density matrix on the A factor is correctable. Okay. So this is a small refinement of the quantum error correction to the case where the code subspace has some additional tensor structure, and just very similar to the criterion, the mutual information criterion that we described before. There is a mutual information criterion for this refined case. The only difference is that because the code subspace now has this tensor product structure, we can talk about a basis of states I for H sub A and I prime for H sub A prime. And then corresponding to that, we'll introduce a reference system which also has a similar tensor product structure. Okay, so the reference system will now comprise of a reference corresponding to A and a reference corresponding to A prime. So here it is. And again, we consider this sort of maximally entangled state between the reference and the physical Hilbert space. We introduce this, so the action of the error is here modeled by introducing this environment and again acting with this joint unitary transformation. Okay. And in this case, the criterion is the following. So this error corresponding to this joint unitary U is correctable on H sub A if and only if the reduced density matrix, this time on both the reference systems and the environment, factorizes thusly. Okay, so this reduced density matrix should factorize between R sub A and the rest, R sub A prime and the environment. And in particular, again, you can reformulate this factorization condition in terms of a mutual information. It's just the statement that this particular mutual information has to be 0. Okay, so this is just a slight, again, as I said, this is a slight refinement of the mutual information criterion that we described a little bit ago. And so that's all I wanted to review as far as quantum error correction goes. The next thing for us will be to basically try and compute these mutual informations in a gravitational setup. But before that, are there any questions? Okay, so
I have a question.
Yeah,
So maybe you have already mentioned it, but in normally error correction, you only correct the eraser kind of error, right? But you have in information perspective, you have some phase flip and other kind of errors also. So how does this incorporate in this, or you are going to consider that kind of possibility also?
Yes, yes. So in our discussion, the error channel will be kept completely general. There are some small assumptions we have to make to be able to do the computation, which I'll describe a little bit later. But in principle, these errors are completely general. We don't particularly restrict to any specific. So you're right that in the usual AdS CFT context, one restricts one's attention to sort of erasure errors happening on the, let's say, the complement of some subregion.
Right.
But here, our errors are completely general. That's the novel thing about this, which is that the errors will act on the radiation system. They will be more or less general, and still we'll see that the black hole interior is robust against these errors.
Okay. Okay.
So that's the sort of new thing about these.
Yeah. Okay, and also one question is that could you also able to find the exact recovery channel? But because in finite dimensional Hilbert space, you can in principle write, and for example 2-qubit case, you can find a exact recovery channel. But in this case, if you have I mean you have a infinite dimensional systems or something, so is it possible to find this R channel exactly? Or
that's a great question. We haven't thought about it, and in particular our computations mostly focus on computing this mutual information, which then sort of tells us whether the error is recoverable or not. But that's a great question, and I think that maybe yeah, I think the answer should be yes. It should be possible to write down these recovery channels without much trouble, but we haven't done that, or I'm not going to describe that in this talk.
Oh, thank you.
But thank you. That's a great question. Yeah. Okay, so yeah. Okay, so the next thing I'll do is I'll describe the setup for computing this mutual information in the context of black holes and islands and so on. So what we'll do is we'll study this mutual information in a particular toy model for an evaporating black hole, which was constructed in this paper from 2019. So the toy model is the following. We consider a sort of entangled state between the black, remember again that B here is the quantum system dual to the black hole. R is this bath or the radiation system, which sort of absorbs the black hole radiation. And the toy model for this evaporating black hole is that it's an entangled state of this type between the black hole states and some basis of states in the radiation or in the bath. Now, I should describe what these black hole states are. Hopefully, these are already familiar, but let me describe them anyway. So the state psi sub alpha or psi alpha is a state of this quantum system B, which is dual or which has a dual semi-classical description in terms of a black hole. And then in addition, there is an end of the world brane deep inside the interior of the black hole. And alpha is a label for some intrinsic degree of freedom on that end of the world brane. Okay, so alpha will be taken to range over 1 to some number k, some integer k. And as I said, from the black hole perspective, it's just some intrinsic degree of freedom on the on the end of the world brane. And on the Barth side, again, note that we have the same alpha, but here on the Barth side, alpha is a label for a basis of states on the Barth. Okay, and this entangled state between the black hole and the radiation is sort of a toy model. You should think of it as a toy model for an evaporating black hole, where you sort of have this black hole entangled with a bunch of radiation in the Barth. Okay. Now this parameter k over which alpha ranges plays the role of the evaporation time. So in particular, when k is much smaller than e to the s, then the quantum extremal surface relevant. So you could ask for the entropy of this Barth system or the radiation system, and it turns out that when k is much smaller than e to the s, then the QES relevant for this entropy is the empty surface. But when k is much greater than e to the s, then the quantum extremal surface relevant for the entropy of the Barth happens to be this bifurcation point in the black hole geometry, and then this blue region, namely the island, is part of the entanglement wedge of the Barth. Okay, so in this sense, k plays roughly the role of time in a real evaporating black hole. And just one last thing is that the mechanism for this transition of the quantum extremal surface in a replica trick calculation is given by the replica wormhole. So far, I'm just sort of reviewing some basics of this toy model from this paper, but hopefully much of this is already familiar. So now our goal will be to study this subsystem quantum error correction in this toy model. So let me just quickly run through the setup of quantum error correction, but now described in this new language of this black hole coupled with the Barth. So in this language, what we called H physical before, the physical Hilbert space or the big Hilbert space, will be the entire Hilbert space of this quantum mechanical system dual to the black hole H sub B and the Hilbert space of the Barth H sub R. Okay, and what we called the code subspace before is going to be the Hilbert space of semi-classical degrees of freedom in the black hole geometry, but we can imagine that it sort of factorizes between the interior degrees of freedom and the exterior degrees of freedom of the black hole. And then, of course, the point of viewing this as a quantum error correcting code is that the Hilbert space of the semi-classical degrees of freedom are embedded or form a subspace inside this bigger Hilbert space, namely the Hilbert space of the full quantum mechanical system dual to the black hole times the Barth. Okay. So corresponding to some set of basis states in this code subspace, we could imagine sort of the image of these basis states inside the big Hilbert space or inside the physical Hilbert space. And in order to denote that fact, that this particular state is the image of some state in the code subspace, I'll just put these labels I and I prime, denoting these basis states in the code subspace on this physical Hilbert space capital psi. Okay, and the way to think about this is that this same labels I and I prime are now on the black hole state. So what this black hole state is that it's a state of the this quantum mechanical system, which is dual to a black hole, Now, this black hole, as before, has an end of the world brane in its internal state alpha. But in addition to that, it also has sort of some excitations of bulk quantum fields in the state I prime, living on let's say some Cauchy surface in the bulk. Okay, where I labels the state of these bulk quantum fields in the interior of the black hole, and I prime labels the state on the exterior of the black hole. So this particular equation here gives you, it sort of tells us what the encoding map is. Okay, it tells you how to take a state in the effective field, like the semi-classical Hilbert space of the bulk, and map it to a state in the full Hilbert space, or the physical Hilbert space of this quantum mechanical system B and the Barth system R. Okay, so you should think of this as my encoding map for the error correcting code. Now, you could ask me, well, how do I construct such states that I just described? Well, you could construct them from a Euclidean path integral in the dual quantum mechanical system. This Euclidean path integral happens over sort of an interval of time with an endpoint. So this endpoint here is just, let's say, Euclidean time equals 0, where the state is defined. But there's another endpoint where you specify some boundary condition. And this boundary condition is essentially what is isomorphic to this label alpha. So depending on what boundary condition you put at this other end of this time interval, the corresponding bulk picture is that the end of the world brane will have a corresponding sort of internal state alpha. So we could think of the boundary conditions here as being isomorphic to the intrinsic state of the end of the world brane. And in addition to that, this Euclidean path integral could also have some sources turned on. So this cross here denotes some sources which are being turned on in the Euclidean path integral. And those you could think of as creating this bulk state I prime on the bulk Cauchy slice. Okay, the state in the code subspace, if you will. Now, there is a small caveat that I should explain. For a sufficiently smooth source that you turn on in the Euclidean path integral, the state of matter fields in the bulk will not be a product state in general. For our formalism, we kind of would prefer to have product states of this type, product states between the interior and the exterior. But we could sort of avoid the issue of a large back reaction at the bifurcation point by just restricting ourselves to a small code subspace, just consisting of a few low energy excitations far from the horizon, and then the rest of the modes being in their Hartle-Hawking state. So in that case, you could very well consider a code subspace of this type, except that if you let this be a product state, a complete product state, then that could have a large back reaction. But when we have a sufficiently small code subspace with only a few low energy excitations far from the horizon, then such code subspace states are well defined, and you could imagine constructing them as superpositions, perhaps, of these sort of Euclidean path integral states. Okay, so that's sort of a formal description of how you might think of constructing states of the type we need from a Euclidean path integral in the boundary quantum mechanics system. But nevertheless, we can go ahead and try to use gravity to do our calculations. That will be our main motivation. Now, as I described before, our main motivation or main question that we want to go after is to ask sort of which errors acting on the Barth-Hilbert space can we correct on the interior subsystem. Okay, so because we want to formulate this question in terms of the interior of the black hole, this is sort of a question in subsystem quantum error correction. But note that this, I hope that it's clear that this is slightly different from the quantum error correction setup that one usually considers in AdS CFT. In particular, this setup is the one that was recently proposed in this nice paper. And what we'll do then is we'll use this framework of subsystem quantum error correction. We'll model our error with some Krauss operators E sub m. These Krauss operators, in our case, will only act on the bath system, the radiation system, if you like. And so if you recall, the way these error operators are modeled is that we introduce this ancillary environment system, which is denoted by ENV, environment. So here in this figure, you can see it in purple. And then we act on the bath and the environment system with this joint unitary transformation U. Okay, the role of this environment and this joint unitary transformation U is that it implements the action of the error channel on the bath or on the radiation. Okay, so this is our setup, and furthermore, we have to remember we have to compute this mutual information, which will tell us when this error is correctable. So in order to compute that mutual information, you'll remember that we need to introduce these additional reference systems, R sub I and R sub E, and then define the state psi prime, which is sort of maximally entangled between the reference and the physical Hilbert space. And then we have these joint unitaries U corresponding to the error channel. So this is the full picture of the setup. We have some semi-classical qubits, let's say, or some semi-classical degrees of freedom in the interior of the black hole and the exterior of the black hole. These are entangled with these reference systems, R sub I and R sub E. There is a bath which the black hole is radiating into, and then there is this error channel which is acting on the bath by introducing this environment and doing this joint unitary transformation U. So I'm sorry if this picture is sort of elaborate and involves a lot of different factors, but the sort of nice thing about this setup is that at the end of the day, once you have this full state defined, then the task is to basically compute this information theoretic quantity, namely this mutual information, which is just some difference of entanglement entropies. And so the question of whether this error is correctable or not boils down to checking whether this mutual information is 0 or small or not. Okay, and in fact, for gravity computations, it turns out to be more convenient to calculate the Renyi version of this. So instead of computing the mutual information directly, we instead compute the Renyi mutual information and then take the limit n going to 1 from above. Okay, that's a calculation that we can do completely in gravity. And so that's what we'll turn to next. But before that, are there any questions? Okay, I hope I haven't lost connection or anything.
No.
Okay, great, wonderful, wonderful. Thank you for that check. Great. So the next, in the next remaining few minutes, I'll describe how to compute these Renyi mutual informations in terms of a gravity calculation, and in particular, as you probably have imagined by now, we'll use JT gravity to do these computations. So let's start, for example, with this particular mutual information, the Renyi mutual information. Note that we have the difference of 3 terms here, 3 different Renyi mutual informations. So let's, for example, consider one of them, where we consider the mutual information, the Renyi entanglement entropy of this reference system union with the environment. Now, these equations are not super important, but let me just quickly describe what they're saying. You compute the reduced density matrix on this factors, and you take the nth power, and you take the trace, and so on. But the main thing that you will notice in this equation is that there are 2 types of terms. There are these terms involving overlaps of black hole states, or the quantum mechanical states dual to the black hole. And then there are all these blue terms. These blue terms are essentially encoding information about the errors. Okay, all of the stuff about all of the information about what quantum error is or what the error channel is. All of that information is sort of packaged inside these blue terms. And then there are these products of these black terms, which are just the black hole overlaps, black hole state overlaps. Okay. So what one can do is one can basically combine or repackage all of these blue terms into a tensor. That tensor I will call little f. Okay. And it's most convenient actually to visualize that tensor as in terms of a tensor network. So if you stare at it long enough, then you'll see that this particular object, which sort of includes inside it all of the information about the errors, takes the form of a tensor network where these blobs, these gray blocks here, are basically these joint unitary transformations corresponding to the error channel. Okay. And in addition to that, as I said, there are these overlaps corresponding to black hole states. Those you can see on the right-hand side picture are denoted with these black lines. And so the full answer involves some products and sums between this tensor network, which is now glued on to these black lines, and then you perform various sums. Okay, so that's the sort of schematic structure of this particular Renyi entropy. Now, the key point is that all of the information about the errors is encoded only inside this index structure F, and everything else, these overlaps of black hole states, are just some things which we can use JT gravity to compute. Okay, so that is going to be our strategy. We are going to use JT gravity to compute these overlaps of black hole states, and then plug in the answer into this expression, and then we can think about doing these rest of these sums with this index structure F. Okay, so that's what we'll do. But before that, I should mention an important assumption that goes into this calculation. The assumption is that this F tensor, this F tensor, which, as I said, includes all of the information about the errors, the assumption is that this F tensor contains no additional black hole microstate overlaps inside it. You see, if it did, then it could in principle source additional asymptotic boundaries. Okay, and that would change the calculation. That's not what we are doing. We are assuming that this F tensor is just some given thing. It depends on the error, but it doesn't depend, or it doesn't have inside it any other black hole microstate overlaps, which could introduce additional asymptotic boundaries. Now, a clear counterexample to this is when the error channel uses the PETS operator in the PETS operator in the bath corresponding to some interior, an operator in the black hole interior. Okay, this is a clear counterexample because this PETS operator or the PETS map explicitly uses the black hole microstate overlaps for this reconstruction. And so then in that case, the error channel would introduce additional asymptotic boundaries. But such channels are sort of very finely tuned because they need prior access to the details of black hole microstate overlaps. And furthermore, we expect such channels of this type to be exponentially complex. So at least in the rest of this calculation, I'm going to ignore channels like that. And we will assume that this channel, the error channel, has no prior access to black hole microstate details, and sort of more pedestrianly, this F tensor or the sort of error channel will be assumed to not introduce any additional asymptotic boundaries. Okay, so with this assumption stated, we can go ahead and do our gravity computation. As I said, this is roughly the picture that we get. And what we do now is we fill in these black hole overlaps. The black hole overlaps in this equation, these overlaps here are basically these black lines. So I've shown 3 overlaps here, so there are 3 black lines. And the task now is to fill them in with various different bulk JT gravity geometries. So in particular, the simplest one you could consider is the fully disconnected geometry, where all of these black lines are just filled in by their individual black holes, which end on end of the world branes. These red lines here, the solid red lines, are end of the world branes. And there are no connections between them. And then in this case, you can sort of go ahead and evaluate what this expression or what this particular Renyi entropy gives you. And I'll spare you the details, but what you find is you find an expression like this, where d sub I is the dimension of the interior code subspace or interior factor of the code subspace. D sub E is the dimension of the exterior factor of the code subspace. And then from the F tensor, you get this particular expression. So note that all of the information about the error channel goes inside this factor here. Okay, what this factor here is that you take a maximally entangled state on the bath and you couple it to this environment corresponding to the error channel, and then you do this joint unitary transformation and you trace out the bath. Okay, so in other words, this trace sigma environment is the density matrix you would get on the environment if you acted this error channel on a maximally mixed state of the radiation. Okay, so that's where all of the information about the error channel is going, and then these other factors just depend on the dimensions of the code subspaces. Now, similarly, you can also compute the other 3. There are in total, we have to compute 3 Renyi mutual informations. You'll remember Renyi entanglement entropies. You'll remember, and so just like the way I described above, you can calculate all 3 of them, and this is what you get. And when you go ahead and calculate the Renyi mutual information this time, coming from the disconnected geometry, you find 0. Okay, so in particular, what this means is that when the disconnected geometry is dominating your calculation, the Renyi mutual information is 0, and the quantum error is correctable. The error channel E that is acting on the bath is correctable. Now, of course, more precisely, what we should say is that the mutual information is exponentially small or suppressed in this extremal entropy of the black hole, because of course there are going to be subleading corrections coming from connected geometries, or at least partially connected geometries and so on. Great, so that was the fully disconnected answer. We can also compute the fully connected answer. This is the analog of the replica wormhole, where you'll remember that in this fully disconnected case, these end of the world branes just capped off individually and there were no connections between the asymptotic boundaries. But the fully connected one is where they're all sort of connected in order to have like a fully connected geometry filling in these asymptotic boundary conditions. This is exactly the analog of the replica wormhole. And in this case as well, you can go ahead and compute these Renyi mutual informations, not in complete generality, not for arbitrary n, but at least in the limit that n goes to 1 from above. And what you find in this case is similar answers, but there are some differences. In particular, the factor coming from the error channel is now slightly different. What in this case, the factor coming from the error channel is basically the density matrix you would get on the bath when you acted with this error channel on a maximally mixed state. Remember that in the disconnected case, what this factor was the trace of sigma environment to the n, which is the density matrix you would get on the environment when you acted with this error channel on a maximally mixed state. But anyway, the details are not super important. The main punchline is that for the fully connected, sorry, this is a typo. This should say fully connected geometry. For the fully connected geometry, what happens is that this Renyi mutual info, just the mutual information is finite and non-zero. In fact, you get 2 times log of the dimension of the interior Hilbert space. So the punchline is when the fully disconnected geometry dominates, the mutual information is 0. When the fully connected geometry dominates, the mutual information is non-zero, and you get 2 times log of the interior dimension. And you can also ask, when does this exchange of dominance happen? There's a simple criterion in terms of the sigma R and sigma environment that I defined, which tells you when this exchange of dominance happens. In fact, the left-hand side of this equation is entirely a function of this error channel. It's what's called the coherent information of this channel. And so what this criterion says is that when the coherent information is much greater than minus the black hole entropy, roughly speaking, then the error is correctable. But when the coherent information goes below this number, then the error is non-correctable. Now, the coherent information of a channel is sort of a measure of how noisy it is. The more negative this number, the more noisy it is. And so this is saying that as long as the error channel does not have prior access to microstate details, and provided that it is not too noisy, where by not too noisy, we mean this particular inequality, then the corresponding error channel is correctable. Or in other words, the black hole interior is protected. Okay, and let's see, I have about 3 to 4 minutes, I think.
Yeah, sure.
Yeah. So in gravity terms, this particular violation of this particular inequality basically means that this black hole interior moves into the entanglement wedge of the environment, where the environment is the environment corresponding to the error channel. Okay, not the original bath. So that's what this inequality is saying. So let me just skip over that and tell you so in what I described so far, we just computed the fully connected geometry and the fully disconnected geometry. But you can in fact also resum all the sort of planar geometries in some special cases. So if you restrict attention to a specific error channel, namely it's sort of an erasure error channel, where you're basically erasing, say, T qubits from the bath or from the radiation, then in that case, you can actually go ahead and resum all of the planar geometries using Schwinger-Dyson techniques, and you get a plot for the Renyi mutual informations, which looks like this. It's 0 until you erase sufficiently many qubits, and then the Renyi mutual information jumps to 2 times log of di. And if you one could compare this with the quantum singleton bound, and it turns out that it doesn't do that badly. It sort of just falls short of the quantum singleton bound by an order 1 number. Okay, so in some sense, gravity comes close to saturating the quantum singleton bound, but misses by an order 1 amount. So let me conclude with some final remarks. We know that in the usual AdS CFT context, the encoding of the entanglement wedge of some subregion inside this boundary subregion is generally only protected from errors acting on a complement. This is the standard story of error correction. But in the black hole case, well, of course, this also applies to the black hole case. So whatever calculations we did here, you can also use them, or similar calculations rather, to check that the entanglement wedge of the black hole is always protected from errors on the bath. But in addition, the black hole interior also seems to have this slightly different, but a robust error correction from errors which are acting on the bath itself. And at least in our calculations, what we found was that as long as this error channel does not have prior access to black hole microstate details, and provided that it is not very noisy in the sense of this coherent information bound that I described, then such error channels, then the black hole interior is also protected against the action of such channels on the bath. And we expect that this form of error correction, this slightly different but robust form of error correction, should also work more generally for entanglement wedges in regions which are sort of behind non-minimal QESs, or what are called sort of these Python's lunch regions. Of course, the black hole interior is one such case because it lies behind the empty surface. But more generally, we expect that this robust version of error correction should also hold true in more general Python's lunch scenarios. And maybe I can end with a speculation that this sort of new type of error correction stems basically from the complexity of the encoding map. With that, I'll end, and thank you for your attention.
So thanks, Omkar, for that wonderful talk. And now the floor is open for questions. So anyone in the audience have any questions, please go ahead.
Can I ask a question?
Sure, go ahead.
Yeah. So in this original PSSY, the West Coast paper, there's a consider entanglement wedge reconstruction, in particular using the PETS map, as you have mentioned.
Right.
And then there you have sort of, in the back of all this, you have also error correction kind of picture, but where, of course, there is just a erasure error, where you raise the black hole system, you keep the radiation system, you try to reconstruct operators on your radiation system.
Yes.
But now in your setting, you're saying the error acts on the radiation system. So can you comment on the difference of the setting?
Yes, it's exactly what you just said. In the usual setup, what one does is one basically, so if I recast that in the present situation, it's exactly what you said. You would basically think of this code subspace state being embedded inside the full black hole times bath system, and then you would erase the bath system, and then you would try to construct a recovery map which recovers from that error. You think of erasing the black hole as sort of an error, and then you construct a recovery map, namely the PETS map, which reconstructs from this error. And if you then use the adjoint of that map, then that is essentially the PETS operator that was described by PSSY.
Yes.
Yes, but the main difference here is that we are not, so exactly as you said, the error in our case is acting on the radiation. Okay. And the black hole interior is in the entanglement wedge of the radiation. But nevertheless, the black hole, the degrees of freedom in the black hole interior are still somehow robust under the action of this error. Now, one other difference is that in principle, right. So in principle, you could have imagined a slightly more general error, which acts not only on the bath, but also on the black hole. But that's something that is not being done. So in this case, the error only acts on the bath, and so somehow the black hole system, which is sort of error-free in this case, is in a sense acting in a way to sort of help with this error correction. So it's really this black hole which is error-free, which is sitting around, and so as long as that black hole is macroscopic, then the black hole interior is robust against such errors. Okay, yeah. So it's exactly what you said. The differences are exactly what you pointed out. Yeah.
Okay. Yeah. Okay. Yeah. Thank you. Yeah. Thank you.
Sure.
Any more questions? And if you have any questions for the previous speakers, you can also ask. Actually, we have like
I have two questions actually.
Go ahead.
So first question is that can you go back to the previous slides? I mean, where you have plotted the Renai mutual information?
Sure. This one?
Yeah. So
okay.
So is it something that you're telling that Renai mutual information can be a distinguishable probe for the page time in that sense? Because it jumps from.
So it's not a probe for the page time. These calculations always happen after page time, because you see, it's only after the page time that the black hole interior is in the entanglement wedge of the bath. So before that, before page time, it's kind of obvious that any error on the bath is correctable, because the interior is just not in the entanglement wedge of the bath. So whatever errors happen on the bath will be sort of trivially be correctable, right? So this calculation becomes interesting and non-trivial only after page time. Now, what is this t? So I suppose the real question is, what is this? What is the x-axis? You see, the x-axis is, so what we are doing in this particular figure is we are choosing a particular error channel. This particular error channel acting on the bath, what it does is it basically erases qubits one at a time. Okay. So you imagine erasing 1 qubit, 2 qubit, 3 qubits, 4 qubits, and so on. And that parameter, how many qubits of the bath have you erased, is this parameter t. Okay. So what this figure is saying is that if you erase a small number of qubits, there is no mutual information, and so the error is correctable. But once the number of qubits becomes sufficiently large, then the mutual information jumps to its to 2 times log of t, and then the error is not correctable anymore. And if you look, so you probably won't be able to see it from this figure because I haven't told you all the numbers involved. But if you look sufficiently closely, then you see that where this jump happens is kind of an order 1 number close to the singleton bound, the quantum singleton bound. So this encoding is sort of close to saturating the quantum singleton bound, but not exactly. It fails sort of an order 1 number before that. But importantly, not like an order 1 over G Newton number. It fails like an order 1 number before the singleton.
Okay. So another question is that if we think in the field theory side, so these models should be some equivalent, some large and some models in the field theory side, right? So there are some proposals by Milekin that shows that for at least for harmonic system, you have this Gator collection is exact for large infinite n. It's not exact for any finite system. So if you consider something like SOIK or something is dual to this thing, so do you also expect this? It is possible to argue this something thing, or is it?
That's a great question. So let me answer it in 2 parts. First of all, the mutual information is only 0 for the strictly disconnected geometry in our calculation. So even if you include like partially connected geometries, which you must, then you will get this mutual information has like e to the minus s naught corrections. So indeed, the mutual information is not strictly 0. It's e to the minus s suppressed. And that, as we discussed a little bit ago, so e to the minus s gives some sort of an upper bound on how correctable this error is in the approximate error correction setting. Now, coming to your question about Milekin's paper, that's a great question. I haven't really thought deeply about, so if I remember correctly, his paper tries to think about quantum error correction in some sort of an SYK model type setup, right?
It's a matrix model.
Matrix model type setup. Yeah, I think that's a great question. I haven't really, well, okay, there are some differences because in his setup, he thinks of these errors as taking you away from the singlet sector of the matrix. But I agree with you that kind of, you could think of this code subspace as being like the singlet sector and stuff like that. So it sounds very similar, but I haven't really thought very deeply about making a connection there. It sounds like a great question to me.
Okay. Okay, thank you for your nice talk.
Sure. Thank you for your questions.
Any more questions? Questions from previous talks also? you can ask actually if you have any questions. You have like 10 minutes of buffer or so. You can ask to Bartek and Onkar both of them. Okay. Okay. So I think I will say formally thank you both the speaker for wonderful talk, and thank you very much. So we'll start roughly in 7-8 minutes. So I wanted to ask one thing to Bartek actually that time probably. So so what will be the ingredient for this simplicities in the when you talk the gravity point of view? You need to put this simplicities inside, right? I mean, what is the SPT state language will transfer into when you talk in, for the holographic side? I mean, you still had to talk about triangulation, etc., right? Inside the bath means you need to think about some model of tensor or something like that.
I think yeah. So because it's very much work in progress, I'm not really sure if what I'm about to say is correct, but let me try anyway. So so if we so ordinarily when we talk about geometry, it's enough to just do a triangulation of the geometry, and then if you want to take, let's say, the volume of some space, then you can triangulate it, and if you know what the volumes are of all the simplices, then you add them up and you have the geometry and you're done. I think in this case at hand, we cannot just reduce the thing to simplices. So just taking a geometry and let's triangulate it is not good enough. The reason why is that we would have to know how to interpret a simplex sort of in a CFT language. And I believe that we don't have it, and we will not have a direct interpretation of an arbitrary, of a higher dimensional simplex. Like let's say that we are in AdS 7, okay, which also shows up in the AdS CFT correspondence. I don't think that we will have an interpretation of 6-dimensional simplices on space or 7-dimensional simplices on space-time. And let me tell you why. So when we're in 2 spatial dimensions in the bulk, so in AdS CFT-II, then the kind of simplex we need is a triangle. And for a triangle, we can rewrite it as okay, so I have 3 sides of a triangle, and each of them corresponds to a piece of a Ryuta-Kayanagi surface. That's why, because the triangle has straight lines, yes? So, so it's a Ryuta-Kayanagi surface that bounds it from every side. Now, the idea is that, I'm gonna pull out my slides again, is that I would take, oh, I'm not sharing screen yet. Can you see my screen now?
Yes, you're taking laptop.
Yeah. So if I take a triangle, then I want to extend its sides so that it becomes bunches of Ryuta-Kayanagi surfaces. Now these Hilbert, these regions that were hit by these Ryuta-Kayanagi surfaces, I can call them A, B, C, D. And then I know what things I'm talking about from the CFT point of view. So, but this triangle is not doing any simple job like taking a state on A and taking a state on B and mapping it to collective state AB. These triangles were, these ones were doing this kind of simple job. I had one Hilbert space, another one, and I mapped it to a collective one. But that's because its sides went out to the boundary everywhere. But when the sides don't go out to the boundary, what I have is I have some subsystems and some other subsystems which are overlapping. being mapped to yet another system, which is also overlapping. And so we need to understand that. And what I'm proposing is that there is a very special set of chains, which we do understand, I think, which are the ones that are related to holographic inequalities. So these ones we understand because this is related to an inequality A plus B greater than or equal to AB. It's related to subadditivity. So in a similar fashion, I want to say that just like this triangle is sort of related to subadditivity, and in particular, it's related to some quantum channel, which takes the state rho A and rho B and maps it to the state rho AB. It's taking these two entanglement wedges and it's making a bigger entanglement wedge out of them that contains them. In a similar fashion, I'm proposing, let's take all known inequalities and map them to regions. So here is an example of what strong subadditivity would become. And so for these simplices in 2 and in higher dimensions, if this proposal is correct at the level of inequalities, then I would ask, can I ever write a triangle in terms of circuits that correspond to these inequalities that I already understand? And in 2 dimensions, the answer is yes, I can rewrite this triangle in terms of a very complicated combination of strong subadditivities. This was explained in the first paper that Lampros-Lampro ever wrote together with me. And we explained how to write down the triangle inequality as a linear combination of strong subadditivities.
Oh, I see.
But it's very special to 2 dimensions. So when I go to higher dimensions, I would want to ask, can I take an arbitrary higher dimensional simplex and rewrite that simplex in a similar fashion in terms of inequalities? And I don't think that there is a universal way of doing this. I think that I will need to use different inequalities for simplices in different, I mean, actually, I haven't thought about it enough. Maybe it's possible, maybe not. But anyway, that would be my approach. My approach would be to take simplices that I will encounter in space or in space-time and rewrite them in terms of inequalities of some kind.
I see. So just to rephrase it, that in 2 dimension, although this triangle, the one you showed, the length, this edge and this one sides are not actually going up to the boundary, but you can still rewrite it in terms of this subadditivity, various combinations of those inequality. Various
Yeah, and it's kind of non-intuitive. I mean, it's not trivial to rewrite this in terms of strong subadditivities, but it's possible, and it's explained in that paper that Lampros and I wrote 7 years ago.
I see. Now it's like, I think, got the message actually.
So that one was kind of so the triangle in 2 dimensions was a tractable problem. Can we do a similar thing for simplices in higher dimensions? Maybe, but maybe not. And so if not, then that would say that like there isn't a universal way of talking about a simplex. There is just, if you give me a simplex, sometimes it will be part of some combination of these basic things, sometimes not. What are the basic things? The ones that correspond to strong to entropic inequalities.
I see.
So for example, I'll just add one more sentence. I'm sorry, I don't want to monopolize the time, but I'll just add one more thing, which is
sure.
When you there is a discussion in various papers, most notably, I think, in the paper by Matt Hedrick and collaborators about the bit threads interpretation of monogamy, where they explain that monogamy is basically related to the perfect tensor entanglement. And that perfect tensor entanglement has, roughly speaking, the topology of a tetrahedron. But in fact, it's not actually just filling a tetrahedron. When you draw what monogamy corresponds to in terms of extremal surfaces, those extremal surfaces have the symmetries of a tetrahedron, but they're not actually filling the interior of a tetrahedron. They're doing something more complicated. And so that's the kind of example where it looks like we might have a simplex in like a 3-dimensional simplex, but we have something related to it, but we don't identically have a simplex.
Yeah, actually, I was going to comment on that. So if we somehow think about filling the bulk in terms of those kind of tensor network stuff, probably you can use your technology again, right? Means, I mean,
yeah. And actually, can I add one more comment?
Yes, sure.
I want to emphasize why these inequalities are useful for thinking about the various types of coarse graining and contrast it with what tensor networks do. So in tensor networks, when you have a tensor, it just has some legs. Those legs are not coming from like overlapping Hilbert spaces. You just take one tensor in isolation, every leg corresponds to a separate Hilbert space. So I believe that the picture of bulk geometries as tensor networks is kind of misleading in that way, because when we draw it, we say, oh, there are these separate Hilbert spaces. But when you give me a Hilbert space of this region here, and I ask you, can you identify in this Hilbert space precisely the degrees of freedom that correspond to this piece of an area? You would ask me, like, how would I do that? And so I say, maybe we shouldn't be trying to separate pieces of, like, partition RT surfaces into areas. Instead, we should just be content with taking more general kinds of quantum channels that map combinations of partially overlapping density matrices to one another. But when we do this, we're not doing tensor networks anymore. We're doing some more, some generalization of it that takes partially overlapping inputs to partially overlapping outputs.
I see. I see.
Actually, Bartek, can you say more about this quantum channel? Maybe in a simplified setting, like can you actually construct it in terms of some PETS map or something like this? Or?
Oh, I have no idea how to construct it. I really just, in some sense, the last 5 slides of my talk were just one observation, which is that when you make if you give me an inequality and represent it as a linear combination of RT surfaces with coefficients, then those coefficients, understood as a chain in the algebraic topological sense, always form a boundary of a higher dimensional chain. That's all I meant. And so you would ask, what's the interpretation of that higher dimensional chain, whose boundary the entropy inequality is? And I would say it's probably some kind of circuit. Now, why would I say that? Because let's think about a single thing like this, yes? Just a single RT surface. Now, by now we have internalized it so much that we don't think about the homology condition that defines the RT surface anymore. But what is the homology condition telling you? That this RT surface has to be uniformly deformable to the boundary region. So I would interpret this as saying that on the boundary, there is a rho density matrix that lives there. That's the CFT density matrix. But then there is a circuit that sort of compresses it. And then the RT surface lives a compressed version of the same density matrix. Because that's why we would add areas with unit measure. If you see what I mean, like there's a constant density of information per unit area. So we compressed it. So if you believe me that an entanglement wedge is performing a compression from the boundary to the RT surface, then if I take regions of this type or of this type, then what I'm doing is just taking like subsections of these types of compression maps and combining them in various ways. And I think that those combinations can be interpreted as as chains and geometrically in the sense of, and as algebraic topologists would do it.
I see. Thanks. Probably we have to move to the next talk. So hand it over to Shugo to do that. But thanks, Bartek, again very much.
Thanks so much for the questions and for engaging with the talk. Thanks so much.
Thanks, Onkar and Bartek.
Yeah, thank you so much for your invitation, for the questions. Yeah.
Okay, so we move on to the next session where the speakers Ayan Patra and Aranya Bhattacharya. Ayan, are you around?
Yes.
You are the co-host now, right?
No.
Okay.
Yeah.
Okay. Can you go ahead and present?
Yeah.
Yes, it's good. Can you move your cursor around a bit?
Yeah.
Okay, it's great to have Ryan Kumar Patra from Saha Institute, Kolkata, and he'll be talking about page curves and path deformation. Please go ahead.
Yeah. First, I want to thank the organizer for giving me a chance to speak about my work in this wonderful workshop. So the title of my talk is Page Curves and Path Deformation. And this work was done in collaboration with Elena Caceres, Arnab Kundu, and Sanjit Sasi. So the outline of my talk is the following. So first I will give a brief introduction about information loss paradox. Then I'll say about this W holographic model and page curve. After that, I move to describe about the setup and the page curves at the probe of RG flows. And finally, I will conclude and tell about future directions. So we can make black hole from collapse of a PO state. After the formation, it can radiate away by Hawking radiation. So this is an example where PO state goes into mixed state, and it is known as Hawking information loss paradox. We can quantitatively formulate this problem by calculating the entanglement entropy of the radiation, which is nothing but the von Neumann entropy. If we plot the entropy of the outgoing radiation as a function of time, we find that the naive computation gives us this growing behavior of the entropy of the outgoing radiation. But from the unitary, we expect that it should follow a curve like this, growing initially and then decline and become zero. This is the thermodynamic entropy of the black hole, which decreases as the black hole evaporates. The time at which the entanglement entropy of the Hawking radiation equals the thermodynamic entropy of the black hole is known as the page time, which is this point. And the recent work suggests that we can recover quantum information semi-classically in simple toy models involving black holes by assuming the island rule. So that motivation for our work is how do these page curves and the page time change when we do a class of element scalar deformation of the path. So start with giving a brief review of this Ryo-Takanagi formula. So the entanglement entropy of a boundary subregion B can be computed by evaluating the area of an extremal bulk surface such that this bulk surface, this extremal surface follow these two constraints. The first one is homology constraint, which says that the boundary of this extremal surface should be the equals to this boundary of this subregion. And the second one, there exists a region, 4-dimension 1 region, such that its boundary, the boundary of this region is the union of this extremal surface and the boundary subregion. So this is a classical formula. So we can try to find the quantum correction to that, and the quantum correction is given by the this contribution coming from this matter field that is here in this region RB. So this is just the von Neumann entropy of that region. So this is called the quantum extremal surface prescription or quantum extremal surface formula. Now it describes a W holographic model and the page curve. So this models is a class of models where the island rule can be written holographically. These systems have three equivalent descriptions. The first description is that a d-dimensional boundary conformal field theory, that is a boundary d-dimensional CFT with a d-1 dimensional boundary CFT. So this is a cartoon picture for that. So this is the defect CFT, and which is connected with a bath CFT, which you call it quantum wire, and this is a dot. So for black hole evaporation, which will be important for us, this second prescription, which is the non-gravitating d-dimensional CFT, the bath coupled to a gravity on an asymptotically AdS d space MD. The half space CFT bath is coupled to MD via transparent boundary condition at the interface point. And the island rule is saying that the entanglement entropy of the radiation region is given by extremizing this generalized entropy and choosing the global minima, if there exists, multiple extremal surface. This is the picture for that model. So here is the AdS black hole, which is coupled to a Minkowski half space, both sides. And this is a radiation region, right radiation region, and left radiation region. And this is the island. So if you compute this if you compute the entanglement entropy using this formula, we find that initially there exists no island surface and the entanglement entropy rises. After it, after some point, which is a page time, it saturates to the some constant area that is given by the island area of the island surface. And this is a page curve for eternal black hole. The third prescription, which is the Einstein gravity on an asymptotically radius d plus 1 space containing a MD as an end of the world brane. So here is this is a physical brane. So this is a physical brane, and which is connected by this defect to the bath, and there can be exchange of energy such that this system is in thermal equilibrium. The part of the bath is the radiation region, and there exists this island surface sorry. So there exists the island which is a co-dimension 1 surface on the physical brane, and we compute the entanglement entropy of the radiation region by computing this area of the extremal surface and minimizing. So now I will talk about the setup. So here we take with d plus 1 dimensional Einstein gravity with a negative cosmological constant and coupled to a scalar field with some potential b pi m square phi square. The action for such system is given by this equation 5, and you can find the equation of motion by varying the metric and the field. We take a very specific solution. So the solution is Kastner universe near the singularity region and AdS Schwarzschild or deformed AdS Schwarzschild near the boundary. So if we plug this ansatz into this equation of motion, which is the Klein-Gordon equation and the Einstein plus scalar equation, is find this set of ODEs, and the temperature of the black hole is given by the this f prime exponential minus chi plus by 2, and if plus is given is the value of f at the horizon, and chi plus is the value of chi at the horizon. To solve this equation of motion, we need to put some boundary condition. The boundary condition are listed here. So so this is a near boundary constraint, the r tends to 0, and this is a near singularity constraint, boundary constraint, which is r tends to infinity, and we have to put this expression when we are solving this fields. After we can define this new coordinate rho in terms of this radial coordinate. So we can define this coordinate tau in terms of this radial coordinate and find that the Kastner matrix is the following, and the Kastner exponents are given by this expression. Now we move to compute the surface areas. So we take a probe limit where the brane does not back react, and tensionless brain, and this is the bath, and the part of the bath is the radiation region. So there exist two possible classical surface that whose area we have to consider. One of them is known as the island surface, and another one is known as the Hartmann-Mallersson surface. So the island surface is a time-independent quantity, while the Hartmann-Mallersson surface is a growing function of time. So we can compute this areas by extremizing the area functional and find the Hartmann-Mallersson surface as a function of boundary time, and area of the island surface is just a constant. And the page time is given by when these two quantities are equal. So the area of the Hartmann-Mallersson equals the island surface area. There is another interesting quantity which is known as the page point. So if this radiation point, which is this point, this is a one point of which defines a radiation region. So if that point is greater than 0 but less than equals to some point, then there exists no page curve. So we get this constant entanglement entropy. But if the this point is greater than some page point, then we get this page curve, and we can plot this page point in units of horizon radius as a function of deformation parameter, which is just the phi naught by t to the power d minus delta, where d is the 3. And we find that so there is always exist some page point above which we always get this page curve and page time, but below this we did not get any page curve or page time. So next we plot this page time as a function of this deformation parameter, and we find that the page time for d equals to 3 and d equals to 4 is monotonically increasing function of the deformation parameter, and now we conclude. So we find that this keeping the radiation region are fixed, we increase the deformation parameter, find that within our numerics that the page time monotonically increases. And if we compute, if we compare to fixed values of the deformation parameter, we find that the difference in the page time increases as the radiation region is pushed away from the interface with the brain. That is, as we trace out more boundary degrees of freedom. We also found that as the deformation parameter is going to infinity, the page times are independent of delta, which from the BCFT point of view says that page time is just the ratio of the central charge of the boundary and the central charge of the bulk. We also find numerically that the exterior back reaction dominates when evaluating this page time, when this endpoint of the radiation region is near or comparable with the page point, but interior back reaction dominates when this radiation region is far away from the page point. And there exists some interesting future directions. So we can restrict the deformation only to the bath. To isolate this effect on the bath, we need a scalar field that vanishes on the brain. And in this brain plus bath theory, we'll only deforming the bath. And so in this work, we have considered the tensionless brain. Extending our work to non-zero tension brain adds an extra parameter to the picture and could lead to non-trivial phase transition involving critical phenomena. Also, it will be very interesting to ask how the holographic superconductivity may be probed by this page time. Thank you.
Right. So thank you, Ayan, for your very nice talk. Are there any questions for Ayan's talk? Please go ahead. The floor is open. Okay, appears that there are no more questions. Thank you, Ayan. You can unshare your screen.
Thank you. Thank you.
So the next talk will begin at 6 in roughly 10 minutes. Arun, are you around?
Yeah.
You can share your system that we can see whether it's working or not. We can do a check.
Yeah, I'll try.
Yeah, very good. Yeah, I think it's fine. Yeah, I think the cursor is visible, everything. Can you go full screen for a second?
Yeah.
Yeah, perfect. Very good.
Okay.
All right, so we can catch a break for 8 minutes before Rania starts talking. You guys can catch us. You guys can feel free to engage in discussions among yourselves if you feel like. I'll pause the recording as well. All right, I think it's time. Now we can start. So the next session, the speaker is Rania Bhattacharya from Center for High Energy Physics at IISc Bangalore. And he will tell us about his work on island and sub-region complexity in doubly holographic brain mold model. Welcome, Aranya. Please go ahead.
Hi. Yeah. Thank you. And let me start by thanking the organizers for inviting me in this wonderful workshop. So I'll be talking about this recent work on islands and sub-region complexity in a doubly holographic brain world model. Okay. This is based on this archive number and was done with my brilliant collaborators, Arpan, who is a co-organizer of this workshop, Pratik, and Ayan. So let me start by introduction. So we all know since last few years, we have seen many applications of quantum information in holography. And the most important one probably has been the holographic entanglement entropy. There have been many proposals of the holographic version of entanglement entropy, which involves Ru-Takayagi, Hubeni-Rangamani-Takayagi, and extensions of these proposals. So what these proposals tell us is that the entanglement entropy between two parts of a CFT can be computed by computing a minimal, which amounts to this Ru-Takayagi proposal, or extremal, which gives a time-dependent holographic entanglement entropy, area, minimal or extremal area, divided by 4 G Newton. And building on this, people think that there is a notion that entanglement builds geometry, and other quantum information theoretic quantities have also come in the picture since last few years.
where the general idea has been to extend this proposal of entanglement builds geometry to something like a quantum information builds geometry. And one of the central puzzle or central goal of this quantum information ventures have been to look beyond the black hole horizon. And in doing so, the central component that has come in the picture in the last few years has been the complexity equals volume, and also the complexity equals action conjectures given by Susskind and collaborators. We will concentrate on the complexity equals volume conjecture in this talk, which deals with pure states. And in general, complexity measures the difficulty of preparing a quantum state. So let's say we have already heard a few talks about complexity in this workshop. So if you have a reference quantum state and a target quantum state, which are pure states to begin with, then complexity measures typically the optimal number of elementary quantum gates that are needed to construct the target state starting from the reference state. And the gates are assumed to be unitary for a consistent unitary evolution of a quantum state. So this was works done by Nielsen, which was extended to like lattice systems by Jefferson Myers, and other extensions were done by Chapman, Heller, Camargo, Flory, and many others. So what I talked about was about pure states till now, but what happens when we go to a mixed state scenario? For example, we have a pure state, and we simply trace out some degrees of freedom from the pure state. And in general, we should have a mixed state. If the pure state is not some product state of two other states, if it's not a product state, then the traced out degrees of freedom should form a mixed state for us. And how to compute quantum information theoretic quantities for these mixed states. So the way people do so was also explained by Michal Heller in his yesterday's talk, and it involves a phenomenon called purification. So the idea is that when we have a mixed states, we need to add an auxiliary system or ancilla system to the mixed state to make it pure again. So given a mixed state, there can be infinite number of choices or ways through which we can add ancillary systems to the mixed state and make it a pure state. Then for a given mixed state, the quantum information theoretic quantity that we want to compute, for example, if we want to compute the entanglement of purification, we want to minimize that entanglement of purification or entanglement entropy quantity in terms of all possible purifications. And the parameters of these auxiliary systems play a role over there. Similarly, in computing the complexity of purification, the general idea is that one has to minimize the complexity functional in terms of the auxiliary system parameters. And this was done by Chapman, Myers, Heller, Camargo, Hahn, Takayanagi in a set of papers for simple enough systems, for lattice systems, for 2D Ising models, and so on. So what would be a holographic version of this, let's say, complexity of purification? So the idea is that, which was given primarily by Ali Shahiyar and then extended by Schwingel, Caceres, and many people, is to compute what is called the holographic subregion complexity. And the way it is done is to compute the maximal volume below the RT surface that divides two subregions of a pure state. So if I start with a pure state and I divide it into two subregions, both of these subregions are in general mixed states by themselves. Now let's say I want to compute the complexity of purification for these two mixed states, which when summed forms a pure state.
I think we might have lost Ranya's connection. Ranya might have lost his connection.
Ah, I see. I think so. That's what.
You guys can hear me, right? Arpan, you can hear me, right?
Hmm.
I think my connection is fine, but I think
He's back. You can start.
Yeah. Is can you? I have to share the screen. Yeah. Yes. So I don't know when exactly did my internet broke. So till what part could you hear me?
yeah, can you please go ahead, move on, some more slides?
Yeah.
I think you keep going.
Yeah, actually, I was in this slide.
Yeah, this was the slide you were discussing here.
Yeah. So
you didn't cover that. You were talking in the middle of mixed states.
Yeah. So what I was talking about is so for in general in mixed states, let's say I have a boundary pure state. I divide it into two parts, which individually are mixed states, and I want to compute the complexity of those mixed states. So the general idea is to compute the volume between the RT surface and the boundary subsystem. So in a time-dependent scenario, it would be the HRT surface or the QES surface for the cases where we would be interested. And these were proposals given by Alishaya, Schwingel, Caceres, and many other people. So as we know, as has been discussed in the last talk itself by Ayan, recently an extension of even the time-dependent RT surface, which is the HRT surface, has been put forward primarily by Engelhardt and Wahl, and afterwards it has been applied by many other people, which is known as the quantum extremal surface. And so it has played a major role in reproducing the page curve of entanglement entropy between the black hole and a non-gravitational bath. So which was a long-standing problem and could be interpreted as one version of the black hole information paradox. So it was done by many people like Engelhardt, Wahl, Pennington, Almheri, Maldacena, Hartman, Stanford Mahajan, and many others. So it was done for two and had some higher dimensional cases as well. So what plays a major role over in this program is something called entanglement islands, which are purely bulk regions, and they appear in the entanglement wedge of the radiation subsystem, starting from the page time, where the entanglement entropy curve or the growing entanglement entropy curve goes through a shift, and it either comes down for evaporating black holes or it saturates for eternal black holes. So as I said, there are two versions of a page curve. The evaporating one is like primarily it grows, and after page time, it eventually comes down to zero. Whereas for the eternal black holes, the initial growth is there, but after the page time, the curve saturates. Now, the question that we would be asking in our program is, what about the subregion complexities of these black hole and radiation subsystems? So we should remember that the black hole plus radiation, it gives us a pure state in general. And we actually studied this subregion complexity for evaporating black holes in an earlier paper. And it was also studied by Myers and collaborators in one of their papers, Quantum Extremal Surfaces Made Easy Part 3, in which they studied the complexity on the branes, and the paper that I'm going to talk about. So in the previous paper that I mentioned, in which we studied the evaporating black holes, and in fact, I talked about the paper in the last installment of the same workshop. In that, we studied certain multi-boundary wormhole models of evaporating black holes, and we found a typical jump in the subregion complexity of radiation subsystem at page time. which we explained by a quantity called holographic complexity of purification, but rather I should call it probably holographic, let's say, complexity of auto purification, because this purification is different from the purification that I was talking about earlier. In this case, what happens is because the island region certainly gets included in the entanglement wedge of the radiation subsystem, there are certain auto purification of modes or auto purification of certain modes happening. Those are the modes that are in the island regions in the black hole side, and in the radiation, the partner modes in the radiation side. So for these modes, while computing complexity of purification, one doesn't need to add any ancillary system, because the island region already gets included in the entanglement wedge of the radiation system. So this complexity of purification, we explained that this results in the jump of subregion complexity of radiation at page time. This was a constant jump, and this jump didn't grow with time. So yeah, now let me move on to the rest of the talk, where I will explain the this particular model that I was talking about, which is the brain world model, not the multi-boundary wormhole model. So I covered the introduction. I will now talk about the brain world model. Then I'll talk about something from this model itself, which is the left-right entanglement. And then I'll talk about eventually the subregion complexities of the radiation and the black hole subsystems. And finally, I'll end by some concluding remarks. So the brain world model that I'll be talking about is, or rather we consider in our paper, is basically the same model that was studied by Hao Gang, Kart, Subrat, and collaborators in their paper of this archive number. So the idea is that islands in higher dimensions were modeled by, particularly by Myers and collaborators, by certain RS brain world models with subcritical tension brains. Another version of which is also known as Karch-Rundle brain world models, where massive gravitons exist. And in general, RS models are such that we treat the universe as a higher dimensional space, and the elementary particles are assumed to be localized on the brains in the brain world model. And the fine-tuning parameters over there are the bulk cosmological constant and the tension of the brain we consider. So in the model that Subrat, Hao Gang, and collaborators considered, they what they do extra is to also take into account a weakly gravitating bath, whereas in previous models people only took into account non-gravitational baths. So the way they do so is to by introducing a second brain in the bulk, and in this way they argue that the gravitons become massless and mostly localized on the weakly gravitating brain, although some of those are also localized on the physical, or rather actual brain that was present in the non-gravitating bath scenarios as well. I will show you some pictures as I go on. And the brain angles dictate, so there are two brains now in our picture, which would be like these ones. The left one we would call the physical brain, which is an angle θ1 from the conformal boundary, and the bath brain, let's say the weakly gravitating brain, is at an angle θ2. So these angles θ1 and θ2, they dictate the strength of the gravity on the brains. So as you can see, the weakly gravitating brain is in lesser angle with the conformal boundary over here. And we, the authors of this paper, considered zero temperature as well as thermal black string configuration in this bulk region. And what they find is that for a gravitational bath, so in general, the idea would be that there is some gravitational bath region where the radiation gets stored. Let's say that is this R region, and there is some island region in correspondence to what Owen was talking earlier. But there is a difference in the case where one has this weakly gravitating bath. So what happens here is what is found by the authors of this paper is that in case of a gravitational bath, there is no diffeomorphism invariant way to differentiate between local degrees of freedom, because the gravity is present both in this black hole and as well as the bath region or radiation region. So you cannot really differentiate the gravity degrees of freedom between or systematically between black hole and the radiation region, which results from the fact that no simple tensor factorization of Hilbert space is possible in gravity. So
Ranay, are you around?
okay, so as I was saying, in this case, what the authors found that the radiation region for zero temperature case becomes simply a point in this whole line, and therefore there is no entanglement entropy for zero temperature cases at all for a gravitating bath, which is a constant zero entanglement entropy, we could say in another way. Or what we could say is what defined for the thermal black string configuration is there is this horizon in this picture, and the radiation or the HRT surface becomes simply this or QS surface becomes simply this horizon region. Therefore, what it measures is the Bekenstein-Hawking entropy. Okay, so let me repeat what Owen probably already said in this context. So when we had one brane in bulk, so that would be the configuration with non-gravitating bath. Let's say we don't have this right brane in our picture at all. Then there are three equivalent pictures through which one could describe the physics. The first one would be a d-dimensional boundary CFT, which is this boundary with this CFT with this red point as the boundary. The second one is asymptotically AdS-D connected to a d-dimensional CFT on half Minkowski space. So we could also consider this asymptotically AdS-D brane connected to a d-dimensional CFT. And the third one is the simple thing that Einstein gravity on asymptotically AdS-D+1, which is the bulk region over here, containing a d-dimensional KR brane as an end-of-world brane. So this was the scenario in the non-gravitating bath picture. So what happens if we have this right brane in our picture as well? So what happens is one can extend these equivalences to again three equivalent pictures. One would be a d-1 dimensional defect CFT, which is simply this red point. So we don't have this boundary CFT, d-dimensional CFT anymore in our picture. So we have this defect, d-1 dimensional defect CFT. The second one would be two d-dimensional CFTs or with asymptotically AdS-D bulks, which are the two branes connected at a d-1 dimensional defect. And the third one would be Einstein gravity on asymptotically AdS-D+1, containing two end-of-world branes instead of one. connected at the defect again. So this is the picture through which one uses the ideas of double holography in these models. So one can simply get away by computing quantum extremal surfaces instead of, or rather classical HRT surfaces, rather than computing some bulk entanglement entropies in this picture of matter fields in this picture. And so one computes the dynamical RT surfaces in the bulk for the two brane situation. And as I mentioned, that the dynamically decided radiation regions for the vacuum or zero temperature case becomes just a point, and for the black string it becomes the whole of the horizon, which gives us the Bekenstein-Hawking entropy. So in both cases, with the gravitating bath, the authors found that the entanglement entropy becomes a time independent constant, which is supported by previous flat space arguments given by these authors in a paper, and which is based on the idea that all bulk information, even the information inside the black hole, is present in an infinitesimal width Cauchy slice on boundary. So the main takeaway from whatever I told here is to understand that in just the result of this part of their paper, that the entanglement entropy remains a time independent constant and one doesn't get a page curve. But what they also showed is some other scenario where they indeed get a page curve, actually an eternal black hole page curve, by considering something called the left-right entanglement. And this page curve can be derived by considering simply by partitioning the defect CFT degrees of freedom on the left and right modes. By the left and right modes, naively by saying that the left modes live on the left brane and the right modes live on the right brane of the thermofield double state of the d-1 dimensional defect CFT. So I showed you one defect, but in the other side there will be another defect which is connected by the Einstein-Rosen bridge and so on. So it is basically a thermofield double state. And in such a scenario, as I mentioned, that naively one could understand this partition as some left and right modes living on the left and right branes respectively, and the partitioning point would be the defect point itself, red point. And one considers candidate RT surfaces in this picture, which they assume to end on the defect. So let's see this picture. We would have two candidate RT surfaces. One could be just the Hartmann-Maldacena-Matthews surface, which grows indefinitely, which starts from this defect and goes all the way through the partnered defect mode on the other side of the Einstein-Rosen bridge. And this red circle actually is sort of the horizon in our picture. So after this, you would have the beyond horizon region. So one of the candidate RT surfaces would be the full Hartmann-Maldacena-Matthews surface. Another RT surface would be all the surfaces that starts on the one on either of these branes and ends on the defect point, because defect point is the point through which we make the partition. And there is, from this picture itself, you can see that there are many surfaces, infinitely many surfaces, which could start from this defect and end on these two branes. And what one finds is that although naively we were considering the left modes to be situated on the left brane and right modes to be situated on the right brane, it is not the case in general, because if one considers the lengths of these lengths or areas of this Hartmann-Maldacena-Matthews surfaces and the island surfaces, initially the Hartmann-Maldacena-Matthews surface is in the minimal surface, but as it keeps growing indefinitely with time, whereas these surfaces are in the exterior region and they don't grow, they are constant surfaces. At some point of time, these surfaces, or rather this surface in particular, becomes the minimal surface choice. And as we can see that although primarily the left modes were situated on the left brain and the right modes were situated on the right brain, after a certain point of time, some of the right brain modes are also situated on the left brain. Or in another way, we could say that some of the left brain modes get accessible to the entanglement wedge of the right brain when this green surface becomes the preferred minimal surface. So one can indeed recover a eternal black hole page curve because these are simply constant surfaces. So eventually growing Hartmann-Walderson's surface is this black line, and these are the constant lengths or surface areas for these island surfaces, where I have taken this blue, green, and red things. They amount to this different θ1 values. So I'm basically changing this physical brain angle. In this picture, I haven't changed the right brain angle, but if I even change that, that doesn't matter because it is always weakly gravitating. And as one can find out that since it is weakly gravitating, the island surface will always come in the strongly gravitating brain. So I vary the θ1 coordinate, or rather θ1 angle, and I have different island surfaces. So for θ1, as you can see, for increasing θ1, the length of the or area of the island surfaces decrease. Another way of understanding is the same thing, is that the point on which this island surface is anchored on the left brain comes closer to the defect point as we increase the strong brain or physical brain angle. Okay, so the fact that is understandable from here that the left and right modes are not simply the modes living on the left and right brains, but different parts of left and right brains can be accessible to left or right modes at different times, which is similar to something that we saw in a non-gravitational bath scenario where islands appear and one indeed gets a page curve. So what we find is a non-trivial transition from one RT surface to another, and the left modes could be analogously thought of as the eternal black hole modes, whereas the right modes could be understood as the non-gravitational radiation region where the radiation gets stored. And at some later point in time, this a part of the eternal black hole interior becomes accessible to the radiation region. And this page curve actually exists in both gravitating as well as non-gravitating bath model. Even if we consider a bound brain instead of considering the right brain, if we consider the space to be all the way through the conformal boundary, even if then one could define this partition and one could find this kind of surfaces. So the right brain can be at the conformal boundary or at a small angle, which is the case considered over here, which is weakly gravitating in the bulk with the defect. So the island surfaces can in principle be found on both the brains, as I mentioned already. Operationally, what we do is we shoot geodesics from different points on this left brain or right brain also. You could shoot geodesics, and we put the constraint that these geodesics have to hit the brains orthonormally as well as they have to hit this defect point orthogonally. And the minimal one among all possible island surfaces is what we consider to be the preferred minimal surface. And as I mentioned that this point on which the island surfaces end on the brain is called the critical anchor, and the critical anchor is monotonically decreasing function of the brain angle. So if we increase the brane angle, the critical anchor comes towards the defect points. So since for the bath brane, or rather the weakly gravitating brane, it is always in a lesser angle than the strongly gravitating brane, the islands, the preferred islands will always, the minimal preferred islands will always be on the physical brane, because these candidate island surfaces on the bath brane would always be bigger in area or length, depending on the dimension of the space-time. Okay, so now I will talk a little bit about the computation of this surfaces. We consider the AdS d+1 black string metric in the bulk, which is simply this one. And we consider d is equal to 3 and d is equal to 4 scenarios, to be precise. And in this coordinates, u greater than 0 is simply the radial direction. Mu can run from 0 to 2 pi is the angular coordinate. And this x vector denotes the d minus 2-dimensional orthogonal directions. So the Hartmann-Maldacena surface is always located at a constant mu angle, which is simply this straight line going from one defect to its partner defect mode. And therefore we could consider simply mu equals constant slices, minimize the area functional there. We start from this time dependent action and minimize this or extremize this Lagrangian, which should be this one. As we could figure out, we don't have any explicit time dependence over here in the Lagrangian, and therefore you can write a conservation equation of this form, from which we could write u dot this way, where the sign is plus, where u is less than the horizon, which is the exterior region, and minus otherwise. And from by requiring the realness of this thing inside the square bracket, we could integrate up to certain critical value of u, which is defined like this. And in this way, one can indeed compute the area of this Hartmann-Maldacena surfaces. And one finds out there would always be certain divergences over there, and after we regulate those divergences by the UV cutoff delta, the regulated Hartmann-Maldacena surface has this area, which grows indefinitely with time, whereas the island surfaces are, as we mentioned, are constant, and therefore there is no time dependence, and the embedding function is found by solving with a time slice and considering u equals to u of mu embedding.
Rania, why is the leading term, the leading divergence negative? Is it a time?
No, actually the leading divergence is positive. Since I am mentioning this is the regulated one,
oh, yes,
so I have subtracted this thing from.
Got it. Thank you.
Okay. And the embedding action for the black string metric for the island, for computing the island surface area in d equals to 4 is given by this action. And there would again be a similar divergence over here, and one could indeed show that actually it is understandable better from this picture, that at some point near the defect, this island surface matches exactly with the, or overlaps with the Hartmann-Maldacena surface, and therefore the divergences of these surfaces are also very similar in terms of the UV cutoff. Therefore one needs to again regulate this island length, and finally one could get a constant surface area. Now these plots simply denote how we exactly compute the critical anchor, that is the point on which the brane on which the island surface ends. So we require the surfaces which can go up to the defect, that is u equals to pi by 2, but it cannot reach the conformal boundary, which is this boundary. So it cannot go to pi by, it can go to pi, but it cannot go to pi by 2. And if we look at these mu values and corresponding u values, if we keep changing u values, we would find that at some point these surfaces stop going all the way to pi by all the way to pi, and they simply hang in space-time. So the first surface hanging in this picture would be the U value corresponding to the critical angle. So these are the way through which we compute the critical angles, both for d equals to 3 and d equals to 4. Now let me move on to the subregion complexity business. So we are interested in a way to compute the volumes of these regions for the Hartmann-Maldacena volume and volumes below the island surface to compute the island volumes. Now, as I mentioned that for the static case, the situation is very simple and one could simply compute the volume below the RT surface. However, for a covariant definition or a time-dependent case, the proposal that exists is a combination of the complexity equals volume, which requires wants to consider maximal space-time volumes, and the static proposal. So the covariant subregion complexity proposal would be something like we have to consider all the time slices given the anchored RT surface. We have to go to even bulk times, which are different from the boundary time T0, which I denote by T, and we have to look for all codimension 1 bulk slices, and among all those codimension 1 bulk slices, we have to find the bulk slice which maximizes the volume. So although that is the proposal, that is a very hard job to do in case of a subregion complexity business, because it is already hard to figure out which RT surface is the minimal one. Then among all the RT surfaces, you have to rather all the preferred RT surface, which is anchored at specific points, you have to go to other bulk points, other bulk times, and figure out for which bulk time the volume is maximized. So we actually do not do this job. Rather, what we do is, so we exactly know that up to the page time, the Hartmann-Maldacena surface which grows is the preferred HRT surface, whereas after the page time, the island surface, which is a time independent surface, is the preferred HRT surface. So we simply consider the volumes between the left brane or right brane and the corresponding RT surface, and as we'll argue later, that we can qualitatively match the behavior between these volumes and the maximal space-time volumes, if one is able to consider so. The reason why it is in general hard is to, instead of considering either mu dependent embeddings or T dependent embeddings, which we do for island surfaces and Hartmann-Maldacena surfaces respectively, for a time dependent case, one has to in general solve the equation of motions in terms of both a mu and T dependent embedding, which is in general a very hard problem to track. Maybe it could be done numerically, but still we couldn't figure out a very good way to do so. So the volumes that we compute are simply, let's say for the left modes, initially Hartmann-Maldacena surface is the preferred surface, for which the volume would be the volume between the left brane and this Hartmann-Maldacena surface, and at a later point of time, the volume would be, after page time, the volume would be simply a constant volume, which is between the volume between the island surface and this part of the left brane. Again, what we find is that this volume, that is the Hartmann-Maldacena volume, grows indefinitely in time, whereas the island volume, which is the preferred volume after the page time, is simply a constant volume, because the island surface also doesn't, also is a constant time independent thing. And these are the plots for different physical brane angles. So what one finds that initially the volume grows until the page time, whereas after the page time, the volume corresponding to the left brane, let's not still call it eternal black hole, because it is a situation where the plot suggests that the left brane or the left brane modes are analogous to the eternal black hole situations, because they give a similar eternal page curve, but in principle it is basically the left and right modes of the defect. So initially the complexity of the left modes grow, and after the page time, it simply becomes constant. And as we increase the physical brane angle, these values decrease because simply the volumes also decrease. One could figure out from this figures as well. As we increase this brane angle, this critical anchor point would come down towards the defect point, and therefore the volume would also decrease. So as I mentioned, let's say we consider the maximal volumes for the Hartmann-Maldacena volume, which let's assume is not assume, but will be in general greater than the volume that we compute. And island surface is independent of time or time independent surface. So it doesn't really depend upon bulk time or whether we are considering bulk time or boundary time. So this one is all okay. Whereas the Hartmann-Maldacena maximal volume could be greater than the volume that we considered. That is, the maximal volume could grow more than the volume that we have plotted over here. However, time 0, we could simply figure out from this figure that this volume at time 0 would still be greater than this island volume. And therefore, even at time 0, the Hartmann-Maldacena volume is greater than island volume. That is consistent with what we find over here, that the blue line after page time is less than the t equals to 0 volumes. And so overall, one could argue that even if one considers the covariant volumes, one would still get a similar plot that is initially growing, and after the page time, the volumes would come down to this constant volumes of islands. Similarly, one could consider the volumes corresponding to the right brane. One would have to simply again compute this side of the Hartmann-Maldacena surface by foliating with these Hartmann-Maldacena surfaces themselves throughout the space-time. And instead of the jump, instead of the dip, one finds the jump in this case. So initially the volume would be this volume. Afterwards, a new volume will be added, which is simply this volume will be added to the Hartmann-Maldacena volume after the page time, when these modes also become accessible to the right brane. So newly change from what we find in case of evaporating black holes and radiation subsystem we considered also over there. So that would be analogous to considering right brane volumes over here. So the change is that the new volume added to the Hartmann-Maldacena volume after the page time also grows, because you see, although we have drawn until the horizon, this region also has an interior of black hole region. So this volume is also supposed to grow. So instead of a constant volume being added after the page time, in case of this model, a growing volume gets added after the page time to the radiation subsystem, or what exactly is actually is a right brane or right modes of the defect CFT. So in this case, if we compute the change of the volume after the page time, the growth is like this. Although the reference volume that we have taken also grows with time, but we have simply subtracted that growing volume from our after page time volume. So initially this volume is 0, which is delta VT. And after the page time, the change of volume is there and it grows with time. Whereas if we considered the total volume, that we did not consider the reference volume to be 0, we would find that there's a zoomed out version of this plot where initially the right brane volume grows, and after the page time, there is a small jump in the point of this time, which is the page time, and afterwards the slope would increase a little bit than the previous one. As you can see, as you go forward in time, the distance between the black curve and the red curve increases a little bit. So instead of a constant volume being added, a growing volume results in this increment of difference between these two plots. So these were the main results. Now let me end by some concluding remarks. So we compute the left and right complexities where the system follows an eternal page curve, or a page curve analogous to an eternal black hole of entanglement entropy. And at page transition point, the subregion complexities go through a jump for the right brane or right modes, or dip for the left brane or left modes, consistent with previous studies about evaporating black holes. Although what is different is that instead of the jump being a constant jump, we have a jump over here which grows with time. The Hartmann-Marder volumes are different for different brane angles, as is expected. Although when we were computing the Hartmann-Marder surface area, it was a constant surface, and mu equals to pi/2 surface, and therefore the area doesn't change with changing physical brane angle, but the volume changes because the volume enclosed by these two things, the left brane and the Hartmann-Marder surface, is supposed to change. The volumes corresponding to the left brane after the page time becomes constant, which is the volume between the island surface, which is a time independent surface, and the left brane. For the right brane, the volume increases forever with a jump and an incremental growth rate after page time. The jump can be, again, to the best of our understanding, should be associated to the complexity of the automatically purified modes within the radiation entanglement wedge, because more and more modes keep becoming accessible to the right brane, and those modes automatically get purified with their partner modes in the right brane system, and one doesn't have to add any ancillary system to compute the complexity of purification for those automatically purified modes. But one has to consider the complexity of these automatically purified modes as well while computing the total complexity, because that forms a part of the state as well. So these, if one can address these quantum gates in some scenario or some model, then possibly one could have a better understanding of what we are proposing as the reason of the jump or dip at the page time for the right and the left branes respectively. And the volume evolution matches qualitatively with the covariant maximal volumes, as I argued, and supports the plots derived. So there are certain future directions to this problem. One is to divide the radiation subsystem into even different parts. Let's say I have a R, or the right brane, if I can divide it into different regions, R1, R2, and so on, as was done in a paper by Onkar, Vijay, Arjun, and people, called geometric secret sharing. And in those cases, one could check how the quantum secret of the islands, that the region getting added to the entanglement wedge of the radiation subsystem after the page time, is separated into these different parts of the radiation subsystems. And if the union of those parts can give us the total island or not, which actually the paper that I was mentioning, the geometric secret sharing paper authors find that actually even if one considers the union of the R1, R2 regions, then even then one could only have access to a partial region of the island. And to have the total access of the total island region, one needs to do certain secret sharing or through some quantum channel and so on. So I'd like to understand such things, if such things can be understood by computing volumes in such models, and we are working on that. Whereas another direction would be, as Owen figured out, to check if renormalization group understanding from bath deformations can be built from computing subregion complexities, following something similar to what Owen talked about. And finally, to understand the event of auto purification that I mentioned, that the purification of the island modes along with their partner modes in the radiation subsystem due to appearance of islands in a simple lattice model, although it would be extremely non-trivial to do, and I don't have a very nice idea of very precise idea of how one could do that, but it would be nice if this purification business could be understood better. Yeah, so that's all I had to say to you, and thank you for all your time, and sorry for all the interruptions due to network disconnections.
Not a big deal. Okay, Aranya, thank you very much for your nice talk. The floor is open for questions. Please go ahead and ask questions if you have for Aranya. And also, if Pratik is around, you can also ask Pratik questions.
I think, right.
Oh, no.
Yeah.
I'm sorry, my mistake. Sorry. Okay, it looks like there are no more questions for the speakers. So I thank the speakers, both the speakers for this session once again, Ayan and Aranya. Thank you very much for your nice talks. We hope to see you back in the next year as well, if we have one. Thanks.
Yeah, thanks a lot.
So we start our last session of the workshop, and we begin with the talk by Edgar Shagorian from UPenn. Welcome, Edgar, and he will talk about islands and cosmology. So I will hand it over to Edgar to start the talk.
Thanks, Arpan. Thanks for inviting me, and thanks for hosting a great workshop. I was able to catch bits and pieces of it from my time zone, and it looks really exciting. So I'm going to talk mostly about a paper that appeared, I guess, about a year ago now, and some other work that I did with Raghu Mahajan, which never really appeared in print. But hopefully if I have time, I can make some comments about what he and I have been discussing and trying to understand. So I'm going to do a kind of lightning overview of the information paradox and the role of islands in the information paradox. So as everyone knows, in the 70s, Hawking found that pure states seem to evolve into mixed states in the presence of black holes, if you assume that the entropy is given by the Bekenstein-Hawking law. So assuming this, he found this, this puzzle, and he called it the breakdown of predictability. So this has kind of haunted us for a long time and continues to haunt us. In slightly more computational terms, he computed the entropy of radiation that comes out of a black hole, and he found this green curve, which after a little bit of time is basically linear and continues growing linearly until the black hole completely evaporates, and then you're just left with some finite amount of entropy. But if you started by creating the black hole from a pure state, of course, the entropy is 0, and you can't evolve from 0 entropy to finite entropy without having pure states evolve into mixed states. Okay, so that is the puzzle. In the 90s, Don Page provided a target for what a correct computation should look like, and that's this curve. Okay, he computed for a unitary theory, if the radiation actually encodes what fell into the black hole, at some point this has to sort of turn around. The time at which it turns around has been called the Page time in his honor, and has to go back down to 0, again, if the black hole is created by a pure state collapsing. Okay, and in 2019, there was a flurry of progress in trying to compute this purple curve, what we call the Page curve. Okay, it was first computed from holography by these authors, and then later by assuming the gravity path integral in these two papers. So I'm give a very quick overview of that in the next slide, but what I want to talk about today is, does this have any lessons for cosmology? My perspective on trying to understand black holes and the information paradox is really as a warm-up problem to trying to understand cosmology. That's my personal motivation. So let's jump into lightning review. So how was the page curve computed? Well, using holography or again, the gravitational path integral, there is a new formula that you can write down for the fine-grained entropy of some region R in a theory with gravity, okay? And the formula looks like this. It's called the island formula. And what you do looks a little bit funny. If you want to compute the entropy of some region R, so first, just to kind of have things under control, region R should be in a weakly or non-gravitating region of space-time. So in this picture here, I have a Penrose diagram of an evaporating black hole in asymptotically flat space. And this purple line is just some kind of arbitrary line I've drawn where gravity should be kind of weak outside of it and somewhat strong inside. You know, this kind of thing is made more precise in these models of black holes in AdS coupled to a flat space bath. But let me use this picture for now. And what you want to do is you want to compute the entropy of radiation out here. So here I've drawn various Hawking modes. So this red mode here is entangled with its partner red mode in here. This green mode is entangled with this green mode. And you want to measure the entropy of these little black slices here, labeled by T0, T1, T2, T3. So the Hawking computation would tell you that the entropy just increases linearly. So those same times are represented here in this plot. And the Hawking entropy just says that this kind of goes up linearly. You know, each of these entangled modes you could think of as like a bell pair. It contributes log 2 to the entanglement. Then you just keep getting more and more log 2s, and it just increases until the black hole is done evaporating and it tapers off. Okay. What the island formula instead instructs you to do, so these are the regions R here. It says when you're trying to compute the region R, you should look for other regions called island regions, in the gravitating part of space-time, which is the left of this purple line, which if you input it into this formula, where you extremize what's called the generalized entropy of I union R, and then minimize over all possible islands, you look to see if that gives you a smaller answer than the Hawking answer, which is this green one, which becomes big at late times. Okay, that's the name of the game. And what happens is at early times, the answer to this minimization problem is to choose I to be a trivial surface. So you don't include any region I. So at T0, the entropy is just the Hawking entropy, okay? That's here. At T1, it's the same. You don't include any island in the gravitating region, so you still have the Hawking entropy. But at T2, something happens. At T2, you've accumulated so much what we call semi-classical entanglement, which is the entropy of R on this sort of fixed space-time without including islands, that actually if you include this region I and then extremize and minimize, you get a smaller answer for the entropy of R. Okay, so here's the island region at time T2, and it leads to this, so this black curve is the page curve, it leads to this smaller entropy. Okay. Once the island appears, it sort of stays. At later time T3, the island looks like this blue curve here, and it leads to a decrease in the entropy of R until it eventually goes all the way back down to 0. I'm sorry?
I have a question.
Yeah.
So in the intermediate region where the entropy is the highest, is it a mixed state? Is the radiation in a mixed state?
Yeah, the radiation by itself is in a mixed state if you trace out the black hole, but you should think about it as a bipartite system. It's just entangled with the black hole, and together they're in a pure state.
So the entire pure state equals to the final pure state.
That's the idea, yeah.
Okay. Okay, thanks.
Sure. Any other questions? Okay, so I'm not going to spend much time on this because I'm assuming people are familiar with it, but this is the island formula, and it tells you how to compute the entropy of a region R in a theory with gravity. Okay. And the reason it's sort of conceptually interesting, okay, so technically it produces for you this page curve, but conceptually, what does it mean? Well, we think it means that the island, this region in here, is encoded in the radiation in the same way that the bulk of AdS CFT is encoded in the boundary. And there are these various papers discussing this. For a somewhat different view, I think I remember Subrat spoke at this workshop, and I think probably presented his perspective on these sorts of problems. And that approach is well, that's different. I mean, there's a lot of similar ideas, but I think he would agree with probably very few of the statements on this slide. So you should also check out his perspective and his papers with his various collaborators to understand that perspective. But from the island formula perspective, yeah, this encoding of the interior and the exterior only happens after a certain amount of time. And then it's very much like AdS CFT. Okay. So, something that happened early on in the days of islandology, early on meaning, a year or two ago, is people sort of began searching for islands. They tried to cook up various examples and try and find islands. There's still sort of papers appearing about islands here or there. And so you might hope to kind of construct a more, let's say, methodological search, a more kind of thoughtful search for islands. For example, if someone sort of just hands you a space-time, how would you determine whether or not there is an island? Now, a priori, it's a difficult question because whether or not you have an island depends on a region R, which is often like, it could be a totally disconnected universe. It could be a very far away piece of space-time. So if you fail to find islands, you can always second guess yourself and think, oh, if I was more clever about the region R whose entropy I was computing, I would find an island. That's what makes the problem a little bit difficult. So we would like to write down some necessary conditions for islands that don't depend on a region R. Okay, if you do this, then you can answer the question. If someone hands you a space-time without even telling you what region R you're looking at, you can tell them whether that space-time can host an island or not. Assuming you check these, well, you can rule out the possibility of the space-time hosting an island because we're going to write down necessary conditions. So let me get into the technical details. So I'm going to talk about 3 necessary conditions. It's okay if you don't follow the details. The important point is that they exist. So the first necessary condition comes from the extremality condition of the island formula. If I just go back very quickly here, remember there's this extremality formula of the generalized entropy, S gen I union R. So that means the derivatives have to vanish. So here I've written one of the derivatives. It's a null outgoing derivative. It's not super important, but that thing should vanish. Okay, that's the extremality. And I can just rewrite this formula. So I expanded S gen I union R in terms of the area term plus the QFT piece of I union R. And I added and subtracted the QFT entropy on I. That's these 2 pieces. That obviously doesn't do anything. And then I added this piece here. Why can I do that? Because this derivative is with respect to the endpoint of I. Okay, you extremize for the island regions. And so it just annihilates the QFT entropy on R. Okay, so this is still a correct equality that directly follows from this. And now see, I've split the terms into these 2 pieces, which hopefully are familiar. This is the generalized entropy of I. Okay, so notice it doesn't reference R at all. That's where we're headed. We want a condition that doesn't reference R. And this is the mutual information between I and R. Okay, these are the QFT entropies. So in terms of those concepts, I can just rewrite it this way. Here's the generalized entropy. Here's the mutual information. And monotonicity of mutual information, which says as I grow regions, that the mutual information should increase, tells me that this thing is positive. Okay, this derivative. And I could repeat the same process for an inward null derivative that shrinks the regions. And then monotonicity of mutual information tells me that the derivative is negative. So altogether, you have this inequality, which does not depend on region R. Okay, and in words, the boundary of I, the island, is in what's called a quantum normal region. Okay, this is just defined in analogy with a classically normal region, which would be taking these derivatives of just the area. And quantum normal means you just replace the area with the generalized entropy, which is the area plus a matter entanglement entropy. Okay, so the boundary of I is in the quantum normal region, and this condition was, already written down in this early island paper by these authors. Okay, that's one condition. You can, again, rewrite the extremality condition in this way. So if we do that, then we can use SSA, strong subadditivity of the matter entropy, to write down this inequality of the derivatives. And then we can rewrite it this way. So here I have, the condition here is a little bit different because I have a region R whose entropy I'm computing. There's some region I, which is an island. And then I need to divide the rest somewhat arbitrarily to define what's just labeled G and B. They don't really stand for anything. But often we think of B as in like still the non-gravitating part of space-time and G as in the gravitating part of space-time. So it requires this division. So making this condition strong requires a little bit of, not ingenuity, it's not that ingenious, it just requires some fiddling with what you would call region G. But in any case, once you define these regions, you can do similar tricks using SSA or monotonicity or whatever you want. And you end up with, again, a quantum normal condition on region G. You have this inequality on region G. Okay. This will be sharpest when we have a non-gravitating space-time entangled with a totally gravitating space-time, because then region G will just be the part of the gravitating space-time that is not the island that you're interested in, for example. Okay, so you have this condition as well. And the final necessary condition is going to be a little different. Notice these conditions came from the extremality, that the derivative of the generalized entropy has to vanish. The conditions 2 and 1 both came from that. Condition 3 is going to come from the minimality part of the formula. The minimality says that if you include an island region, the total generalized entropy should be less than the entropy without the island region. Okay, that's what the minimality condition says in the island formula. You can rearrange this. I again added and subtracted the QFT entropy of region I. And then you can use the Araki-Lieb inequality, which says this, to argue that this right-hand side has to be positive. And then you can get that the QFT entropy of I is greater than the area over 4. Now, I pulled a fast one because I put a squiggle here, and I put a hat on SQFT. Why did I do this? It's because this inequality and these formulas you need to be a little bit careful with. In all the earlier formulas I was writing down, I was very careful, even though I didn't talk about it, to make sure that I had UV finite quantities that I was discussing. And here, I don't have that, okay? Here, I don't have, if I start using Araki-Lieb, I don't have UV finite quantities. You have to be very careful to regulate this thing, put in a cutoff, and go through some careful steps so that in the end, what you get is that the finite part of the QFT entropy on I, that's what this hat refers to, the finite part, that thing is greater than the area over 4. And what is a squiggle here for? The squiggle is here because once you put in the regulator and compute these various things, there are some terms that I've dropped, which are subleading compared to this area over 4 term. Okay. Another way to think about it is the finite part of the QFT entropy on I, of course, can be regulator dependent. So you could imagine messing with that regulator and changing what this finite thing is. And that's what the squiggle is there to take care of. If you do this whole thing carefully and you start messing with the regulator and try and make this big, you'll see that the terms that you dropped will start competing and then this formula will break down. Okay, that's technically what's going on. Conceptually, this is exactly what we would expect, right? When we include an island region I, it's because it has a lot of entanglement with region R, right? So that's the way the island formula wins. You pay a gravitational cost in the area term. So let me go back to the island formula. Right? If you include a region I, you're going to pay a cost here. This is going to increase the entropy. So the only time it's going to be useful to include an island region is if this SQFT I union R decreases the entropy of R by a lot. And for it to decrease the entropy of R by a lot, I has to have a lot of entropy. But before you even talk about who exactly it's entangled with, it had better host a lot of entropy. Okay, so it's not a surprise that we want the entropy of I to be sort of, in a sense, more than this A over 4, so that we win by including an island. So conceptually, that's all that's going on. And we call it Bekenstein violating because it kind of looks like it violates the Bekenstein law, which says that you can't fit A/4 worth of more than A/4 worth of entropy in a region. Of course, it doesn't violate the Bekenstein law because it's just a statement about the matter entropy, and we don't even know how to really compute the fine-grained entropy of this region I anyway. Okay, so in the later part of this talk, I'll call this Bekenstein violating. And just some fun, I'll call it phenomenology in quotes. It's just true that if you look in our past light cone and try and see when this bound is violated, if you assume that the matter entropy is thermal, so meaning exactly thermal, only purified like outside of our horizon, let's say, then this bound is violated at the electroweak scale, which is just kind of a funny coincidence. It's what a phenomenologist might call it, an electroweak miracle or something. Anyway, I don't think this means anything, but it's just a funny thing you can compute. Okay, those are the three necessary conditions. I'm not really going to go into the details of them anymore in the rest of the talk, but I'll stop now in case people want to ask anything about them.
So I have a nice question actually. So the three conditions you showed that these are all the conditions that a von Neumann entropy usually satisfies, right? I mean,
there are conditions that what? Sorry?
That usually the von Neumann entropy satisfies, right? To make it to interpret as a valid entanglement entropy. I mean, the Araki-Liev conditions, Haber-additivity, they usually it satisfies. I mean, if I compute S QFT by a formula rho log rho, isn't it automatically satisfies conditions?
Yeah, the properties I used, SSA and monotonicity, those have to be satisfied by any reasonable entropy. The input was the island formula, that the extremality and minimality conditions. So those are the inputs, and that's not something that like an entropy has to satisfy. So those are the inputs, but from there, you're exactly right. I only use things that have to be rigorously true about a von Neumann entropy.
I see. Thanks. I see.
Yeah. Yeah. So here are the three. I just skipped this slide while the question was being asked, just so people can see the three conditions kind of all together. So to emphasize one more time, these are necessary conditions, and they're independent of the region R. Okay. So the boundary of an island has to be in the intersection of all three regions, and I'm going to have several examples now where we look at what this looks like.
Okay. I have a question.
Yeah.
Could you go back to your slide where you have the island, not the island, the page curve?
This one?
Yeah. So in the left-hand diagram, part of the entanglement entropy is inside the black hole, right?
Part of the entanglement entropy is inside the black hole. Yeah, we don't. Yes.
In the region that is below the squiggly line.
Here.
Yeah, here.
Yes.
So that remains inside the black hole. The part that escapes outside is the part that is responsible for the radiation entropy, right?
Yes.
So I don't understand how this pure state business is maintained, because
so you don't understand how what?
The pure state business, the pure state property,
yeah,
of the initial radiation state when the page curve is at the middle.
Yeah, right. The way the pure state is maintained is so you're as I increase time, as you say, these exterior modes enter these slices, these regions whose entropy I'm computing. So here, when the red mode is here, I have like log2 worth of entropy, and then I go to time t2, and then I have a green mode entering, so the entropy increases further. I go to time t3, this blue mode, I don't know if you can see it, but the blue mode enters, the entropy increases yet further, right? So the entropy is continuously increasing, but that's this green curve. When I apply the island formula, the entropy I need to compute is the entropy of I union R. Now, if I look at I union R, let's say at time t2, T2 has this region I, and this region I includes the green partner of the mode that is here. So now this green bell pair, it does not contribute to the entropy because both modes are in the region whose entropy I'm computing. Similarly with the red mode is here. And before, if I didn't include the island, it would add to the entropy. But now its partner mode is captured here on this T2 slice. So the inclusion of the island basically includes the interior partner modes in the computation, and therefore doesn't increase the entropy anymore as you evolve in time. And the area cost is kind of shrinking because this point is very close to the horizon, and the horizon is decreasing in time as the black hole evaporates. So both those effects lead to this decrease.
Okay, maybe we can talk about it after we have finished.
Sure. Yeah. I mean, I went through it very quickly. So if you haven't seen it before, I don't expect it to be clear. I was assuming that most people had seen this before, but we can talk later or offline about this.
Okay. Yeah. Sure.
Okay. So these are the three conditions, and I'm going to analyze these three conditions for various spacetimes with thermal matter. Of course, to apply these conditions, you need to make an assumption, or you need to assume something about what state your matter is in. So here I'm going to assume it's in a thermal state. So let's consider, first of all, an FRW spacetime. So I said I was going to talk about cosmology. Here's a non-accelerating FRW spacetime. It has a Big Bang singularity, okay? And in this case, I've only plotted conditions 1 and 3. So the Bekenstein violating condition puts you down here, okay? This is easy to understand. Basically, think about the regions kind of out here. So the constant time slices look like this. They go and hit, this R equals 0 point here. And when you have thermal matter, it's basically a volume law competing against an area law, right? Thermal matter's entropy scales like volume. So this is in, let's say, 3+1 dimensions. The thermal matter entropy scales like volume. So eventually it will beat this area law, right? Remember I said that the state in this universe is mixed, it's thermal. So as you take bigger and bigger region size, eventually you'll land out here, and then the volume will beat the area. So you'll be good, you'll satisfy that condition. That's one of the conditions you satisfy. But the problem is that the quantum normal condition for region I is totally disjoint. It's over here. The only place where these two conditions have overlap is close to the singularity where the computation breaks down. This doesn't even make sense. I mean, I plotted it because it's kind of interesting, but the computation breaks down here. So these regions have 0 overlap. So this space-time with thermal matter cannot host an island, regardless of what region you pick. You can purify this with another cosmology or a flat space, whatever you want, or even don't purify it. This space-time with this matter entropy cannot host an island, okay? One more thing I should emphasize is when I talk about hosting an island, I also need to specify what the kind of geometry of the island region I'm looking at is. And here for like an FRW spacetime, I'm taking, spherically symmetric, like balls in spacetime, just for simplicity. The conditions will change if you start messing with the regions in the geometry of the regions you're considering. But at least for those symmetric regions, you can't have an island. Okay.
So
yeah.
So that doesn't matter whether it's closed or open or radiation dominated or anything like that. All these different kinds of FRW.
Yeah, for FRW, I don't think it really matters. Of course, if you do closed, you can always hit this funny situation where you can include the whole universe at no cost. But I think for a closed FRW, that's the only type of island you'll have. You won't have sub-region. You'll either include the whole universe or none of it. Like that's the kind of trivial island. And that would, that of course kind of satisfies these conditions because the boundary of I is the empty set. So it doesn't even live anywhere to have to live in, the overlap of these regions. It's kind of like trivially satisfied.
I see.
But for a boundary of I that actually lives in the space-time, I think for closed or open or whatever, I think it would look like this. I'm not sure, but that would be my guess. We didn't compute that.
Okay, but for a closed universe, if we were living in one, then we could be living in an island.
Yeah, Yeah.
Okay. Thanks.
There's a closely related example. So this was FRW. You can do FRW, well, not FRW, but you can do matter with a positive CC. So at late, you start off with like a, it doesn't matter where you start off, it could be a Big Bang singulator, it could be something else, but you asymptote to de Sitter space because at late times the positive CC dominates. You can consider that case, and it looks similar. You again don't have an overlap between just conditions 1 and 3. You don't even need to impose condition 2. And condition 2 actually is usually the strongest condition. We'll see in a second. You don't even need to impose it. You see that you also can't have islands in this case. Okay. So, okay, that's a little depressing. So let's go to something a little bit more interesting. Let's consider a crunching universe. So something that expands and then kind of recollapses on itself. In this case, I've plotted all 3 conditions. Now the purple condition is the second one. So you can see what I was saying before about usually it's the strongest condition. It is strictly a subset of the other 2. Well, I guess not of the yellow one, but anyway, it's kind of the smallest region. And so this seems to allow the possibility of island regions whose endpoints live way out here, okay, in this kind of teardrop region. These were necessary conditions, so it doesn't mean that you have to have an island. But in any example we looked at, when all 3 necessary conditions were satisfied, we were able to find an example where the spacetime has an island. So it really did seem like they were also sufficient. And the example where you have an island now, of course, we need to now talk about a region R whose entropy we're computing. I was still considering thermal matter in this crunching cosmology. So we purify the thermal matter with matter and some auxiliary Minkowski spacetime. That you could have made this auxiliary spacetime FRW if you wanted, it doesn't matter. But it's non-gravitating. Okay, so we have a non-gravitating spacetime with matter in a thermal field double state with the matter in this crunching cosmology. Then if you compute the entropy of some spherical region R out to some point, then at least around t equals 0, this slice here, and kind of near there, up and down some amount, you find an island region that looks like this, whose endpoint goes out and lives in this purple teardrop. Okay, so this is the example that realizes an island, which is suggested by just looking at these necessary conditions. And why is this interesting? We'd just like to make a conceptual aside on these islands and what they mean. I said this a little bit in the black hole case, but I think it's a kind of powerful way to think about a sort of weaker but more general version of holography. It's weaker than holography because it doesn't say such and such system is dual to such and such other system, but it tells you how a state is encoded somewhere else. And it tells you that in a way which allows you to consider things that would have been difficult to consider before. For example, there had been some work on trying to understand holographic duals of crunching cosmologies, but nothing super precise, I think, came out of that work. But here, we're not answering the question, what is the holographic dual? But we are answering a weaker question, which is how is the information in this spacetime encoded somewhere else? And I find it remarkable that we can answer questions like that now using this kind of islandology. So that's what this line here is saying, that we encode, in some sense, holographically this Clapeyron cosmology somewhere else. Okay, any questions about this example? Okay, let's do another example. This will do kind of 2 things at once, cosmology and black holes. You can ask, what about the original black hole case? If I said there's an island there, are these 3 necessary conditions satisfied? Of course, the answer is yes, because they're necessary conditions. They have to be satisfied in the ordinary evaporating black hole. Let's consider a close cousin of that case. So here I have 2-dimensional de Sitter space in JT gravity. Okay. Now 2D de Sitter space is a 2x1 rectangle. And because you can kind of unfold it, the S0 is 2 points. Now, in JT gravity, you have a dilaton, and what it does in one of the solutions is that it goes to plus infinity here and here, at past and future infinity here. And here where these squiggles are, it goes to minus infinity. So these are like singularities. So this part you should think of as inflating, because the dilettante is supposed to like capture the size of the transverse sphere in a higher dimensional description. And here you should think about it as crunching. Why does it look like this? Well, you could think about JT gravity with positive CC, just like you do JT gravity with a negative CC. There we think about it as the kind of dimensional reduction of like extremal black holes in higher dimensions. The same is true here. In higher dimensional de Sitter, you have something like extremal black holes. They're when a Schwarzschild black hole grows and becomes basically as big as a cosmic horizon, and those two horizons coalesce. Okay, that's something called the Nari limit. And if you dimensionally, so the Schwarzschild de Sitter Penrose diagram actually looks just like this. You have an inflating region and you have a crunching region. This is where the black hole is. If you remember from your GR 101, this has this crazy maximal analytic extension, which has an infinite number of inflating and crunching regions, but we just cut those off because you can consider them, and the story gets a lot more complicated there. But you're allowed to cut them off and just consider this part of space-time. So all this is a dimensional reduction of that Schwarzschild de Sitter space-time. That's why it has a crunching region and an inflating region. And therefore, the physical interpretation is that the crunching region is the black hole and the inflating region is the de Sitter space.
This diagram is like the Penrose diagram of a charged black hole which is turned on a sideways, two-dimensional AdS kind of black hole which is turned sideways.
Yeah, it does look like it.
Because of this two-dimension, because in DS and AdS there's not much distinction. If you change the overall signature, AdS2 becomes DS2.
Yeah, I mean, it would look, Schwarzschild de Sitter would still look like this in higher dimensions, but you are right that this looks like that diagram on its side. And similar to that diagram, you can kind of if you maximally analytically extend this one, it goes off infinitely long, just like the diagram you're talking about. That's right.
Comment which reminded me that maybe this is something, maybe.
Yeah. So that's why I said this is, sorry, did you have another?
No, I said sorry about the interruptions.
Oh, no, it's fine. This is why I was saying that this is kind of like a hybrid cosmology example and black hole example, because this region is a black hole, and we can now compute and plot these necessary conditions and see what their overlap is. And we indeed find that there's some small overlap way out here. Okay. And here I'm considering the Hartle-Hawking state. So I'm not considering a mixed state anymore. The global state on this entire slice is pure. Okay. So we have some overlap. There can be an island. Lo and behold, if you compute the entropy of some region R, like here, you have an island that whose endpoint lives in that tiny little sliver. And this is exactly kind of what the overlap looks like if you just did these conditions for an ordinary black hole. Okay. Let me emphasize this example again was two-dimensional. We expect the same thing is true in higher dimensions. The interesting thing about these examples was that they're higher dimensional. And they're another way to see why these conditions are very powerful, because it's generally very hard to compute entropies in higher dimensions, especially to have such exquisite control over them that you can extremize them and minimize them and things like that. So, the existence of islands in higher dimensions has been shown in very few cases. In some cases, it was numerically, other cases, you need a doubly holographic description. This is one case where, because the matter entropy was thermal, we actually had control over the computation and could explicitly show that there is an island. But since these computations are hard, we have a finite lifetime, these conditions are useful to tell you what to try to compute. If you plot them and you find a region, then you convince yourself, okay, it's worth me trying very hard to compute this entropy, because it seems like there's probably an island here. So yeah, I think it's exciting to apply these things to higher dimensions. Anyway, one simple generalization of this example here is this picture. Okay, what is this picture? This might fly by for people who aren't super familiar with it, but in the picture of eternal inflation or the multiverse, what we think is that you have some background de Sitter space, and as you evolve, you nucleate bubbles of various cosmological constants, positive, zero, negative, or whatever. And if you nucleate a bubble of negative cosmological constant, you'll end up crunching. any small perturbation to that leads to a late time crunch that looks like this. If you nucleate a bubble of positive cosmological constant, it'll probably decay further. If you have a landscape of all the options, it'll just kind of keep tunneling down the complicated potential that you have. And so unless you have something that is like a supersymmetric flat bubble, like this one that I've drawn here, that kind of bubble is stable, but almost everything else is going to crunch at late times. Okay, so this is not really a picture of the multiverse I have here. That picture has a bunch of hats everywhere and little singularities and looks really messy, but this is just a toy model of having a single stable hat surrounded by a crunching region. And what this orange dashed line represents is that this is just a toy model where I have two-dimensional de Sitter space and JT gravity everywhere outside of this orange line. So down and in here. And I glued it to flat space JT gravity in here. And you can do that. And then you can ask about the entropy of a region R up here. You imagine you're an observer who lives in this flat stable vacuum, and you go to late times and you measure the entropy here. The question is, does the radiation in your hat encode the rest of the universe or the rest of the multiverse? That's something that we would like to understand. For example, you know, the old ideas of black hole complementarity, which say that the interior of the black hole is encoded in the exterior, have become somewhat sharp with islands. And there are much vaguer versions of that idea called cosmological complementarity, which says that the stuff outside your observable horizon is encoded in your patch. And one would like to test that idea, again, with islands. This is not really a test of that idea because, as I explained before, this is really, again, like the black hole example. All you have outside of your observable horizon is a black hole. But this is just a suggestive picture which says that, which kind of presents a target. What we would like to do is see if you actually had a crazy multiverse out here of all sorts of stuff, would the entropy in your patch encode that stuff? Would there be an island that cuts across the rest of the multiverse? That is the thing that we would like to build towards. Again, this example doesn't show that, but it's just a kind of suggestive cartoon to get people interested in the question. Yeah, okay. That's, I think, all I was going to say about applying these necessary conditions in cosmology and various examples where you can find islands. Are there any questions? The next thing I'm going to talk about is just some comments about closed universes, which they might go by a little quick because there's a lot of background that I won't totally review, but I just wanted to make the comments. So any questions about this part of the talk? Okay, I'll keep going. Oh yeah,
Stupid question. So this yellow dotted line which you have, this is like some kind of domain wall, or can you, like, these have, so this is some matter, the yellow dotted line is the domain wall or something in this diagram?
Yeah, it turns out when you glue with the, I don't remember the details, but I think if you glue with the horizon like this, it's tensionless. So you can kind of glue smoothly. The junction conditions don't have a jump, and so you can glue smoothly onto the flat space JT gravity theory. That's my recollection. But more generally, yes, like when you have bubble nucleation, there will be some, you know, thing there that represents the bubble. And the main challenge, thanks for asking, because I didn't connect back to the multiverse picture. Here, again, in this computation, I took the Hartle-Hawking state on the global slice. But with bubble nucleation and everything, the state of matter and the entropy is kind of crazy. The main question is how to understand what the matter entropy looks like in that kind of a universe. And whether or not you have islands depends very sensitively on what the matter entropy is, of course. So that's one of the challenges in trying to turn this picture into something real. And in the real picture, indeed, you would have, these would be the bubble walls that are kind of going out effectively at the speed of light. And they're really there. They kind of crash into other bubbles and release energy, and they're real physical things. But in this example, it's just a smooth gluing with, I think, zero tension along the horizon.
Okay, thank you.
Yeah, thanks for the question. Okay, so I just want to make some comments about closed universes. This is something that Raghu Mahajan and I had been discussing for a while, because there's some various kind of confusing statements that are made in the literature and in, like, I don't know, just confusing statements. And so we just kind of wanted to understand them and hopefully clarify a little bit of what's going on. So there's this example in this paper by these authors, which says that you cannot entangle yourself with a closed universe. Okay, how does that argument go? It says, well, imagine you tried to do that. CU stands for closed universe. Aux just stands for some auxiliary system. And it says, imagine you prepared something like a bell pair with some qubit in the auxiliary universe and some qubit in the closed universe. And you took this bell pair here, and you wanted to compute the entropy of the auxiliary system. Okay. Well, if you did this with quantum mechanics 101, clearly the answer is log 2, right? It's a bell pair. But the island formula would say, wait a minute, if the closed universe is gravitating, I'm allowed to include islands. So let me include an island that contains the entire closed universe. Closed universes are funny because islands can exist in them without having an endpoint, right? So you pay no gravitational cost. It doesn't have an endpoint, so the extremality condition is trivially satisfied, right? There's no endpoint to vary. And you've now included the partner qubit in the I union R part of the island formula. So now the entropy is 0, right? So this was the argument by these authors, which said that if you look at the island formula, it says this strange thing. It says you can't entangle yourself with a closed universe. This was also implied by the picture of the black hole evaporation. At the end of a black hole evaporation, you can think about it as a closed universe that kind of split off space-time and had a bunch of interior Hawking modes there. And the entropy of all the stuff outside includes as an island this entire closed universe. Okay, so the entropy seems to be 0. And people have taken that to suggest that the Hilbert space of closed universes is one-dimensional. The reason they have taken this computation to suggest that is that if you can't entangle yourself, no matter how hard you try, with the closed universe, it must mean that there are no states there to entangle yourself with. So therefore, it must be one-dimensional. That was an argument made kind of by various people, but that argument is wrong. It's simple to understand. I'm just going to do the same computation. Let's assume you did have a non-trivial Hilbert space in the closed universe. Okay, 10 states, 15 states, infinite number of states. And there are examples of this where we do have such a thing. One simple example is 2D topological gravity with end-of-the-world brains. This was studied by Mroff and Maxfield. Okay, in that model, there are these particular states in the closed universe. You don't really need to know what they are, but I picked these ones because they're kind of closest to representing a qubit. This psi1 state is like the degree of freedom on the end-of-the-world brane. So psi1 and psi2 are kind of like 2 states of a qubit you might have. And these things are orthogonal to one another. You have a Hilbert space. These things form part of the basis of that Hilbert space. They're orthogonal. And if they're orthogonal, then the computation which gives you log 2 is the correct computation. The undergrad quantum mechanics 101 is the right answer. Okay, there's no room for island formula magic or whatever. You just do quantum mechanics on this state and you get log 2. And the answer is not given by the island formula. Okay, you can also do this with like gravitational path integrals, right? You might worry, oh, what if I did the gravitational path integrals and I saw a replica wormhole and that reduced it? You can do gravitational path integrals to this state. You'll again get log 2. That's because the gravitational path integrals are totally consistent with the quantum mechanics, which gives you log 2, as it has to be. Okay. So there you go. You can entangle yourself with this closed universe. One important thing to keep in mind, though, is when we entangle ourselves, we're sort of using the ensemble degrees of freedom in this Euclidean gravity picture of closed universes and Hilbert spaces on closed universes. Every unique state on the closed universe is effectively in one-to-one correspondence with a member of the ensemble in the dual description. So, examples of this to think of are like either the SYK theory. That thing is an ensemble of theories, and we believe therefore will be dual to a bulk with a non-trivial closed universe Hilbert space. Or recently this Noreen ensemble that's been studied. JT gravity is not a great example because it's a two-dimensional bulk and it's dual, quote unquote, to a 0 + 0 dimensional boundary theory. So it doesn't quite fit this Maxfield formalism. But in any case, in this formalism, which is really just an AdS version of the Coleman-Giddings-Strominger formalism. So if you're familiar with that, this is the very similar thing. It says that the non-trivial states of the Hilbert space of closed universe are in one-to-one correspondence with members of the ensemble, okay, in the dual description. Okay, so in ensemble language, what's going on here? Well, what's going on is in ensemble language, you can compute two things a priori. You could compute the average of the entropy, or you could compute the entropy of the average state, okay? Now, the average of the entropy is often is what's computed by the island formula, and that's equal to 0, okay? But the entropy of the average state is the thing that's computed without islands or anything like that, and that's the thing that gives you log 2. Now, you can say, whoa, what's going on here? I had no averages, no ensembles. I just had a state and I computed its entropy. But remember, I said that the closed universe Hilbert space is basically like the ensemble. So what this would mean, the entropy, the average of the entropy would mean I fix to a member of the ensemble, I compute its entropy, and then I average it over all possible choices. Okay, here I have two members of the ensemble, 0 and 1, because the closed universe is just the ensemble. So if I fix to the 0 member of the ensemble, that's the 0, 0 state. That clearly has 0 entropy. If I fix to the 1 member of the ensemble, that's this 1, 1 state. That clearly has 0 entropy. If I took their average, I would get 0 entropy. Okay, but if I did the entropy of the average state, that's like considering the members of the ensemble all at once. That's considering this whole state at once, and that's the thing that gives you log 2. Okay, I apologize. I know that if you haven't thought about these things, it sounds like I'm just kind of running around in circles, but this is actually kind of an important point. And Raghu and I were confused again about various things statements that were made in the literature, so we had to kind of go through this somewhat carefully. But in any case, hopefully it's clear that you can have a Hilbert space of closed universes and set up some entanglement. I'd like to present a different perspective, which is closely related, which kind of leverages the idea of ER equals EPR. So if entanglement is just wormholes, you might say, of course I could entangle myself with a closed universe. Let me just attach some wormholes. There we go, I'm entangled, okay? I'd like to point out, again, also something that is not, I think, carefully spoken about in this subject. This doesn't really work, okay? The way you can see why this doesn't work is pretty simple. Here I just drew the picture again. Let's say I wanted to compute the entropy of all three. So I should say what these are. You could think of these as black holes that are entangled with auxiliary black holes here, like in thermal field double type states, or you could think of them as like a quantum wormhole of just like a bell pair or something. It's just kind of a cartoon in this part of the talk, but it just represents some entanglement supposedly. And let's say you wanted to compute the entropy of all three of these black holes or three of these qubits, whatever they may be. And now we want to use the island formula, okay? Well, what would it do? The island formula would tell you to extremize. So you can break this surface up into these three things, kind of cut across this bridge, rejoin here, and then it can shrink off the end of the universe. So when you extremize, this thing just wants to run off and shrink to 0 size, and you get 0 entropy. All this is a geometrization of the argument I was talking about in this paper. Okay, there you had like some quantum matter in a bell pair. Here, all I've done is geometrize that quantum matter and put like 3 copies of it. It's really the same thing, okay? But the thing I want to emphasize is, and people don't really emphasize this enough, I think, is that the correct slogan of ER equals EPR is really ER equals semi-classical EPR. So remember, something funny happened. I said entanglement is wormholes. Let me put in some wormholes. And then I went to compute the entanglement and I got 0. So clearly entanglement is not wormholes, because there you go, here's some wormholes. And the reason I put semi-classical EPR is because these wormholes represent semi-classical entanglement, meaning that's the thing you would get if you did not apply the island formula. Okay, if you computed the entropy of this thing, not applying the island formula, you would get an entropy. But the fine-grained entropy is not the same as wormholes. And this is actually the key to why you get the page curve and all these sorts of things. This distinction is very important. And I think the reason this subtlety has been a little confused in the literature is that we have this famous example of the thermal field double black hole, which informs our whole ER equals EPR picture. And there it is really fine-grained entropy. The entropy of one side is a finite amount, and you have the fine-grained entropy is the black hole entropy, and you have a wormhole. There, I would say it's actually a bit of an accident. There, it's because the semi-classical entanglement is the fine-grained entanglement. And so in that case, you can just say ER equals EPR without this modifier. But more generally, this is the correct version of the statement. Okay. An interesting point is that even if the dimension of the closed universe Hilbert space is 1, you can entangle subregions. If I took just 2 of these things and tried to compute the entropy, there's a topological restriction. Now it can't run off over here because of this guy. The best it can do is run around and come back to here and give you, log 2. And this picture of the one-dimensional Hilbert space is consistent with the topological picture of gravity. This is kind of what Chern-Simons theory is like. If you take Chern-Simons theory on a 2-sphere, on a spatial 2-sphere, the dimension of the Hilbert space is trivial, but it's believed that if you try and slice the sphere into subregions, then you'll have sort of non-trivial Hilbert spaces on the subregions due to edge modes and things like this. So that's possibly a good model for what happens in gravity. Gravity is a more serious version of this because any closed manifold you put it on, it has a one-dimension. Well, we believe any closed manifold, it'll have a one-dimensional Hilbert space. With Chern-Simons theory, it's only the 2-sphere. If you put it on a torus, it has a rich Hilbert space. It's just the Hilbert space of line operators. Okay, so you could still entangle subregions. Why is that? Well, topologically, you can just shrink this. Instead of thinking about this as some stuff that's entangled with a closed universe, just shrink this closed universe, then you see, oh, this is just some stuff entangled with itself. It's altogether a pure state. But if you take subregions, of course, you'll get some entanglement entropy, as is true in any pure state. Okay, so I want to say about closed universes, just a quick summary. So these consistency conditions for islands, I was trying to motivate they can help guide the search in general spacetimes, including cosmological spacetimes. And in greater than 2 dimensions, our tools are very limited, and it can give a route to some kind of weakened form of holography. And the one example we found that admitted islands was this recollapsing cosmology example. So the admitted islands seems to have some holographic encoding. So that is an interesting case to look at. Okay, I tried to motivate this kind of extreme idea. Is the multiverse encoded in our observable patch? Is that something that can be made precise? And the final thing is this, just wanted to carefully talk about the slogan that really it's ER equals semi-classical EPR. All right, I'll stop there and take any questions.
Do you mind if I show somebody?
Sorry? I'm in the middle of
Okay.
Not to they just look forward to reading his papers. Hopefully in the coming months, he will put out some of these last ideas. The floor is open for questions. Please go ahead. There won't be any discussion section after the next final talk because it's a bit late in India. So if you have questions, we can please go ahead.
So I have a question.
Yeah, please go ahead.
If you have an island, if you have an island in a black hole, will its effect be same will its effect be same on both sides of the wormhole?
If you have, if you have a collapsing black hole that's evaporating, there's only one side of that black hole. And so you can only see an effect on one side. If you're thinking about the eternal black hole, which has 2 sides, then to have an island in the interior, you need to have radiation from both sides. So both sides will be important to have an island. In the de Sitter example, it's sort of funny because both sides of the wormhole are the same region. That's just a funny thing of de Sitter space. Here's one side of the wormhole, the black hole, you go through, you come out here to the other side of the wormhole, but you're back in the same part of space-time. So here, this region is kind of both sides of the wormhole, but in the AdS or flat space examples of thermal field double, you really need access to both sides of the wormhole, which are kind of disconnected universes.
Okay, thank you.
Yeah.
I have a question too. What do you exactly mean by semi-classical EPR? What's like how to measure it as a notion of entanglement?
I mean, yeah. So I think you should tell me, but in the gravitational sense, what I mean is the semi-classical entropy, the thing we would measure without the island formula. So the Hawking entropy or whatever, it's the entropy on a fixed gravitational space-time. In like a tensor network type description, it's the legs sticking out, you know, it's that thing. It's not the actual full thing, it's the legs coming out of the tensor network. I think it probably has some fancy way to talk about it, which is the thing that you can explain to me in like error correcting codes or something. There's probably a way to speak about this, but it's a little funny because it feels like a fiction. It's not physical entanglement, but clearly it's very important because if it's the thing that becomes wormholes and does all this work, it has to have some fundamental meaning. So I think about it as the legs of the tensor network, the legs sticking out of the tensor network, for example, but there's probably more one could say about what this is.
I mean, yeah, in an error correction sense, I think, you know, you could say it's like the entanglement of the logical qubits rather than the physical ones, I guess. Like,
there we go. Yeah, that's the kind of words I'm looking for.
Thanks.
Yeah.
Okay.
I think my time's up, so should we move on to Hrant?
Yeah, I mean, Gwen, can you share your screen? Let's see if
I have to make him post.
Yeah.
Yeah, I think.
All right. Awesome. Yeah, let me try to share the screen. Here we go. Yeah. Slideshow. Okay, good. Can you guys see it like full screen? Everything is good?
Yes,
yeah,
yes.
awesome.
Can you move your cursor around a bit?
Oh yeah, for sure. Good. So thank you for this opportunity to give this talk, and thanks Edgar for a nice talk and discussion, and organizers for this workshop. So I will be talking about this paper with Adam Brown, Jeff Pennington, and Lenny Susskind from 2019, which addresses like geometric abstractions to the decoding Hawking radiation. It's a proposal for like geometric signature for a high complexity, and we call it Python's lunch. Hopefully by the end of the talk it'll be clear what we mean by it. And I'm a postdoc at Caltech at the moment. It's from Qubit postdoc with John Prescott's group. So going back to 2013, Harlow and Hayden argued in their paper, like quantum computation versus firewalls, that decoding information from Hawking radiation after a page time, when like the radiation is larger than the remaining black hole, in the late time, like more than half of the black hole has evaporated, presumably all the information about the black hole is encoded in the radiation. But they argue in this paper that the encoding is exponentially complex, and their argument like assumes like there's two important assumptions. One of them is that the Hawking radiation that got emitted was mixing like before being emitted with the remaining black hole. So in the process, like the first mode is mixing with a like large black hole coming out, and then continuously, and like there's like the remaining black hole is mixed with the emitted like early radiation that came out, and this seems like a fairly like reasonable assumption that the dynamics of the black hole will have such a behavior. And second assumption was that the complexity class reduction, essentially they argued that if you could do this decoding easily in a polynomial in entropy of the remaining black hole time, then it will lead to some complexity class reductions. Like Aronson actually like even clarified it even further in 2014 paper, arguing that if you could do this decoding polynomially, you could invert one-way functions, which is a computational like class reduction that is extremely highly unlikely to happen. So in a complexity theory sense, this is like in a level of a proof. That was like kind of the consensus 2013, 2014, that decoding Hawking radiation, if there is such a decoding, will be extremely complex. It'll be exponential in entropy of the black hole. So this was even further strengthened, this argument, by Kim, Tang, and Preskill's paper, where they actually illustrate that the Hawking radiation. So here we have some infalling matter that like evolves with some scrambling evolution, and then R is the early radiation that's like slightly more than a half of the black hole. Like B is the newest emitted mode of the Hawking radiation, and H is the remaining black hole degrees of freedom. And they argue that the radiation and the early radiation and the newly emitted radiation together are in a pseudo-random state. What pseudo-random means is that this state is indistinguishable from like a thermal state with the polynomial resources in the size of the entropy. So again, with the polynomial amount of computational power, you cannot really tell apart this radiation from a maximally mixed state. And they even further argued that with the polynomially bounded unitaries acting between observer and the early radiation, you cannot really disturb the correlations between the B and its pair like mode inside the black hole. So basically, like the encoding of the newly emitted B inside the black hole is really robust, and like with the polynomial operations, it cannot be perturbed. Again, suggesting that whatever this encoding is, it's not like simple. So it should be exponentially complex. Like parallel to this line of thinking that like decoding Hawking radiation should be exponentially complex, another line of thinking was about relationship of complexity and volume of the wormhole, and this was developed largely by Lenny, Adam, like Ying, Brian Swingle, and Roberts, and like several other collaborators. And the idea here is that suppose you have a state at of the thermofield double evolve for like T left and T right on the left and right sides. It's some quantum states on the field theory, conformal field theory, and the state keeps growing, and the extremal surface connecting these 2 points, which is in the blue, is the Einstein-Rosen bridge. And the Einstein-Rosen bridge continues growing until really late times. And there was a question, what is this Einstein-Rosen bridge length or volume dual to in the boundary? And the proposal or conjecture of Lenny collaborators is that this volume is actually dual to the complexity of the quantum states in the boundary. And later on, this was actually clarified a bit more, that it's not just the volume, but rather an action of the Willard-DeWitt patch that is dual to complexity. But for practical reasons, volume is good enough analogy to describe complexity. But what this suggests that complexity is dual to the volume. So at the early times when the volume of the wormholes is not large, like it's polynomial in the entropy, the complexity shouldn't be very big. And this,
Harant?
Yeah, for sure.
Can you just make a comment? What's the sort of thing that the volume proposal misses? Like, are there certain examples where it's just like totally wrong, or is it not known, or like?
Good. I mean, in the examples, there's one key thing missing, that complexity in the rigorous models is hard to compute. So there is only now recently that there's the random circuit calculations for like how complexity grows, and that indeed it's linear. Before that, it was largely like the boundary part was largely conjecture. Now it's becoming more in the level of the proof. And I think for chaotic systems, that's actually becoming more and more clear that that's going to be the right behavior. I don't think there's any like a model where like if you use like volume as a notion of complexity, it will lead to contradiction. I don't know if that's an example. Like, but I think that's something, because volumes are easy to compute. You could try looking for such an examples where like if the complexity behaved that way, they would lead to some kind of complexity class collapse or something. But I don't think there are such a so in the examples when like you can assume that, then it doesn't seem to be any contradiction. And now there's even like the boundary complexity computations coming to support this volume picture.
Got it.
At least
Thanks.
for this like linear growth until exponential times. I think this was like actually recent development for like a random circuits.
I'm sorry.
Yeah.
So if I remember the papers correctly, so the motivation for this volume proposal was that the volume can roughly, if you think about Swingel's, way of using tensor networks to model the AdS space itself. So this roughly the size of the tensor network is equal to the volume. And the volume is some kind of continuum version of the size of the tensor network. That I understand. There is a heuristic. I get the heuristic picture. But could you tell me what is the heuristic picture behind this action proposal? Like, why do we think? Is there some quick?
Yeah, I mean, it's beyond the scope of my planned discussion. But I think there are examples where if you just take the volume, there would be an issues. Like I think for charged black hole, like there's an issue to use the volume, but using the action actually resolves that.
I see. But from the tensor network or the other way, is there an intuitive way the action?
Good question. Yeah, I don't know of an intuitive way, but like in the tensor network story, right? You like take the extremal surface and like if you build it as a tensor network, it becomes the volume. And I think that's the right intuition in general. But I think if you use that for the case of the naively thinking is that like the things that like everything that it's kind of like instead of having one like a minimal like extremal like surface, the Cauchy slice that you try to build all of them. That's sort of like what it is. Like the Wheeler-DeWitt, like the action of the Wheeler-DeWitt is basically all possible tensor networks.
I see. Okay, thank you.
Yeah, like so you see, like you basically sum over all of them because sometimes like the prescription to pick the minimal is not the right one. Yeah, I think that's the naively.
Thank you.
What it is. Yeah. Okay. Good. But okay, to continue. So there is this apparent contradiction, which is going to turn out not to be a contradiction, is that like if you wait for a page time for a black hole to evaporate and collect the radiation more than half, you only like evolve for polynomial time in S, right? So the whatever volume there is or like action you will compute can like there's no reason it should be exponential. However, this complexity arguments and this mixing arguments from Harlow and then later on like strengthened by Preskill and collaborators suggest that like it should be exponential to decode Hawking radiation. So we were just confused about this like volume or like action notion of complexity, how this is comprehended with the exponential, that this polynomial can be comprehended with the exponential complexity that like this decoding arguments give. And the answer to it that these two actually measure different notions of complexity. So what specifically they measure is we call them restricted and unrestricted complexity. So suppose we start with the infinite temperature thermophile double state like psi AB. That's a tensor product of like n bell pairs. And then we act with a unitary UAB that's like can be built out of C gates, and C here would be unrestricted complexity, meaning that these gates can like act within system A, within system B, and cross from A to B, like couple things between A and B. So the unrestricted complexity of the UAB would be to basically use minimal, like what is the minimal number of gates like that go across A and B and stay within, and like that they can approximate very well your UAB. But there is another notion of complexity here. And because the state is maximally entangled, and assuming that the UAB is scrambling, some chaotic, like the technical term is like it needs to be a 2 design, basically it should be like mixing enough, then you can actually approximate UAB with only acting on the one side, because the final state is actually also maximally entangled in this case. So all of the dynamics that UAB does to go from psi to the final site, phi plus AB to the final state can be done by acting only on one side. And then you could ask, what is the complexity of if I am actually approximating my unitary only allowing actions on A? So this is restricted complexity where you only allow restricted gates acting on A, and this complexity will be different from the unrestricted complexity. And this is sort of the distinction between the complexity that measures, like measured by volume, that is the unrestricted complexity, and the complexity that's measured by decoding Hawking radiation, because decoding Hawking radiation implies that you only are allowed to act on the Hawking radiation rather than entire like system of radiation with a black hole. Good. So in like some kind of a tensor network pictorial way to see this is that you start with a bunch of bell pairs, and then you can reproduce the exact same states, either like with allowing like gates on the one side, restricted, or like allowing like gates to go across. And the counting number of these gates can be very different for generic like a unitary's UAB. So in the case of thermophile double, where we evolve it with the Hamiltonian that is not coupling left and right, these complexities agree with each other. And this has to do with the symmetry of the dynamics, and then and the fact that the evolution does not have any gates that couple left and right. So you can basically build the exact same dynamics either with the same exact number of gates, either by acting on both sides or acting on one side alone. So this was an easy case, and then unrestricted and restricted complexities of this state, this thermophile double state, are the same. Like evolved thermophile double state are the same. So when it gets different, so it is very different when you have a Hawking evolution, like a Hawking emission process. So suppose we have a black hole created by an infalling matter. So here's like the orange line is the infalling matter, and then there's a blue is the horizon, and red.
Sorry, Hrant, can I ask another question?
Yeah, for sure.
Just on the previous slide, I don't think I totally understood the statement. If I want to think about bulk reconstruction in the thermophile double, I of course would need both sides to reconstruct the entire bulk. And if I just have one side, I would only be able to reconstruct like, outside the horizon of one side of the thermophile double. But is the point that the complexity of doing the whole bulk with both systems is like the same as the complexity of doing half of the bulk with one system or something? Like, I don't understand this equality, I guess.
Good. Let me say this. So from the complexity point of view, if you like start with a thermophile double and time evolve it, right, with the left and right, then the complexity of the state is
both sides forward, right?
Exactly, both sides forward. Okay. That's this picture right on the left.
Yeah.
And the idea is that this complexity, because there's no coupling between left and the right in the evolution, there's no gates going across, is the same as doing operations on the one side alone. And this has to do with the fact that you have a maximally entangled state to start with. So like basically everything you can do in both, you can do in one alone. And the complexity of doing it would be the same. And this is kind of in agreement with this, like if you have a wormhole, like a wormhole, like ER bridge, and think about a tensor network, sort of like you can continue shrinking this tensor network basically from one side alone. And that has to do with this, like there are no bulges, but we're getting there, yeah.
Okay. But sorry, but just to make sure, this is talking about the complexity of reconstructing the entanglement wedge of both sides or just one side? Like, I agree with this picture. This is, as you said, this is saying that you can use the time isometry to like bring one side back to 0 and just evolve the other one. But when I talk about these complexities, it's about the complexity of reconstruction of the bulk, right?
So like we are actually like the more technical part we are doing is like constructing states from one side or the like from a fixed side. Reconstruction, it requires another level of, but I think like a lot of things you say about like building the states from the gates like can be translated to inserting operators and reconstructing them from the other side, but like mathematically is not exactly the same.
I understand. Thank you.
But there are like, I will mention a little bit in the end how this like a gap can be bridged, but you know the main like talk is mostly about like building the states and the complex like relative complexity of states.
Got it. Thanks.
All right, okay, let's go back to the forward actually to the infalling matter and like a black hole created from an infalling matter. And then there's radiation modes at each time step coming out, like the green lights and the one pair falls into the singularity, the other pair exits the black hole. And in this process, the dynamics actually of each of the emitted Hawking pairs will couple to the remaining black hole. So basically, like in the process of the like emitting this Hawking pairs, like there is a left and the right sides in this like naive pictures that I introduced with the tensor network will have like a coupling gates going across that will couple the emitted Hawking mode to the remaining black hole. So the question is, and this is why the reconstructing the state from the radiation alone will be exponentially hard. And the question we were set to ask, like from a circuit point of view, this seems like fairly straightforward that the restricted complexity can be hard in a certain instances because you're trying to like rebuild the couplings between left and right from one side alone using the entanglement structure of the initial state. But I think it wasn't clear to us what was about geometry that knows about this. Like, is there what feature of the geometry can tell you whether you can easily decompose like the state from a single side, like in the thermophile double, versus in a case of the Hawking radiation, you can't. And we wanted to find a signature in the geometry. And this signature in the geometry is what we call like a Python's lunch. So the basic idea, what you need to look for in the geometry to like find high complexity regions is that if you have like Python, which is like a smooth geometry, like in the wormhole, like ER bridge of the thermophile double, this is a low complexity to decode from one side. And then in the case of the Hawking radiation, we argue that you have what we like call a Python's lunch, meaning that there's like a fat bulge, a lunch inside the Python, and the geometry has this feature that like it starts with the minimum, max, and mean. So there's like this min, max, mean pattern in like a Cauchy slice. Like I'll talk about the details of how to find this feature in the Hawking radiation, what exactly are these surfaces in the upcoming slides, but that's the essential idea. And to actually explain why this means that like if you have this Python's lunch geometry, why you have a high complexity, I think will be the next few steps. And then we'll go back to the Hawking radiation and like explain how to find this Python's lunch in that case. So now let's go to the tensor network picture, assuming it's accurate description of geometry, or in certain instances, at least it approximates what's happening well. So suppose we have this bulge in the tensor network. So what we mean by it, let's see. Okay. So what we mean by it, we start with some like input state psi on the left side, and then we have some ancilla qubits being inserted at the 0 state, and these tensors act like as unitaries, but we have like we fixed one of the input ancilla states to be 0 in this edge, and then we're gonna post select on the output being in 0 stage later on. So how this tensor network will like kind of push the information through the network is following. So we start with the psi I, then we add, let's call ML, and is a number of the ancilla legs we include in our dynamics on the left side. Then we act with the unitary, overall unitary that characterizes the evolution of this tensor network. And then for the later, we'll assume that it's deep enough a network that it's scrambling. So each of the legs is like unitaries pushing information forward unitarily, and it's like mixing enough and long enough that it's scrambles the information. And then in the end of the day, we want to get the information out on a part of qubits more than what went in. So we have an isometry, so we don't have any loss of information from left to the right, but we do it by post-selecting on the on this qubits once it starts shrinking. And the number of the qubits we post-select on, we will label them with MR, like M right. And the final state will be again a pure state that will come out of the network. And as I said, the key assumption is that this tensor network is like sufficiently deep, but not too deep, meaning like it's polynomial in the number of qubits involved in the dynamics, the complexity of it. So the idea is, how do we go? So with this post-selection, if you allow post-selection, it seems that it requires only polynomial complexity circuit to get from psi in to psi out. But the question is, like, definition of complexity, restricted complexity, does not allow post-selection, because this is not something you can do in the physical systems. So the question is, how can you replace this post-selection that this tensor network is doing with the unitary evolution and still get the final state out? And we call this unitary that will like basically start with the initial state and end up with the final state, with having post-selected legs in zero state. And the question is, how can you build this UPL, like your Python's lunch, which is a unitary that essentially replaces the post-selection. So we want to go from a post-selection circuit to like a circuit that does not have a post-selection, and measure the complexity of the circuit. Good.
Sorry, Aaron, maybe you're about to say this, but I thought the post-selection represented the right part of the tensor network where you start losing what were originally the ancillary bits or whatever. But now if you don't post-select, you're saying you can still do that? You can still lose them?
Good. So no, you don't lose them. So if you don't post-select, like the question is, with the post-selection, I have a tensor network with polynomial length, right? And it takes me from psi in to psi out with a polynomial number of gates plus post-selection of MR legs.
Yeah.
The question is, can you get rid of this post-selection? Because it's not a physical concept. So it's not like if you want to basically like do operations from the right system alone, you are not allowed to like do post-selection. So you want to understand like how can you reproduce this tensor network that plus post-selection with some like some dynamics that only involves unitary operations. And the complexity of that dynamics will be the complexity required to actually do, like, this would be the complexity of like unrestricted, like a restricted complexity on the system.
But so the bulge is supposed to decrease again, even when you get rid of the post-selection, but find this unitary you're talking about, the PL one? Or I was just confused because in the picture you had the bulge decreasing, but you had gotten rid of the post-selection. That's what I was confused about.
Yes. I'm sorry. This is a pictorial thing. Like UPL is a circuit without the bulge.
Oh, okay.
The UPL does not have a bulge. It does not have a post-selection legs. It's only it's a unitary process. Yeah, I'm sorry. Yeah, I think like the thing that has a bulge has a small volume. UPL has a big volume. It's a much bigger network without a bulge.
Okay.
And the question, the complexity, like the complexity of that network, or like number of legs in that network, is actually what is the restricted complexity. if you want to do it unitarily without post-selection.
Great, thanks.
Good. So and how do we? So one way to like give an intuition about like how can you get rid of post-selection or like measure a complexity of doing a post-selection, you can actually just run your like circuit, like initial circuit that's like polynomial complexity, then measure the post-selection legs, and then if you find all 0 state, you are like, oh great, I got my final state. That's right. But the probability for like if your U is mixing enough, the probability of hitting the right bit string is exponentially small. So it's 2 to the minus MR. So to actually like hit the jackpot, you have to keep trying it until you get the right state out. This is basically like doing post-selection kind of like naively by just trying all different measurements. And with only assuming that the unitary is scrambling, this would be exponential like prefactor on top of what it takes to run the circuit. So it'll be like the complexity of the circuit times 2 to the MR, which is like the probability of hitting the right bit string. And the problem with this is, first of all, it's non-unitary, requires measurements, and you have to keep rerunning the same circuit. So instead of this, there's a better way to do it for getting like rid of post-selection, and that's like using some kind of a generalized Grover search algorithm, where we are searching for the post-selected like state in the qubits that will eventually lead to the final state we want on our like output qubits on the network. And the procedure for doing it is the following. So suppose we start with some input state phi, and then we act with a small like polynomialist big like tensor network unitary UTN, and then we want to post select on the MR number of qubits to be in 0, and the way to do it using a Grover search is to construct U phi that's that's a unitary that flips the sign of all the orthogonal states to phi except phi. So it's like flips the sign for everything, all the other orthogonal states to phi, but keeps the sign of the phi the same. And then we do the same, and then we construct V, which is the same trick on the post-selected legs. We do the same with the swap on every, like flip the sign for everything except the MR. And then we actually like sandwich it with our like a unitary, like, and apply U and U dagger. It turns out if you construct such a like U phi V unitary, and then keep repeating this, you will keep approaching the desired state like unitarily. Like and it will require only like square root of 2 to the MR number of repetitions to hit the final state. Good. So the unitary that the UPL that gets rid of the post-selection, that's actually a circuit without any post-selection in it, will be given by UTN times this like L time repetition. And then with L, you keep converging better and better to the final output. But the idea is that you only need square root of 2 to the MR repetitions to converge really well. And this is actually an algorithm that Yoshida and Kitaev used for their 2017 paper for like decoding Hawking radiation, like where they essentially like replaced post-selection with a unitary evolution. And but there is one problem with this. Like this problem will actually like this algorithm works only for fixed input state phi. So the way you construct this unitary depends on what your input state was. Otherwise, it wouldn't work. And that's actually a bad thing if you're trying to reconstruct like operators in the interior, like, because then you're in the interior of your tensor network, because it will like reconstruction will be different for a different different input states. And you want to have a reconstruction of like from tensor network that has a bulge to a tensor network that does not have a bulge, that is independent of phi. And there is a way to do that. And so the way you do it, like it's this is also an approximate, but you actually have to have an ancilla qubit in a fixed state in input. It's kind of like the other end of the bulge also has to be small. And actually it has to be smaller than the psi in number of qubits in psi in has to be smaller than the number of qubits in psi out. And again, you play the same game, like you flip the signs for everything in your ancilla now, like flip the sign of all the orthogonal states except the post-selected state you want to, and then also sandwich with the unitary of the tensor network. And then the unitary like that you will need that will approximate well this like post-selection dynamics will be like L repetitions of this sequence UV, which will be independent of psi in. And the tricky part was to show that if your MR is smaller than ML, meaning that you put in more ancilla legs than the output legs, then the whole like in and out is an isometry. Then you can like actually map this like bulge tensor network to unitary one with a high accuracy with only like L repetitions, and the complexity of doing this would be square root of 2 to the MR times the initial complexity of your network. So basically there's like this exponential enhancement coming from how much post-selection you need to do. There's a technical term for this called like amplitude amplification, actually oblivious amplitude amplification, which is like independent of the input state. It can still like amplify certain like choice, like certain choice of a vector. Yeah, like Barry et al. And Gillian this like has studied this in detail, and there's a technical like like the term for this called like block encoding, where you amplify a block of your unitary and like turn it into a unitary itself. And yeah, this turns out to give you like a measure of complexity and a way to like map a tensor network with a bulge to one without a bulge. Good. So I think one important question is like, okay, we got an estimate. We have this procedure. We have an estimate for complexity. Is it an optimal one, or there's like a better way to do it? And there is no mathematical proof that this is the optimal way to do it, and this is like the minimal complexity. In fact, if your unitary has certain structure or a symmetry, there might be shortcuts. There might be ways to do it even better than this, like oblivious amplitude amplification. And but with a certain assumptions, it is the optimal one, and the assumption that like your tensor network should be scrambling enough, meaning that it's to design or has a certain like is built some certain like circuit with the scrambling enough unitaries. Then with this assumption, it's highly unlikely there would be a shortcut, because if there was a shortcut, it would lead to this collapse of a PP class to the BQP, where like PP stands for probabilistic polynomial, which is a very large class. It contains MP, and it's also equal to post BQP, which is like a quantum computers plus post selection. And this is highly unlikely to happen because it will lead to some like really massive complexity class collapses. So with this assumption of the unitary being like sufficiently chaotic, or like the tensor network being sufficiently like mixing, it's unlikely it's highly unlikely there would be any shortcuts. So this estimate for the complexity will be optimal one. Good. So okay, so I gave this prescription, and now we want to have like kind of more rigorous way to like finding this how many legs you post select on. In this tensor network I gave, it was kind of clear, like from like just the way we construct it, how like we do the like what are the ancilla input and what are the post selection outputs. But in the general, it might not be so easy. So we needed to give a prescription how to find like the number of post-selected legs that in your geometry, as well as like in a tensor network. And the prescription is like minimax, meaning that you basically start, okay. So finding the minimal surfaces, that's easy. That has been like you know, like finding the minimal cut has been explored a lot in the starting from Ryu Takanagi later, like for tensor networks, like minimal cuts. So the two minimas are fairly like standard to find. What was like a new thing was this, like the bulge size. The size of the bulge was a tricky thing to like describe accurately. And our proposal is to basically look at all different like possible slicings of your tensor network, or later like your Cauchy slice, and then find the maximal slice, and then you minimize over all possible slicings. So you have like various slicings that can like go from left to the right, and then for each slicing you have the max, and then you find the minimum of these maxes. So this is like a minimax prescription for finding the minimal number. And in this network, obviously, this is like pretty straightforward. That would be like whatever slicing you choose, you know, there'll be like many different maxes, and the minimal one is like this n max that will just cut the network across. And the conjecture for like general tensor networks that we have is that the complexity of the restricted complexity will be given by the size of the network times the exponential of the difference of this n max that we defined with this minimax prescription minus the largest minimum size. Good. So this is like a way to find in the tensor network to find this the size of the bulge. So what about the gravity? So
sorry, can you say where the minimization in time part happened? Why was that?
Oh no, it's not in time. So this is assuming for like, I'm gonna get to the Hawking radiation soon, but this is assuming you have this like nice slice. So you have some you know, like tensor network description, or you have some geometry. Then what you do, like you can find the minimus on this Cauchy slice using like standard prescription of finding the minimal cuts, right? But the maximum is hard to find because, you know, there might be like so the way you do it, you like have different like slicings. For each slicing, there's a maximal slice, right? And then you minimize over those. So sort of like, you know, imagine like one slicing goes like this at the angle, and then you pick the maximum of this, and then you have another slicing going the other way. So the minimal like of the maximums will be the max.
Okay, maybe I'll wait for the way you're about saying gravity, and then I can maybe ask again.
Yeah. I mean, it's kind of an important point. Like, so the max is like, you start with a slicing of your network or the geometry from like left to the right, right? Like you have two lengths, and then from like.
So when you say slicing, do I keep fixed the boundary endpoints, let's say in AdS, and then I consider different Cauchy slices that connect the same fixed points?
Not yet. No.
Oh,
so you pick a Cauchy slice. This is a prescription for a chosen nice Cauchy slice. Like I will talk about how you go about like changing the Cauchy slice to have a covariant version of this. But for now, if you have a fixed Cauchy slice, you want to find the max on this one. You do it by like having like, you have two means that you found, right, on this specific Cauchy slice. Now you slice from one mean to the other, like you have different slicing, right? Like where you can like basically move from left to the right. And for each slicing, there's a maximal part. So you minimize over the slicing, the maximum of each of the slicing. So that's why we call it like minimax. So you basically like slice from left to the right between the two minimums. And for each different ways you can go from left to the right, there's a maximal one. And you minimize over this maximal ones. Okay. Yeah, maybe when we add the changing Cauchy slices might be simpler, but like I think in the tensor network, I should have drawn on top of this, but you could imagine, you know, from going left to the right, you can slice it this way, like at the angle, right? And this would have some maximal slicing guy. And then you can slice it the other way. Like you have all this.
Yeah, I guess from the gravity picture, this is just to keep some runaway from happening, because you can always like, there's a point you can always angle your slice in a really funny way and keep increasing the area. And so this minimization is kind of necessary to like actually land on something.
Exactly. Like, because you can't just keep like changing your slicing and like make the surface big, but no, you want the minimum of this like maximal cuttings. Yeah.
Right. Okay. Thanks.
I mean, that's at least what we propose, and that's the right answer for the tensor network. You know, you can have like all different maximas, like cutting at the angle, but like really the one that matters is the minimal of these maximums.
Right. Okay.
Good. All right. So in the gravity sense, what we are arguing is that if you just think about the geometrized version of the wormhole, like there's a subtlety with the adding, like, you know, geometrical plus the bulk entanglement, like in reality, like for the whole evaporating black hole, it should be like generalized entropy rather than geometry alone. But the naively is like the difference between the something that has high restricted complexity, such as like a evaporating black hole, and something that has low restricted complexity, polynomial in entropy, like thermophile double. Like the difference between these two will be that the second one, the hard one, has a like min max min pattern of the generalized entropy or the area in cases when there is no like bulk entanglement. But basically, like Python's lunge is a feature you need to look for to have a high complexity of decoding of the region. All right, so let's now let me try to explain why there's a Python's lunge with the remaining time. Hopefully I'll make it explain why there's a Python's lunge in the Hawking radiation. So in the Hawking radiation story, so we have like a wormhole. This is like a nice Cauchy slice, and then like individual like Hawking modes keep coming out, like first mode, second mode, third mode, and then we collect those in some like a quantum radiation system. And you know, this process and the wormholes, like remaining black holes, like area keeps shrinking. This is kind of pictorial of like what's happening. And like more precisely in terms of like the diagrammatic way to think about it is like this nice slice that I have been like drawing here is essentially this like dashed line where like you have Hawking modes living here at like the line like the going across this slice like characterizes different time steps where like Hawking modes came out. And then like A0 is the size of the initial black hole. That's like the fattest part here. And then it like shrinks off, the wormhole shrinks off. And then this is the area of the remaining black hole, which is like a smaller than the initial one. So basically this is like this kind of a Penrose diagram description of this nice slice. And then for this nice slice, we can play the same game as for the tensor networks. You can compute the minimal generalized entropies, and those would be two different cuts. One would be the S radiation, the cut that like cuts the radiation degrees of freedom. The other one would be the cut that cuts the remaining black hole area. And then the question would be where is this max and how to find it. And the transition point where the radiation gets more than the remaining area is like known as a page time. And the precise definition of it is that the entropy of radiation at this point equals, like after this point equals like the entropy coming from the area of the black hole B. So this is the page transition. Basically, this is when before this time, the black hole side was the largest subsystem. After this time, radiation becomes the largest subsystem. And now about the so the covariant version of like finding the surfaces where like you don't want to like worry about the definition of this nice slice was described by Engelhardt and Wall, and then later on like clarified in this 2019 paper by like authors introduced this maxi-min prescription to finding this minimas. And the idea is you like look for generalized entropy, you look at all Cauchy slices, and then find the minimal cuts for each of them, like this minima 1, minima 2 for each of the Cauchy slices, and then maximize over all of them. So this is like a precise way to find the min 1 and min 2. like you go through all Cauchy slices. This is like a covariant way to do it without like looking at this nice slice. But if you can find this nice slice, then you can like think about it as this like very analogous to the tensor network, and like means are more precisely defined. So this is like the using the maximin to find the minimas. And then now what we do with the finding the maximal cut, the sort of the bulge, like how would one go about like finding it like covariantly? So before going to the covariant version, like let's suppose we have like this nice slice that I described. And in this nice slice, like basically we know how to find the two minimas pretty clearly. Then we do the same thing as for the tensor network. We go from the left to the right, or like from radiation to the black hole. And like we have all different slicings of like cutting the systems. And actually two key differences, there's two different slicing. One is like a forward when we go from radiation to the black hole. The other one is the backward. And they will have different contributions. Like here, for example, we will have the cutting radiation and then area piece, and then continuously going forward. And the maximal cut will actually be this guy, where you have the radiation plus the area of the initial black hole, like cutting this tip. And that would be like sort of the maximal generalized entropy point. However, there would be another important slicing that will come from the radiation point of view, where we like cut with the maximal would be cutting this endpoint 2 times, sort of like start with the radiation and then cut this last leg, and then you have 2 horizon, like remaining horizon area contributions and the radiation cut. This we call this like reverse slicing. And essentially, like you want to, as I said, you want to minimize over this maximums. So you pick the minimum of this maximal like cuts, and this minimums, whether it comes from a reverse slicing or the forward slicing, will switch at the halftime. So basically, your like maximum surface will switch at the halftime, where halftime is like when the remaining area is equal to the half of the initial area of the black hole. All right, so we have this maxi-mini-max proposal for finding the surface covariantly, which is essentially doing like searching over all different Cauchy slices. So we like for each Cauchy slice, we use maximin, and then we minimize over all the Cauchy slices. And like we don't have a proof that this is exactly the right way to do it, but it seems pretty natural, like generalization to the to this like from a like covariant prescription of the finding the minimas to finding the maximal cut. And in for the case of JT gravity with the non-interacting fermions, we're actually able to like find this exactly like this maximal cut, exactly this like fetish bulge part, exactly by using this maxi-mini-max approach. And this essentially like leads us to go forward and make a conjecture about the complexity of decoding the Hawking radiation. And either from the Hawking radiation or in the beginning before page time from the like a black hole side, but after page time, if we want to decode everything from the Hawking radiation, the proposal is that the conjecture is that the complexity of this decoding, the restricted complexity, will be the volume contribution, like I call it CTN, but it's essentially the volume of the of this nice slice, nice Cauchy slice, and enhanced by the exponential factor that comes from this difference between the maximal cut and the largest minimal. And after page time, the largest minimal will be simply the radiation entropy, which we find it by the maximin prescription. And then we find this maximal cut with the maxi-mini-max prescription. So the idea is there's like exponential enhancement if the difference between this, like the bulge of the black hole and the minimal area, like get larger, you will have this like large factor in terms of like complexity of decoding your radiation. So here I'm just plotting the the logarithm of the restricted complexity and how it would grow, like for this JT gravity with the non-interacting fermions with time, and then indeed like after, like it grows exponentially, and then after page time it like grows linearly in this region. It's like not really clear. It's like the log of the complexity, and then it starts decaying after that. As more like modes come out and it purifies. So there's a region of like a high exponential complexity for decoding information from the Hawking radiation. Good. So this was the presence of Python's lunch that has like a bulk entanglement and the gravitational like contribution, like area contribution, as well as like a bulk entanglement contribution to the generalized entropy. However, there are, I think, like Python's lunges in like purely geometric setups. Like if you have a pure state black hole that is evolving, and then you ask whether like if you divide it into like left and right subsystems, like I call it A and A bar, I think there would be also like a bulge in this scenario as well. And you know, there's two minimal surfaces going like left of the right of the black hole, and then if you use the prescription that I described with this minimax, like with the for the slicings from left side to the right side, then indeed you will discover a bulge. And I think that'll be interesting to like investigate this a bit more, like what it tells about the complexity of like reconstructing operators in the interior from the only like one half of the boundary, like half of the boundary. And like if this wormhole is like sufficiently long, like longer the scrambling time, the probably like is likely this would be exponentially hard to reconstruct. Like another example like that, there is like a geometric bulge is like for the like empty AdS actually, with the where we choose a system to be two like darker, like more bold lines, and then we'll have two minimal cuts, in this case like the orange and the blue, and then you can actually move from one to the other with this like slicings, and then find the maximal cut. And like this also tells you about like the complexity of like the reconstructing operators in the interior part from like sub-regions of the bulk. And here I doubt there will be exponential complexity because the network is not like deep enough, not scrambling enough. But yeah, I think it's also an interesting direction to look into this model. Like another actually interesting result from Engelhardt and Pennington and Shabazi Mogadan that recently came out, it was sort of like a claim for the converse of the proving the converse of the Python's lunge. And in their paper, like, you know, conjecture of Python's lunge says everything in the lunge is difficult between X mean and like second X mean is like hard to construct if the bulge is big enough. So what they actually argue that, so suppose like C here is like a causal wedge, like the WC is a causal wedge. So everything in this wedge can be easily reconstructed using HKLL. And then the question was whether everything from between X and C can also be easily reconstructed. And what's the problem if you try to cross X? And they actually have this nice construction, like using like certain like perturbations of in the boundary that can push the causal wedge to all the way to the X. So basically, and then use the HKLL on this like a perturbed boundary. So basically, it's like it gives a precise way to reconstruct everything between X and C. But this approach like completely fails once you reach X. So sort of like this method like pushes the causal wedge forward all the way to X, and then breaks down once you like try to go into the lunge, which is like another illustration that like the lunge region must be quite hard to like reconstruct from the boundary point of view. Good. All right. I think just to give a quick summary, and then maybe we can spend a bit time to discuss. So what we have here is just this conjecture that if you have a Python's lunge in your geometry, that is defined with this existence of this like maximal cut and 2 minimal cuts, like min, max, min pattern, and the difference is significant, meaning that it probably scales with the entropy of your system. Then the complexity of decoding would be the volume that is like unrestricted complexity enhanced by the exponent of this like difference of the entropies. And this would, like from a tensor network point of view, this comes from the fact that you have this like when you shrink your network, you have this post selection, and doing the post selection from the one side is extremely difficult. And extremely is like exponential in number of the legs you post select on. So I think there's interesting future directions here, like one, like going beyond the tensor network formalism to like prove this about complexity. And I don't really know, like there's this new notions of complexity for field theories, and perhaps one of them can actually be useful in like trying to prove this like high complexity in the Python's lunge, like beyond the tensor network model that we have. Second is, like I mentioned, a couple examples of the Python's lunge geometries that appear in like purely geometric setup or geometry with the bulk entanglement. I think like just looking at more examples, or like even pure AdS, I think it will be worthwhile to investigate those geometries and what Python's lunge mean in those contexts. And another interesting, whether there's a connection between this Python's lunge geometry and like a extended quantum Church-Turing thesis. This is this paper by Vazirani and Bulan that they have this like interesting constructions where like multiple shock insertions into the black hole. That there seems to be like they argue that this gives you exponential complexity of the boundary to the bulk mapping. And I think it'll be worthwhile to investigate whether there is a notion of Python's lunge in their setup as well. I think there is, but I think it has to be even looked in more detail to establish a better connection.
I'm sorry, I couldn't hear you clearly. Which paper are you referring to right now?
This is Vazirani Bulan paper, where they have like this multiple shock insertions into the like thermophile double, and then they argue that this is something that like how many shocks you inserted, which determines the length of the wormhole. The boundary, like bulk observer inside the black hole can easily tell apart, but the boundary observer can't because it's pseudo-random. So this also uses this notion of pseudo-randomness to argue that like it's polynomially impossible to tell apart. So that it's something that inside a black hole is easy to do, something is provably hard in the boundary. So the map from in and out, inside to the outside should be hard. And I think that they basically use it as a way to like say that the dictionary should be exponentially complex. But I think their dictionary is exponentially complex because the state they reconstruct with these multiple shocks has some form of Python's lunge. I mean, I kind of have an idea how this should be found, this Python's lunge, but making it rigorous, I think, will be also like a worthwhile investigation. Yeah. Yep. Yeah, I think that's about it for me. So thank you.
Okay, thanks, Ram, for a very beautiful talk. The floor is open for questions. People, if you have questions, please go ahead. Unmute yourself.
Question.
Yeah.
Does the min-max cutting surface depend on any island geometries if it's there?
So good question. I think like the Python's lunge and islands in this example, like at least in the Hawking radiation case, seems to be the same. Like you know, except we have this like a maxi mini max way to like find the maximum cut. In the island case, I don't think there's any interest to find this. Like they just are interested in this like a region that's encoded in the boundary. But in general, I'm not sure there's like a you know duality between the two, and yeah, but definitely like it's a very close to the island, like finding the islands. Yep.
Oh, thank you, sir.
Aaron, can I ask you about the covariant statement of these surfaces? So Let's say I'm doing AdS CFT. I pick my, let's say I have one boundary, two boundaries, whatever. I pick a boundary time slice. And now I want to search for the, let's say the actual minimal surface with this boundary time slice. Then for some region, let's say, then I do the maximum prescription, and that will pick up for me both a Cauchy slice and the minimal surface on that slice.
Exactly.
But now if I maxi-min with the rule that on every Cauchy slice, I'm looking for the second minimal surface. Can't that land on a different Cauchy slice than my first one did?
Yeah,
like,
it
there's
can.
no guarantee it's the same Cauchy slice. So in the end, I was confused exactly which Cauchy slice you were on.
No, that's right. I think it can land on in general, and I think what we're saying that like in the formula, like you only care about the large one for reconstruction. So I mean, even like the maximal one might land in a different Cauchy slice than your.
Yeah, but before we even get into the maximal one, the two minimal ones can be on different ones. So what slice were you talking about? I got a little lost there.
Yeah. So in terms of in the case of radiation, right? I think actually you will land in the same Cauchy slice in this Hawking radiation picture, right? When you like find the generalized like two means for the radiation as well as the black hole, you will actually you can find this nice Cauchy slice where both of this live in.
Yeah, that's well, I guess one of the surfaces is trivial, so maybe in that case it's I guess a little easy.
Yeah. In general, I think that you can still have a conjecture even though they are living in different, like you can have covariant version of the conjecture that like they live in a different like Cauchy slices, right? But I mean, in this evaporating black hole, we're kind of lucky. There is a nice slice that like all the surfaces live on. But in general, I don't want to make any claims whether like, like my understanding is this tensor network picture breaks down, like you could have this proposal for like using the min-max, but since they're not in the same Cauchy slice, then, you don't know how to think about this post-selection in that context, right? So yeah,
Sorry, so is a statement that you're most confident in the case where, I guess there are three things that happen. There are two maxi-mins and a maxi-mini-max.
Yep.
You're most confident when those things land on the same Cauchy slice, then everything is rigorous and fine. And if they land on different ones, of course, you can still write a formula, but you're saying it's less clear that it has to be true. Is that right?
Yep, it's less clear. It has to be true partially because this analogy with the tensor networks break because they don't live in the same Cauchy slice. So I don't know how to think about this post selection for things that live in different surfaces. So we didn't dig like too much into it, like this simple toy model where we can explicitly find this maxi mini max, like they happen to live in this nice slice. So that wasn't an issue, but I think in general, I don't know. I mean, I think it's worth looking in the model where they disagree and what exactly that means. The thing is, you might not be able to tell much about complexity in this case. Like you might write the formula, but like whether it's true or not. I guess it'd be interesting to have a case when like your formula gives you like maximal, like very hard complexity, but somehow in a fixed slice, it's actually low complexity. So like if you conjecture that you fix that they have to be in the same slice, then like there's a big disagreement between complexities. But I don't know an example like that where you can like hook up.
The maxi mini max is the one that worries me because if you have like that one can just run off if you have like a expanding universe or something. So why wasn't it enough to, once you use let's say the two minimal ones live on the same slice, why wasn't it enough to then do the mini max on that slice and not worry about maximizing overall slices? Why wasn't that good enough?
Good. I think for the Hawking radiation, you could do that, but it's a non-covariant proposal. I think for Hawking case, we could like say, okay, let's stick with this like a nice Cauchy slice and then use the tensor network prescription, right? Of finding minimax, doing minimax on the nice Cauchy slice. And that's what I did in this like pictures, and that's what we computed. Turns out that's the same as doing maxi minimax for the Hawking radiation case with the JT with like a like non-interacting fermions, right? It turns out to be the same. Whether there's like a more subtle differences between the two in other contexts, yeah, I don't know. I mean, it's hard to find the surface, I think, in like even interacting fermions, like, but for a fixed slice, Cauchy slice, you can find it, and it still gives you the right exponentiation. Yeah. So I guess we just wanted to have like a covariant definition. I think that's.
Yeah, I mean, the other covariant thing, which I thought it doesn't, well, it's different, I guess, is just instead of maxi mini max, to do a mini max, and not the mini max you meant, but the mini max, which is you just do a minimum in time and a maximum in space. So that's another covariantly defined extremal surface, but that's not the one. I guess that would not be the same as the one you're talking about, right?
No, it wouldn't be the same, because then with the maximum in space, it's a very like, you know, like you need to do this minimax in the space. Like just from a tensor network point of view, because you can arbitrarily make your cut larger. Like by like going on the network, you can have slicings, right? Like if you go from a wormhole left to the right, you can have arbitrarily like, but not arbitrary, but like quite large, but that's not the interesting surface. Like, you know, by like, like changing the slicing. So like in terms of like a network point of view, tensor network complexity point of view, this like minimax is a relevant one. The point is when you want to do this maximization over Cauchy slices, whether like you want to add it to have the covariant definition or not, or you want to like pick a slice and just use maximin on that slice. I think that's a subtlety we like haven't fully addressed. Like, but the toy examples we know they agree with each other basically. Like the places we can do it, like actually find the surface exactly, then they agree.
Okay, well, I'll probably ask you more offline, but I'll stop talking so other people can help.
Are there any more questions? Okay, if there are no more questions, then it's over to Arpan.
Okay, thanks again, Karan, for wonderful talk. So this was the last talk. So we conclude our workshop, and we thank all the speakers over 3 days and all the participants. And I should thank also my co-organizer, Shubho and Anindo. Also IIT Gandhinagar for providing logistics. And we hope that we can organize again this kind of workshop in future.
I just want to apologize to Ran because we didn't get to, it was the transition between Edgar and Ran was a bit rushed, so we didn't get to introduce him, but he introduced himself. Sorry about that.
No worries, no problem.
And yeah, I also forgot to wish you good morning and everything. They've come very early from the West Coast. Thank you very much. That's all.
Thanks, guys. Thanks for a great workshop.
Yep, great talking.
The videos will be posted in a couple of days. They're being processed and split up.
Share you the raw video over the meantime.
For the time being, we'll keep the recording, and then after a few days, for individual speakers, there'll be separate videos which will be put out. So, thank you very much again.
All right, bye everybody.
Bye.
বন্ধ করে আবার কল করছি।
Yeah, so I'm stopping the recording and then I'll